Hello, good morning to everyone, guys. I welcome you all to this wonderful channel by Unacademy NEET English. My name is Kar Khurshid Alam and you can also call me KK sir. All right, guys, enough about me. Tell me what's going on in your life. I believe everything is going good. But before we move ahead, I want a quick confirmation that if you can see me clearly and hear me clearly, let me know in the chats. Let me know in the chats if you can see me and hear me clearly. Let me know in the chat. Okay, all right. I believe we are live now and super excited to start today's session on GOC, which is the most important chapter of organic chemistry. We are going to discuss everything in this chapter, and that too from scratch, so that no question from GOC can even dare to bother you in NEET examinations. But let me tell you, if you have not studied anything from GOC yet, be with me. We will kick off the session very nicely. So without wasting much more time, let's get going. Now, first of all, you must remember what formal charge means. So let me tell you, it's a hypothetical charge assigned to an atom in a species, assuming that electrons in all chemical bonds are shared equally between atoms, regardless of relative electronegativities. Now, let's take one of the examples so that we can understand how to calculate formal charge of an atom. For example, if we are having H, C, H, and H. I mean to say for example, we are having CH3 and we have to calculate formal charge. We have to calculate formal charge, say for example, of this carbon. If we have to calculate formal charge of this carbon. Now, what will we do? First of all, we must know that hydrogen is having one valence electron when hydrogen is neutral. Similarly, boron is having 3 electrons in its valence shell. Carbon is having 4 electrons in its valence shell. Nitrogen is having 5. Similarly, phosphorus is having 5. Sulfur, oxygen is having 6, and similarly sulfur is having 6 valence electrons. But when these atoms or elements are what we call in neutral state. Similarly, if we talk about fluorine, fluorine is having 7. Similarly, chlorine is having 7, bromine is having 7, and iodine is having 7 electrons in its valence shell. But when these elements are neutral elements. Now, look towards this. As you can see over here, this carbon is bonded to hydrogen and one bond is made up of 2 electrons. Similarly, this bond is made up of 2 electrons. This bond is made up of 2 electrons. Now, what we have to do, we have to assign a formal charge to this atom. But for that purpose, we have to assume that this bond is made up of 2 electrons and these 2 electrons are equally shared between carbon and hydrogen. That means in this bond, only 1 electron is of carbon. Similarly, carbon is having only 1 electron here. Carbon is having 1 electron here. That means carbon in total is having what we call 3 electrons here. Now tell me, beta, if carbon is having 3 electrons here, can I say this carbon is having a lesser electron than neutral species? neutral species, neutral carbon is having 4 electrons in its valence shell, but this carbon is having only 3, which clearly indicates this is having 1 electron less than that of neutral carbon. So whenever any species is having less electron than neutral, we simply say that neutral species has basically lost its electron. So how many electrons have been lost? As neutral carbon is having 4 electrons, but in this species, neutral carbon is having only 3, which clearly indicates 4 minus 3. That means this is that carbon which loses 1 electron, which clearly indicates that its formal charge will be +1. I hope this is clear to everyone. Let me know in the chats, is this clear? Is this clear? Let me know. Is this clear? Okay. Now, am I audible, please? Let me know. Is this clear? Is this clear to everyone? Now, let's have another example. Let's have another example so that it's more clear to you. For example, we are having H, N, H, H, and H. Suppose we have to see what is the formal charge of this nitrogen. Then what will we do? And we know this bond is made up of 2 electrons. This bond is made up of 2 electrons. This is made up of 2 electrons. This is made up of 2 electrons. What we have to assume? We have to assume that these 2 electrons are equally shared between nitrogen and hydrogen, which clearly indicates among these 2 electrons, only 1 is of nitrogen. Similarly, in this bond, nitrogen is having only 1 electron. In this bond, nitrogen is having 1 electron. Similarly, in this bond, nitrogen is having 1 electron. What does that mean? That means nitrogen in this species in total is having 4 electrons. But in neutral state, nitrogen is having 5 electrons, which clearly means that this nitrogen is having 1 electron lesser. Whenever any species is having 1 electron lesser, that means that species will acquire a positive charge. So formal charge of this will be simply once again +1. Now, is this clear till now? Please let me know in the chat box, is this clear till now? I'm waiting for your chat reply. Is this clear to everyone? Is this clear to everyone till now? Okay. Okay, great. Now, let's take another example, and I will be waiting for your answer in this. What is the formal charge for this carbon? What is the formal charge of this carbon here? You have to answer me. Now, answer this question. This is very, very simple question, that what is the formal charge of this carbon? You have to answer. Come on. It's very, very easy, because I promise you that we will start this GOC from scratch. So let me know whether you are getting me or not. So let me the answer in chats. What will be its, I mean to say, formal charge? Formal charge of carbon in this example will be. Come on, come on, you have to answer, come on. And I know you can easily answer this question. Great. Yes, exactly, it's -1. Good, Shri. Yes, nice, nice, nice. That's great, that's great. Now, how we can solve this question? Simply, we have to check out whether carbon is having 4 electrons, 5 electrons, 3 electrons. How many electrons carbon is having in this species? Here it's 1, here in this bond it's 1, in this bond it's 1. Total 1, 1, 1, 3, 4, 5. That means this carbon is having 5 electrons. That means this carbon is having 1 electron greater than neutral carbon, clearly indicating its formal charge will be -1. Now, I hope you can calculate formal charge easily now. Now, another thing you must be knowing is hybridization. But for that, we have to calculate hybridization, and you must be knowing one of the formulas, that steric number or hybridization is equal to number of sigma bonds plus number of free lone pair of electrons. This is the formula which you must be knowing, and if the value of H comes out to be 3, or simply we can write down like this, if this comes out to be 4, hybridization is sp3. If this value comes out to be 3, its hybridization will be sp2, and if value comes out to be 2, its hybridization is sp. Now, in organic chemistry, we need these types of hybridizations only. One is sp, sp2, sp3. sp5 is another hybridization, but we don't need that as well. Now, so for example, to understand this, if I write an example like this, HC triple bond N, and suppose we have to calculate hybridization for this, I mean to say nitrogen. So what will be the hybridization for this nitrogen? We have to calculate, we have to count sigma bonds. We have to count what we call sigma bonds. Here, one is sigma, another two are pi. That means only one sigma is there and one lone pair of electron is there. So H is equal to number of sigma bonds. Here is only one for nitrogen, and there is one lone pair for nitrogen. So 1 plus 1 is 2. So its hybridization is sp. I hope this is clear till now. Similarly, if we take another example, guys, say for example, we will write CH2 double bond C double bond CH2, and if we want to know the hybridization of this middle carbon, what will be its hybridization? It's very simple. You can see this carbon forms a sigma bond from this side and one sigma bond from this side, and in total there are 2 sigma bonds and there will be no lone pair of electron. Hence, we can simply say hybridization is, I mean to say 2, because number of sigma bonds are 2, plus 0 because there is no lone pair. So the answer is 2. Hybridization will be sp. Now, tell me, is this clear till now? Please let me know in the chats that is this clear till now. Okay. Let me know in the chats, is this clear till now? Great. Come on. Come on. Tell me, is this clear till now? Great, great. You are giving answers nicely. Great, that's great, that's great. Now, I will give you one more example over here and you have to answer that question. What is the hybridization of carbon over here? Let me know in the chats quickly. Let me know in the chats quickly. What is the hybridization of this carbon here? Similarly, what is the hybridization of this carbon here? Similarly, you have to answer the hybridization of this carbon as well. I will be waiting for your answer quickly. Just write down the answer quickly. Write down the answer quickly. Come on, come on, come on, come on. Yes, yes. Great, great, great. Yes, nice. That means your basics are very much clear. Good, great. So its hybridization will be sp3, because the value of H comes out to be 4, because this is sigma bond, this is sigma bond, this is sigma bond, this is sigma bond. Number of sigma bonds is 4. There is no lone pair. Similarly here, sigma bond is, this is sigma bond and 2 more sigma bonds with CH amine say. In total, this is having 3 sigma bonds, so the hybridization will be sp2. This is 1 sigma bond and CH is also a sigma bond. In total, this is having 2 sigma bonds, no lone pair, so the hybridization will be sp. So I hope this is clear to you as well. Okay, just a moment. So this is basically formal charge. We are so I will rub this one, and because this was calculation of non-bonding electrons, I will simply rub out this one. So next topic will be calculation of non-bonding electrons. How will you calculate non-bonding electrons? So next topic will be calculation of non-bonding electron, guys. So after hybridization calculation, now next will be calculation of, next will be simply calculation of non-bonding electrons. What are non-bonding electrons? You all must be knowing that. Non-bonding electrons, those electrons which do not take part in bonding, these are known as non-bonding electrons. Now, have a look. If, say, for example, you are given this example and you have to find out number of non-bonding electrons in this. You have to find out number of non-bonding electrons in oxygen. How will we find out number of non-bonding electrons? Now listen carefully. This oxygen is having positive charge. That clearly indicates that neutral oxygen has lost 1 electron. How many electrons were present in neutral oxygen in its valence shell when oxygen is neutral in its valence shell is having, say 6 in its valence shell, there are 6 electrons. That means a valence shell of oxygen in neutral state is having 6 electrons. But this is having positive charge. That means that valence electron, 1 has been lost from that, because neutral species having 6 electrons, that means positively charged has lost 1 electron, clearly indicating total electron in its valence shell must be 5. Why? Because neutral oxygen in its valence shell have 6 electrons. So O positive means that neutral species has lost 1 electron, so it's having in total 5 electrons. But among these 5 electrons, this electron is what we call bonding electron. This is also bonding electron of oxygen. This is also bonding electron of oxygen, because another electron is of hydrogen. This is of hydrogen. This is of hydrogen. But we have to calculate electrons of oxygen only. So 1, 2, 3. So among these 5 electrons, 3 are bonding electrons. 3 are bonding electrons. Now, tell me, we have to calculate non-bonding electrons. So total we have 5 electrons, 3 are bonding electrons. So can I say 2 are non-bonding electrons? So 2 are non-bonding electrons. I hope this is clear to everyone. So whenever non-bonding electrons are 2, we can simply call that as lone pair. So we can simply say this is having 1 lone pair of electron. So this structure then becomes like this. It is H, O, H, H, and O is having a lone pair and a positive charge. Now tell me, is this clear to everyone? Can you calculate now number of non-bonding electrons easily? But before moving ahead, let us take another example so that this is more clear to everyone. Now, have a look. If I write like this, H, C, H, H, and then having a negative charge on carbon. Now, tell me how many non-bonding electrons are present in this carbon. We can calculate like this. Now carbon, neutral carbon contains 4 valence electrons, but this carbon is having negative charge. What does that mean? That means neutral carbon has gained 1 electron. That means 4 electrons were present in neutral. Now carbon having negative charge contains 5 electrons because 1 electron has been gained by a neutral carbon. So total electrons present in carbon are 5. Now this bond is made up of 2 electrons, this bond is made up of 2 electrons, this bond is made up of 2 electrons, but we have to count electrons of carbon only, not of hydrogen. So carbon is having total 1, 2, 3 electrons here, which are bonding electrons. So among 5, carbon is having 3 bonding electrons, and in total carbon was having 5 electrons. If 3 are bonding electrons, 2 will be non-bonding electrons. Or we can simply say 1 lone pair of electron. Similarly, if I write an example like this, ON double bond O, and here it's a positive charge and here it's a negative charge, and we have to calculate non-bonding electrons over this oxygen, over this nitrogen, and this oxygen. So how will we calculate? Now look, if I talk about this oxygen is having negative charge. That means neutral oxygen has gained 1 electron, and neutral oxygen in its valence shell contains 6 electrons. So this oxygen contains 7 electrons. Now, if this is having 7 electrons, here in this bond, oxygen is having only 1 electron because another electron is of nitrogen. So oxygen is having only 1 electron, but in total it's having 7 electrons. What does that mean? That clearly indicates among these 7, 1 electron is bonding electron. If 1 electron is bonding, what about the rest of the electrons? That means 6 electrons are non-bonding. 6 electrons are non-bonding. Now, if we talk about this oxygen, as this oxygen is neutral, neutral oxygen always contains 6 electrons in its outermost shell. Now, here this electron is of oxygen, this electron is of oxygen, because this and this are of nitrogen. So there are 2 electrons which are over here in bonding state. So among 6 electrons, 2 are bonding electrons, or 2 electrons are bonding electrons. So total was 6 electrons were there, but among 6, 2 are bonding, hence 4 electrons are non-bonding. Similarly, if we talk about this nitrogen, this is having a positive charge. When nitrogen is having positive charge, neutral nitrogen were having 5 electrons in its outermost shell. Positively charged nitrogen means 4 electrons only in its outermost shell, because neutral has lost 1 electron. Now, if it's having 4 electrons, how many electrons are bonding? 1, 2, 3. 3 are bonding. So 3 are bonding. 3 electrons are bonding electrons. So 1 will be non-bonding. 1 electron will be non-bonding electron. Now, if I write this structure once again, so I will write like this: ON double bond O. This is having 1 electron. This is having 4 non-bonding electrons, and this is having 6 non-bonding electrons. I hope you can calculate now non-bonding electrons. Let me know in the chats, is this clear till now? Let me know in the chats, is this clear till now? Is this clear till now? Can you calculate formal charge? Can you calculate hybridization? And can you calculate what we call non-bonding electrons? Please let me know in the chat box. Is this clear to everyone? Is this clear to everyone? Yes, sir, it's clear. Okay, now let's move ahead and look towards another definition, and that definition is volume charge density, which we can write like this: VCD. Remember, volume charge density, or VCD, is simply magnitude of charge upon size or volume. So this is what we call volume charge density. Now we know charge may be either positive or negative. So for that purpose, positive volume charge density is magnitude of positive charge. It's magnitude of positive charge upon size. And negative volume charge density is equal to magnitude of negative charge upon size. But what we have to remember is that you have to note down this, that stability of any charged species, stability of any charged species, whether it is a positive charged species or a negative charged species, it is inversely proportional to volume charge density. You have to remember this, that stability of any charged species is inversely proportional to its volume charge density. I hope this is clear, that this formula, positive volume charge density and negative volume charge density, you have to remember. Now, if you have to, say, arrange the stability or compare the stability of charged species, say for example, if you have to compare, say for example, we have to compare stability. We have to compare stability. Say for example, we have to compare stability of F having a positive charge, or we can simply say F having a negative charge. Number second, we have to calculate negative charge on chlorine, negative charge on bromine, and negative charge on iodine. So as these are negative charged species, so I will write negative volume charge density is equal to magnitude of negative charge upon size. Now have a look. As magnitude of charge in F minus, Cl minus, Br minus and I minus is same. So this is, say, constant. So can I say negative volume charge density is inversely proportional to size? Negative volume charge density is inversely proportional to size. So can I say as magnitude of negative charge is same. Magnitude of negative charge is same everywhere in F minus, Cl minus, Br minus, I minus. Therefore, negative volume charge density is inversely proportional to size. What does that mean? That means any species which is having lesser size is having more negative volume charge density, and any species whose size is larger is having lesser volume charge density. Now, we know F, Cl, Br, I. We know F, Cl, Br and I. F, Cl, Br and I. They belong to the same group, and on moving from top to bottom, we know size increases. So can I say fluorine is having the smallest size and iodine is having the largest size among these four? Now tell me, if size of fluorine is small, can I say its volume charge density is large? So what will be the order of volume charge density? What will be the order of negative volume charge density? Can I say that will be size of fluorine is lesser, hence its volume charge density is greater. So F is having more negative volume charge density. After that, it's having Cl minus. After that, it's having Br minus. After that, it is having I minus. So therefore, what will be the stability order? What will be the stability order? Stability order is reverse of that. Why? Because you can have a look over here, because stability of any charged species is inversely proportional to volume charge density. So here stability order will be I minus greater than Br minus greater than Cl minus greater than F minus. I hope this is clear to everyone. I hope this is clear to everyone. Now, our another topic that we must be knowing is electronegativity. What is electronegativity? You all must be knowing it is simply the tendency. It is the tendency of an element. It is the tendency of an element to attract shared pair of electrons. To attract shared pair of electrons towards itself. Now, if we talk about, if we here talk about elements, so for elements, we know on moving from left to right along a particular period, electronegativity increases, but size decreases. That means electronegativity and size are inversely related as per elements are concerned along a period. Similarly, on moving from top to bottom along a group, electronegativity decreases, but size increases. Once again, it's clear that elements along a period as well as along a group, they are having electronegativity and size which are inversely related to each other. So can I say for elements, electronegativity, which is denoted by this, and this is known as chi, it is inversely proportional to size. So for elements, remember forever, electronegativity is inversely proportional to size. Now have a look. So you have to remember this formula that electronegativity is inversely proportional to size. Next, if I talk about orbitals, here for orbitals, remember electronegativity is directly proportional to force of attraction between nucleus and electrons. What is meant by that? Now have a look. We know this is nucleus and these are different subshells and orbitals, and we know S orbital or S subshell is very closer to nucleus, and there will be more attraction between this positively charged species, positively charged nucleus, and negatively charged electron present in S, P, D and F. There will be attraction, but where attraction will be more? According to Coulomb's law, you know, according to Coulomb's law, you must be knowing this in physics, that according to Coulomb's law, F is inversely proportional to square of the distance between two opposite charges. That means here distance is very less. Here distance increases, then this is, say larger distance. Now, where distance is less, in S orbital, electron is more attracted towards nucleus. That means electronegativity of S is greater. So therefore, we can simply say electronegativity of S is greater than electronegativity of P is greater than electronegativity of D is greater than electronegativity of F. So you have to remember this as well, that electronegativity of S is greater than electronegativity of P is greater than electronegativity of D and electronegativity of F. Now, next, you must be knowing that we have hybrid orbitals. What hybrid orbitals are actually? So for hybrid orbitals, remember, electronegativity is basically directly proportional to percentage of S, as electronegativity of S is greater. Now the question is, if percentage of S, how to calculate percentage of S? Percentage of S is basically 1 upon 1 plus n into 100. Now here this n means, number of p orbitals. Now have a look. If we are having sp hybridization, then hybrid orbitals will be sp. hybrid orbitals will be sp2, hybrid orbitals will be sp3. Now, according to this equation, here S percentage will be 50%. It's 50% S character. Here, its S character will be 33.33%. And this is having 25% S character. Now, more the S character, more will be the electronegativity, because we know S is having more electronegativity. So, here we calculate only S character, because electronegativity is more dependent on S as compared to P. So, here S character is more. So, therefore, we can simply say electronegativity of sp in general is greater than electronegativity of sp2 hybrid orbital, which in turn is more electronegative than sp3 hybrid orbital. Now, is this clear to everyone? Is this clear to everyone? So, here this is for elements, this is for orbitals, and this is for hybrid orbitals. Now, next is, once again, if I write sp, sp2 and sp3, this is having 50% S character, this is having 33.33% S character, this is having 25% S character. But what about bond angles? What about bond angles? You know, in hybridization, you have already, teacher have already shown that this is having 180-degree bond angle, and this is having what we call 120-degree bond angle, and this is having 109-degree 28 minutes. So this is bond angle, and this information is of about S character. So this is S character information, and this is the information of bond angle. Now tell me, on moving from this side to this side, what will happen to bond angle? Once it was 180, then 120, then 19. That means bond angle from this side to this side decreases. Okay, what will happen to percentage of S? Can I say percentage of S also decreases? From these two, can I say that bond angle is directly proportional to percentage of S character, or percentage of S character is directly proportional to bond angle? Now, so can I say now, as we know, electronegativity of hybrid orbital is directly proportional to percentage of S, but percentage of S is directly proportional to bond angle. So now, can I say electronegativity is directly proportional to bond angle as well? Now tell me, is this clear till now? Is this clear till now? Let me know in the chat box. Is this clear till now? Is this clear till now? Is this clear till now? Is this clear? Okay, great. Great. Now, after that, for alicyclic rings, if we talk about alicyclic rings like a cyclopropane, cyclobutane, cyclopentane, say for example a ring like this, and ring like this. No, here inner angle is 60 degree, here inner bond angle is 90 degree, and here inner angle is 108 degree, which means its actual, or we can write down like this, its expected bond angle of this cyclopropane should be 109 degree 28 minutes, because it forms only sigma bonds. Similarly, its expected bond angle should be 109.28 minutes. Similarly, 109 degree, 28 minutes. But what is actual bond angle over here? What is actual bond angle over here? Its actual bond angle is 60 degree. Its actual bond angle is 90 degree. And its actual inner bond angle is 108 degree. So, can we say there is deviation from normal angle? There is deviation from expected angle. Whenever there is deviation from actual angle, that species, that molecule is always having an angle strain. So this molecule is having angle strain, this is having angle strain, this is having angle strain. But the question is, which among these is having more angle strain? Now, you can calculate 109 and 60. 109 minus 60 comes out to be approximately 49 degree. Similarly, comes out to be approximately 19 degree. It comes out to be approximately 1 degree. Now the question is, which among these is having more strain, more angle strain? It's this one. So remember, for rings like these, electronegativity is directly proportional to angle strain. Any ring which is having more angle strain is basically having more S character. And more S character means more electronegativity. Now tell me guys, whose electronegativity is greater? Can I say that electronegativity order will be simply, it's 3-membered ring, after that it's 4-membered, after that it is a 5-membered ring. So this is the electronegativity order. I hope this is clear till now. Now, after that, remember forever, if you have species like, if you have any element with a positive charge, if any atom is having a complete positive charge, then another atom is having partial positive charge, another atom is a neutral species, then you are having partial negative charge on an atom, and then atom is having complete negative charge. So what will be the electronegativity order? Means say among these species, A positive can simply pull, or what we call attract electrons towards itself more, hence its electronegativity will be greater than this, than this, than this. Now you have to remember this as well. You have to remember this as well. After that, in general, we know F is more electronegative as compared to oxygen. Oxygen is more electronegative as compared to nitrogen. Nitrogen is more electronegative as per carbon is concerned. So this is electronegativity order in general. But remember, if we are having F whose hybridization is sp3, then oxygen, sp2 and sp3. After that, nitrogen, sp, sp2, sp3. Similarly, carbon, sp, then sp2 and then sp3. Here, what will happen? Now, have a look. First of all, electronegativity order will be like this. Electronegativity order will be like this. Fluorine is always more electronegative as compared to oxygen, nitrogen and carbon, irrespective of hybridization. So, fluorine is always more electronegative than oxygen, nitrogen, carbon, irrespective of electronegativity. But oxygen, after that, sp2 oxygen, it should be oxygen sp3. But what happens over here, there will be like this. Now have a look. Nitrogen jumps in electronegativity order over oxygen. So can I say here one jump has been taken place by nitrogen. So whenever you are having hybridization, like oxygen is having sp3 hybridization and nitrogen is having sp hybridization, remember it is nitrogen which is having sp hybridization. It's having more electronegativity as compared to oxygen with sp3 hybridization. Similarly, after that you will write nitrogen sp2. after that it's not nitrogen sp3, it's carbon sp and then nitrogen sp3, and after that it is carbon sp2 and carbon sp3. So here once again carbon has jumped as per electronegativity is concerned. So one jump is observed over here also. So this is modified EN scale. You must remember this. This is modified EN order. This is modified EN order. Actually, nitrogen should have lower electronegativity than oxygen, but nitrogen, when it's present in sp hybridization state, it's more electronegative than oxygen, sp3 hybridized. Similarly, if carbon is present in sp hybridization state, it's more electronegative than nitrogen, which is present in sp3 hybridization state. Now, so this was all about electronegativity. Now, next, what we have here is stability of charge. Now, remember, along a period, if we talk about along a period, you must remember this one, that stability of charged species depends on electronegativity. Depends on electronegativity. It depends on electronegativity. When charged species stability depends on electronegativity, along a period, if charged species belong to the same period, at that time you have to check out what is the electronegativity, and you have to remember these 2 points. Negative charged species is considered more stable. It's considered more stable when charge is present on more electronegative element. More electronegative element. In nutshell, men. Similarly, positive charge is considered, positively charged species is considered more stable. But when it's present on less electronegative element, that means LEN. What does that mean? Let's understand this with the help of an example. For example, example is like this. Example is like this. Now, if you are having CH3 minus, second, you are having NH2 minus, you are having OH minus, and you are having F minus. Now, you have to compare stability of these. Now, first of all, negative charge is present on carbon, nitrogen, oxygen, fluorine. That means the elements on which negative charge is present, they belong to the same period. They belong to the same period. Now, have a look. If they belong to the same period, now, their stability now depends on electronegativity. Now, the question is, which type of charged species is this? Is this a positive charged species or a negative charged species? Negative charged species. That means we have to find out its electronegativity. We know electronegativity in this direction increases. Electronegativity in this direction increases. Now, have a look. What we have written over here, negative charged species is more stable. Negative charged species is more stable if negative charge is present on more electronegative elements. So which one is more electronegative element? F minus. So therefore stability order will be like this. Stability order will be simply F minus greater than OH minus greater than CH3 minus, sorry, greater than NH2 minus and greater than CH3 minus. So whenever negatively charged species are given and that too belongs to the same period, you have to remember that negatively charged species stability is dependent on electronegativity. How? Because negative charge present on more electronegative element should be more stable. I hope this is clear to everyone. Now, if similar elements, I mean say if elements are once again present along the same period, but on those elements, now it will not be the negative charge, but it will be a positive charge. Then what will happen? I mean to say, if you are having CH3 with a positive charge, after that you are having NH2 with a positive charge, after that you are having what we call OH with a positive charge. Now after that you are having what we call F with a positive charge. Now first of all, we know that carbon, nitrogen, oxygen, fluorine, they belong to the same period, and same period, this is the trend that electronegativity increases on moving from left to right. So as these are positively charged species, positive charge is stable on less electronegative elements. So which among these is less electronegative? It's carbon. So can I write stability order over here? Stability order will be simply 1 greater than 2, greater than 3, greater than 4. I hope this is clear to everyone. Now, after that, along a group, you have to remember this one. Stability of any charged species, whether it is positive charge or a negative charge, stability of any charged species is directly proportional to size. It's not only dependent, but it is directly proportional to the size. That means any charged species whose size is large, negative charge or positive charge will be more stable than that. For example, let's take an example. If you have to compare stability of F negative, Cl negative, Br negative, and I negative, we know F, Cl, Br, I, they belong to the same group, and in group, on moving from top to bottom, size increases. So F, Cl, Br, I is having the largest size. Whose size is more, positive or negative charge will be more stable on that. Therefore, what will be the stability order? So stability order among these charged species will be simply I minus, greater than Br minus, greater than Cl minus, greater than F minus. Now tell me, is this clear till now? Now tell me, is this clear till now? Let me know in the chats. Is this clear till now? Let me know in the chats. Is this clear till now? Yeah, definitely. I will do every chapter in organic chemistry. So don't worry about that. And that too from scratch. And Wasim sir is taking care of physical and inorganic, and I will be taking your whole organic chemistry. Someone is writing that code of organic chemistry. Thank you very much. Okay, so this is clear. Okay, now this is clear to everyone. Now, after that, let's practice. Here are a few questions. Now try to answer the first question and let me know in the chat box what will be the answer of first, second, and third. Quickly. What will be the answer of first, second, and third? What will be the answer of question number first, question number second, and question number third? Now, let me know in the chat box. What will be the answer of question number 1, question number 2, question number 3? Come on quickly. Let me know the answer of question number 1. First of all, you have to look towards the question and see whether these elements belong to the same period or they belong to the same group. They belong to the same period or they belong to the same group. Okay, someone has written that it's 4, 3, 2, 1. Okay, that's great. Now, have a look. Carbon, nitrogen, oxygen, fluorine, they belong to the same period. When elements belong to the same period, when charged species belong to the same period, we have to, look towards their electronegativity. And we know on moving from carbon, nitrogen, oxygen, fluorine, fluorine is most electronegative and negative charge present on fluorine is more stable. So the answer is exactly 4, 3, 2, and 1. What about second and what about third? Nice, great. Many students are already giving me the answer. Now, great, great, great. What about this? Can I say sulfur and chlorine? They belong to the same period. So, sulfur and chlorine belong to the same period. Both are negatively charged species. So, negative charge is present more on mole electronegative element, that is chlorine. So, the answer is 2 greater than 1. What about O, S, Se and Te? They belong to the same group. And here size. So, the answer is 4, 3, 2, 1. You have to write down the answer as well as the reason, because otherwise it will be very difficult for you to revise organic chemistry. You have to write down the reason as well. Now, listen carefully. Here, negative charge is present on carbon, carbon, carbon. What does that mean? These elements having negative charge, they are same. Remember forever, whenever negative charge or positive charge is present on same element, at that time, once again, you have to look towards electronegativity. How? Now, this is having sp hybridization. This is having sp2 hybridization. This is having sp3 hybridization. Do you know that more the electronegativity, more will be the S character, or more the S character, more will be electronegativity. And whenever it is what we call sp hybridization, S character is 50%. Whenever it is sp2 hybridization, then S character is always 33.3%. And whenever it is sp3 hybridization, we have 25% S character. Now tell me, among these carbons, which one is most electronegative carbon? This one. And negative charge and more electronegative element is more stable. That means it is simply 1, after that 2, after that 3. Now, after that, I want to know the answer of this one. Write down quickly the answer of this question. Write down the answer of this question quickly. Write down. Yes. Come on, you can do it. Come on, you can do it. Write down the answer. I need the answer of this quickly. Great. Yes, you can do it. Great. Okay, now have a look. This is nitrogen, this is carbon. In general, nitrogen is more electronegative than carbon, and both belongs to the same period. That means electronegativity will decide the answer. But the question is this carbon having sp hybridization? Answer is yes. What about this nitrogen? Its hybridization is sp3. And I have already written over here modified electronegativity. When carbon is sp and nitrogen is sp3, which one is more electronegative? It's carbon, not nitrogen. Hence, here we will write down like this, as this is sp hybridized carbon, this is sp3 hybridized nitrogen. This is more electronegative as compared to this. So the answer becomes 1 greater than 2. I hope this is clear to everyone. So it's not 2 greater than 1, it's 1 greater than 2. Why? Because carbon is sp hybridized and nitrogen is sp3 hybridized. At that time, we have to write down modified electronegativity order. So this is more electronegative. Negative charge present on this carbon is more stable than negative charge present on nitrogen. Is this clear? Is this clear? Because most of the students write 2 greater than 1. Is this clear? Why 1 greater than 2? Let me know in the chats. Is this clear? Let me know in the chats. Is this clear to everyone? Come on. Okay. Now, next is nitrogen is having negative charge, oxygen having negative charge, sulfur having negative charge, chlorine is having negative charge. So this is a mixed type of question. Now, have a look. This is nitrogen and oxygen belongs to the same period. Now, after that, oxygen and sulfur belongs to the same group. Sulfur and chlorine belongs to the same period. Now, first of all, here we will see electronegativity. We will see electronegativity over here. If nitrogen is having negative charge, oxygen is having negative charge. Which one is more electronegative? Oxygen. So oxygen is more electronegative than nitrogen. So it will be like this. After that, we have to consider, say this, we have to consider this, oxygen and sulfur, because they belong to the same group. So we have to consider size over here. Whose size is greater, oxygen or sulfur? If this is having negative charge, whose size is greater? It is of sulfur. After that, you have once again to consider this one. You have to consider this, say electronegativity. So whose electronegativity is more? It's of chlorine. I hope you are getting me what I'm talking about. Now, tell me, nitrogen having negative charge is less stable than oxygen having negative charge. Oxygen having negative charge is less stable than sulfur having negative charge. Sulfur having negative charge is less stable than chlorine having negative charge. So what will be the answer? Chlorine, that means 4, will be first, more stable, then third, then second, and then 1. Is this clear to everyone? Is this clear to everyone? Okay. Now, next, what you have to remember is electronic displacement effect. Now, here it's written that electronic displacement effect is the displacement of electrons, whether that displacement is partial or that displacement is complete. So, displacement of electron, whether complete or partial displacement within a species, which can affect its stability or reactivity. You know, if species gets more charge, it becomes more reactive, and its species is having lesser charge, it's lesser reactive, and more reactive species means less stable, and less reactive species means more stable. Now have a look. If we are talking about CH3 CH2Cl, electrons, here we know chlorine is more electronegative than carbon. So these electrons are partially transferred towards chlorine. So electrons are transferred towards chlorine. So chlorine will acquire a partial negative charge and carbon will acquire a partial positive charge. Now listen, what will happen here? Here basically partial transfer of electron has been taken place. And if we talk about CH2 double bond CH2, and in presence of a reagent H positive, what will happen? When H positive approach this pi electron density, it will simply attract these electrons towards itself. But what will happen over here? Here it becomes like this. CH2 and H means CH3. Electrons have been, transferred toward this carbon. So this carbon will acquire a complete positive charge. Whenever species acquires complete positive or complete negative charge, that means this is complete transfer of electrons. Here it is partial transfer of electrons. Now tell me, due to partial transfer of electron, can I say partial positive, partial negative? In nutshell, polarity arises. Here also, complete positive charge means polarity or polarization occurs. Whenever positive and negative charges or polarity occurs in a molecule, its reactivity will change, hence its stability will change. So that displacement effect or that displacement of electron, whether it is partial, whether it is complete, which can simply affect stability or reactivity of these species, is known as electronic displacement effects. And let me tell you that electronic displacement effects are of two types. One is permanent and another is temporary. Now have a look. Whenever you talk about chloroethane or ethyl chloride, whether this chloroethane or ethyl chloride is present in Kashmir or it is present in Bangalore, wherever chloroethane is present, these electrons will be always transferred towards chlorine. That means here displacement of electron is always present, irrespective of an external reagent, whether that reagent is present or absent, that hardly matters. What we observe over here, that here will be always complete transfer of electrons in chloroethane. That means this displacement is always present. That means this is its inherent property. Hence, this is known as a permanent displacement of sigma electron. But now have a look. In presence of this reagent, displacement occurs. But if I remove this, say H positive, say for example, if I write CH2 double bond CH2 like this without reagent, There will be no displacement of electron because electrons are present between similar electronegative species. So there is no displacement of electron if reagent is absent. There is displacement of electron if reagent is present. So that type of displacement of electron which takes place in presence of reagent and is absent in absence of reagent, this type of displacement is known as temporary displacement. So this is permanent displacement which is always present in a molecule, and it is its inherent property, and this is temporary which is present only at the time of attacking reagent or reagent and absent if reagent is absent. Now have a look what we have written. Now permanent displacement is that electron displacement which is always present. Remember, it's always present within a species like chloroethane, okay? Due to its inherent property resulting in a permanent polarization of the bond and affecting, whenever polarization takes place, affecting the molecule's reactivity without the need of external attacking reagent. Here we don't need any external reagent. Here permanent polarization will take place in a bond, and that will be due to its inherent property. That's why this is known as permanent displacement effect. Now after that, temporary effect. It is a temporary displacement of electrons within a species, usually in response to an external attacking reagent. That means this type of displacement of electron takes place only in presence of reagent. If reagent is removed, there will be no displacement of electrons. Now remember, first of all, we will see types of permanent displacement effect. And this permanent displacement effect is very, very important as per GOC is concerned. And we are having three types. Number one is inductive effect. Another one will be mesomeric effect. And the third one over here will be hyperconjugation effect. And among these three, remember forever, mesomeric effect, or this is also known as resonance effect. Resonance effect. So this resonance effect is powerful than hyperconjugation effect, is powerful than inductive effect. You have to remember this, but here we will write note except halogens. That means in case of halogens, it is inductive effect which is powerful than resonance and hyperconjugation. So this is what you have to remember. Now, these are types of permanent effects. After that, if we talk about types of temporary effects, we have number one, that is inductomeric effect. And number second, that is electromeric effect. And here you can remember that electromeric effect is stronger than inductomeric effect. Now, let us start with what we call inductive effect or transmission effect. Now, try to understand what inductive effect actually means or what transmission effect actually means. Have a look. If I write a carbon chain like this, carbon single bond, carbon single bond, carbon. Now we know carbon can form 4 bonds, but filhal, I mean to say we can write down like this, we can show these bonds like this. Now tell me, if I talk about carbon single bond carbon, I mean say this bond, do you know Carbon-carbon single bond or any single bond is made up of electrons. Now tell me, if this is made up of 2 electrons, this bond is made up of 2 electrons, where those electrons will move? Will they move towards this carbon or this carbon? That depends on electronegativity difference. But we know both these carbons have same electronegativity, hence electron clouds will be symmetrically distributed between these. If electron cloud is symmetrically distributed between these 2 carbons, that means neither of them will acquire positive charge nor a negative charge. Hence, this bond is a non-polar bond. Similarly, this bond is also a non-polar bond. Overall, this molecule is a non-polar molecule because there is no transfer of electrons. So this is non-polar molecule. But if I write like this, CCl, we know Cl is more electronegative than carbon. What will happen? Electrons will move towards chlorine, and chlorine will acquire negative charge, and carbon will acquire a partial positive charge. So can I say this becomes a polar bond? This becomes polar. Similarly, if I write CMgBr, what is Mg? Mg is magnesium and it's a metal, and we know magnesium and carbon is more electronegative than metal, so carbon will withdraw its electron towards itself, so carbon will acquire partial negative charge and magnesium partial positive charge, hence polar. Now tell me, chlorine here withdraws electron. If chlorine withdraws electron, can I say carbon donates electron? Because withdraw and donation, these are 2 relative terms. Similarly, if carbon withdraws electron, MgBr donates electron. So can I write like this? If carbon is attached to electron withdrawing group, here will be a partial negative charge, here partial positive charge. Similarly, if carbon is attached to electron donating group, because this is electron donating, so I will show like this. Okay? Now, this is having partial negative charge and this is having partial positive charge. Now, these are polar and these bonds are what we call non-polar. Now, tell me, if I join this with this, say for example, if I write like this, now what will happen now? First of all, there is electronegativity difference between chlorine and carbon. Electrons will move towards chlorine, and chlorine will acquire a partial negative charge, and similar partial positive charge will be acquired by carbon. Now tell me, here carbon and carbon was having same electronegativity. That's why bond was non-polar. But what will happen over here? This carbon is having partial positive charge and this carbon is neutral. We have already shown over here, whenever element, now have a look, whenever element is having partial positive charge and another element is neutral, which one is more electronegative? Partial positive charge. Now, if partial positive charge element is more electronegative, now have a look, partial positive charge element is more electronegative than neutral carbon. What will happen to electrons? These will be transferred towards this carbon, and this carbon will also acquire another, say positive charge. Now, remember, this carbon will acquire partial positive charge. This is partial positive, this is having partial positive charge. Similarly, now this is having partial positive charge, this is neutral, the electrons will be transferred towards this, and this will be having partial positive charge. Now tell me, can I say if this is bond 1, this is bond 2, now please try to understand, this is bond 3. Can I say in bond 2, polarization has been taken place? Polarization has been taken place. Positively charges, it becomes positive charge. Now polarization takes place in this bond, but it becomes polar only if this was having positive charge. If this was having if this carbon was not having any charge, then this and this both are neutral carbons, so electron will neither move towards this nor towards this. At that time this will not be a polar bond, but this is polar. Why this is polar? Why polarization occurs? Due to partial positive charge over here. Now tell me, why this carbon acquires partial positive charge? Can I say it is because of this bond, because of this chlorine? So can I say this is polarized, this bond is polarized, or polarization occurs in this bond due to polarization of this bond? Can I say in this second bond polarization occurs due to polarization of first? Similarly, in third bond polarization occurs due to polarization of to second. So this phenomenon in which polarization of any sigma bond takes place due to polarization of its adjacent sigma bond. Polarization of any sigma bond takes place due to polarization of its adjacent sigma bond. This phenomenon is known as inductive effect or transmission effect. So how can we define inductive effect? So can I say definition of inductive effect is like this: polarization of any sigma bond, polarization of any sigma bond due to polarization of its adjacent, due to polarization of its adjacent sigma bond is called inductive effect or is called transmission effect. So remember this. Now why this is known as inductive effect? Now have a look. As polarization has been induced in this due to polarization of this. Similarly, that polarization has been induced in this due to polarization of this. Another thing what you have to remember is that partial positive charge is greater than partial positive charge is greater than partial positive charge, which means on moving from say chlorine, or if distance is increased from this electron withdrawing group or chlorine, say polarization or displacement of sigma electron, that decreases. And what is this polarization or displacement of sigma electron? This is inductive effect. So hence we can simply say on moving away from electron withdrawing group or on increasing distance, inductive effect decreases. Similarly, if I write like this, C and after that MgBr, what will happen over here? Now this will donate its electron or this will attract electrons, so this will be negative charge, this will be positive charge. Now this is negatively charged and this is what we call neutral carbon. Negative charge will repel electrons towards this, or neutral carbon is more electronegative than negative, so it will acquire partial negative charge. Similarly, partial negative charge. Similarly, in this second bond, polarization occurs due to polarization of first. Similarly, in third bond, polarization occurs due to polarization of second. So polarization of any sigma bond due to polarization of its adjacent bond. Similarly, polarization of any sigma bond due to polarization of its adjacent sigma bond is known as inductive effect. Now tell me guys, is this clear to everyone or not? Is this clear to everyone or not? Because after that we will write down its characteristics. Now, is this clear till now? Please let me know in the chat box. Is this clear to everyone? Let me know in the chat box. Okay, clear, sir. Thank you. Thanks for replying. Now, after that, characteristics. Point number one. Can I say it's a permanent effect? Because it's a type of permanent effect, so it's a permanent effect. It is a permanent effect. Number second point. Second point, you must know this one, that it involves displacement of sigma electrons only. Involves displacement of sigma electrons only, not pi electrons, only and only sigma electrons. Point number third, it is unidirectional. Now have a look. Whenever you are having CCl bond, that electronegativity difference between Cl and C, or we can simply say that polarization or displacement of electron will be always towards chlorine. Displacement of electron will be always towards chlorine. In this bond, it is towards chlorine. In this bond, it's towards chlorine. In this bond, it is towards chlorine. In this bond, it is towards chlorine. It's not that here it is towards chlorine and it is here it is towards carbon. It's not like that. It's always unidirectional. In CCl bond, it's always towards chlorine. In this CCl bond, it's always towards chlorine. In this CCl bond, it's always towards chlorine. In this CCl bond, it's always towards chlorine. I hope this is clear that this is unidirectional. And if it is unidirectional, can I say it is irreversible? It is irreversible. It cannot be reversed. It is irreversible. Number 5th point is that you have to remember that it's unidirectional, it is irreversible, and after that, remember, displaced, or we can write down first of all like this, it is distance dependent. It is distance dependent and decreases with increase in distance. Decreases with increase in distance. I have already shown this. As distance increases from electron withdrawing group, or say chlorine, or electron donating group, or MgBr, as distance increases, we know this slight negative is greater than slight negative is greater than slight negative. That means this decreases. Displacement, of electron or polarization decreases, or in nutshell, inductive effect decreases as distance increases. So it's distance dependent. After that, it dies off beyond 3 carbon atoms. In general, beyond 3 carbon atoms, we do not take inductive effect. Generally, it dies off beyond 3 carbon atoms. If other effects are absent, then we take inductive effect. In general, we do not take inductive effect beyond 3 carbon atoms. That is the reason I have shown only partial positive, partial positive, partial positive, because here inductive effect is very, very, very less. So we generally do not take that inductive effect. Now, next point is like this. Displaced sigma electrons during inductive effect do not leave their orbitals. They do not leave their orbitals. Instead, a little distortion of orbital takes place. Little distortion of orbital takes place. Due to which polarization occurs. What is meant by that? Have a look. If we talk about carbon and carbon, we know electron distribution is symmetrical. So let us suppose this is electron distribution in this sigma bond or sigma orbital. So we can simply say this is symmetrical sigma orbital, because electronic distribution in this orbital is symmetrical. So this is symmetrical, sigma orbital. But if we talk about CCl, what will happen? Electrons will move towards chlorine. That means electron density at chlorine will be more as compared to carbon. So can I show like this? So electron density here is more and here it is less. It is less, it's more. So this orbital is not now symmetrical. It's irregular. It is what we call unsymmetrical, or we can simply say this is distorted sigma orbital. This is distorted sigma orbital. And due to which electrons will move towards chlorine more. That's why this becomes distorted. Here is electron density is more, here electron density is less. So due to which it becomes partial negative charge and this becomes partial positive charge. But electrons are displaced, but they do not leave their orbital. They are partially displaced towards an element. Similarly, if I talk about CMGBr, say electron donating group attached to carbon, what will happen? Electron density here will be more at carbon and less at magnesium. So here electron density is more, here it is less. That means it is not a regular or symmetrical distribution. So this is known as distorted sigma orbital. And due to this distortion, what will happen? This will acquire slight negative charge and this will acquire slight positive charge. I hope this point is clear to everyone. Next point is that depending upon electron donating and electron withdrawing capability, electron donating and electron withdrawing capability, different atoms or groups, can polarize a covalent bond to different extents. What does that mean? Have a look. If I talk about CF, if I talk about CCl, if I talk about CBr, if I talk about Ci, now tell me, is there displacement of electron? Is this sigma orbital symmetrically distributed, or this will be a distortion over here, distortion over here, distortion over here, distortion over here? Everywhere it will be a distorted sigma orbital, but as we know, fluorine is more electronegative. It will attract electron towards itself and will acquire more negative charge as compared to chlorine, as compared to bromine, as compared to iodine. So the magnitude of negative charge over fluorine will be greater as compared to chlorine, as compared to bromine, as compared to iodine. Similarly, magnitude of positive charge on this carbon will be greater as compared to magnitude of this carbon, as compared to magnitude of charge on this carbon, or as compared to magnitude of positive charge on that carbon. Now the question is, polarization occurs in all these bonds, but this polarization will be more. It depends on electron withdrawing capability. Similarly, it can also depend on electron donating capability as well. So I hope this is clear to everyone. Now, after that, point number 9 is like inductive effect is an additive effect. Say, if this carbon is having chlorine attached to it, only one chlorine. So I will say chlorine will attract electron towards itself and it will acquire a partial negative and this will acquire a partial positive charge. But if this is attached to two chlorine, now I will say this is having partial negative, this will attract electron towards itself, So magnitude of positive charge will be more over here as compared to this. Why? Because this carbon is, surrounded by two electron withdrawing groups. So this inductive effect, due to this inductive effect, electrons will be attracted towards chlorine over here. That means electrons will be also attracted towards chlorine here. That means here are two groups which can show inductive effect. Hence, here will be more inductive effect observed by this carbon as compared to this carbon. So here, two groups have more inductive effect. That's why as two groups are present, inductive effect is more. Only one group is present, inductive effect is less. So we add up here inductive effect of this as well as this. So we can simply say inductive effect is an additive effect. After that, next point, that is inductive effect is a relative phenomenon. It is a relative effect. And whenever term relative is used, there must be some standard reference. So inductive effect is a relative effect, and the standard reference taken for inductive effect is either you will say hydrogen or CH bond. And remember, inductive effect for hydrogen or CH bond is assumed to be 0, is assumed to be 0. Is assumed to be 0. That means hydrogen will neither donate sigma electrons nor will attract sigma electrons. I hope this is clear to everyone. Now, after that, we will discuss its types, and these are the types of inductive effect according to Ingold conventions. According to Ingold convention. Remember, according to Ingold convention, inductive effect is of two types. Number one is electron withdrawing inductive effect, means minus I effect. What is minus I effect? Remember, it is that inductive effect due to which any atom or any group withdraws, that means attracts, withdraws, or we can simply say attracts sigma electrons towards itself more strongly than hydrogen, more strongly than hydrogen. So here hydrogen is the standard reference. So we compare electron withdrawing capability of any atom or any group with hydrogen. If any atom or any group withdraws sigma electrons more strongly than hydrogen, we simply say those species will possess minus I effect. I hope this is clear to everyone. But after that, you must know minus I series, that which type of species having the, say, inductive effect highest. Here are a few species which you have to remember. First, NF3 positive, NR3 positive, SR2 positive, NH3 positive, NO2, SO2R, CN, SO2AR. After that, it is COH, FCl, BR, then O5 or OPH or O-phenyl, because phenyl means C6H5. So this is C6H5. Sometimes it's written as O like this, O, and after that phi. Phi is also phenyl. Sometimes it is written OPH. PH is also phenyl. OC6H5, that's also O-phenyl. Then it's ester, that means COR. Then it is OR. Then COR. Then SH, SR, OH, C triple bond CR. Then NH2. Then phenyl. Then CH double bond CR2. Now, you have to remember these. You can remember this with the help of this trick or mnemonics. You can write down this as well, like NF3. For that, no Ferrari, no Rolls-Royce, NR3 positive, so rich, SR2 positive, and after that, no home, that means NH3 positive. So first of all, we have written over here only cations. So minus I effect, first of all, it will be cations whose minus I effect will be very strong. After that, these species, these are partial positively charged species. Have a look. These are partial positively charged species. If I write NO2 like this, N double bond O and then a coordinate bond, can I say this is partial positive, partial negative? Similarly, it is S double bond O and R. What is this? Partial positive and partial negative. That means these atoms are having partial positive charge. These are having complete positive charge. These are partial positive charge. C triple bond N. C having partial positive, N having partial negative. Similarly, these are partial positive charged species. After that, these partial positive charge, these are complete positive charge, then partial positive, then halogens, and then neutral species. So you can remember no Ferrari, no Rolls-Royce, so rich, no home for these cations. And for partial positive charged species, you can have no soap can stop carbon. And after that, for what we call these neutral species and including these, say halogens, Father Karl Braun in office collecting orders. Then after that, chop sushi, sir. Then chop sushi, sir. After that, O, as this is having triple bond, so O triple. This is N, so new phenyl double. I hope you will remember this order easily. Now after that, you have to compare minus I power. Now have a look. you have to look towards this element which is attached to a carbon chain. That means this element, I can call this atom as key atom. So what is key atom over here? Here, key atom means that atom which is directly attached to a carbon chain. Now have a look. This is F, this is O, and this is N. F, O, and N. Which is more electronegative? It's F. After that, it's O. After that, it's N. From carbon chain, which will attract sigma electrons more strongly? It will be F, then O, then N. So the answer is 1, 2, and 3. Now, have a look. Here, key atom is having positive charge. Here, key atom is having partial positive charge. And here, key atom is neutral. Now tell me. One is complete positive charge, another is partial positive charge, another is neutral. Which will attract sigma electron towards itself? It will be obviously complete positive charge first, then partial positive charge, and then neutral species. Now, have a look. This key atom is sp hybridized. This key atom is sp2 hybridized. This key atom is sp3 hybridized. Which one among sp, sp2 and sp3 carbon is more electronegative, or which can attract sigma electron towards itself more easily? It's sp, then sp2, then sp3. So the answer is 1, 2, and 3. Here, carbon is bonded with oxygen. So here carbon is bonded with nitrogen. Here carbon is bonded with carbon. So this bond, carbon-carbon double bond, will be a non-polar bond, non-polar pi bond. But this will be a polar pi bond. It will be having a positive charge and nitrogen negative, because nitrogen is more electronegative. It will attract its sigma electrons towards itself. So carbon will be having positive and nitrogen negative. But can you say oxygen is more electronegative than nitrogen? So oxygen will acquire more negative charge and carbon will acquire more positive charge. Can I say this is more polar? More polar. This is less polar. And this is non-polar. Now tell me. If this carbon is having more positive charge as compared to this carbon, and this carbon is neutral, which will attract its, say sigma electrons from carbon chain towards itself. So the answer is 1, after that it is 2, after that it is 3. Now have a look. Nitrogen having positive charge, phosphorus having positive charge, arsenic and antimony having positive charge. N, P, As and Sb, they belong to the same group, and in same group we know on moving from top to bottom, size increases. If size increases, now tell me volume charge density, because magnitude of charge is same, we know positive volume charge density is inversely proportional to size. So nitrogen is having lesser size, so its volume charge density, positive volume charge density is more. Whose positive volume charge density is more electronegative. Hence, this is more electronegative. It will attract electrons more towards itself. So the answer will be 1, 2, 3, and 4. Here, have a look. Now, here it's NH3. This is, have a look, NH3 with a positive charge. Then it is NH2. And this is alkyl group attached to N. Here it is NH, and then 2 alkyl groups are attached to nitrogen. Now have a look. This is alkyl, and among alkyl group it is carbon which is attached to nitrogen. Now tell me, among nitrogen and carbon, which is more electronegative? Positively charged nitrogen, and this is neutral species, it will attract electron towards itself. Also it will attract electron towards itself here and here. Now have a look. Here are 2 alkyl groups which are donating electrons, or here are 2 alkyl groups from which nitrogen attracts electron towards itself. Its positive charge will decrease. Its magnitude of positive charge will decrease. Here magnitude of positive charge will decrease, but due to only 1 R. Here positive charge will remain same, because H neither donates electron nor withdraws electron. So can I say positive charge here is more than here, than here? Why positive charge is more over here? Because no element decreases its positive charge, but here R, by donating electrons, decreases positive charge. Here 2R donates electron and its positive charge is still more decreased. So tell me, among these 3 nitrogens, which nitrogen is having more positive charge? It is this one, then this, then this. So the answer will become 2 greater than, so this is, sorry, 3 and this is 4. So 2 greater than 3 greater than 4. 2 greater than 3 greater than 4. Now the question is, what about these two? What about these two? Remember, here nitrogen is attached to 3 alkyl groups, but alkyl groups are considered bulky groups. That means these bulky groups are closer to each other. So electron cloud of this bulky group will repel electron cloud of this bulky group. That means there will be steric repulsion. Yani repulsion between two bulky groups, repulsion between electron clouds of two bulky groups in three-dimensional space is known as steric repulsion. Here it is steric repulsion. What will happen? When steric repulsion takes place, R and R move away from each other. That means due to this steric repulsion, bond angle increases. Here bond angle increases. Now tell me, if bond angle increases, can I say as bond angle increases, therefore percentage of S will increase, or electronegativity of nitrogen will increase. As electronegativity of nitrogen will increase, hence this nitrogen will attract electrons towards itself more than these nitrogens, because there will be no steric repulsion. So whenever steric repulsion concept is taken, so bond angle increases and percentage of S or electronegativity of that central atom increases. Now the question is, at what time we will take this, I mean say steric repulsion? If this element is second period, if this element belongs to second period, of this element is a second period element and is sp3 hybridized, whenever this is second period element and is sp3 hybridized, and that too if it is nitrogen and is attached to three bulky groups, at that time you can take steric repulsion. I hope this is clear to everyone till now. After that, we are having another electron donating inductive effect, another effect that is known as plus I effect. And remember, it is that inductive effect due to which sigma electrons are donated more strongly than hydrogen. So whenever any species donates sigma electrons more strongly than hydrogen, such species will possess plus I effect. Okay, now you have to remember plus I series. For that you have, say trick written over here. It's CH2 minus NH minus O minus CO minus. First of all anions, then tertiary alkyl group, secondary alkyl group, then ethyl, then methyl, then isotopes of hydrogen like tritium, and deuterium. For that you have to write like this: can no one cook, can no one cook. After that it's tertiary. For tertiary, tri. This is secondary, for secondary, some. And this is ethyl, for ethyl, extra. And this is methyl, for that it's meals. Then tritium, that means tasty. And then say deuterium, that means dinner. So the trick is like this: can no one cook, try some extra meals, and after that it's a tasty dinner. I hope this is clear to everyone. I hope this is clear to everyone. Now let me know in the chat box, is this clear till now? Is this clear till now? Let me know in the chat box. Let me know in the chat box. Come on, I will be waiting. Let me know in the chat box. Is this clear to everyone? Okay, clear. Now, applications of inductive effect. First application is stability of a positively charged species. For that, you have to remember that it is directly proportional to plus I or electron donating group attached to that positively charged species, and it is inversely proportional to minus I and electron withdrawing group. You have to remember this formula. You have to remember this formula, formula number 1. Another is you have to first write down minus plus I. After that, you have to write down those species which do not show either plus I or minus I, that means neutral species, and after that you have to show minus I. If in a question there are more than one plus I, then you have to write down first strong and then you have to move towards weak. So strong to weak. Here weak to strong. What is meant by this? Now have a look. We will use these formulas in, say these types of questions. We can use, say this trick in, say for example, question like this. Say for example, you have to compare stability. Suppose you are having question like this: CH3 with a positive charge. Number second, it is CH3 CH2 with a positive charge. Now after that you are having like this: CH3 CH3 CH2 with a positive charge. Now after that you are having like this: CH3 Cl CH2 with a positive charge, and lastly you are given like this: FCH2 with a positive charge. Now have a look. First of all, positive charge is everywhere, but this positive charge is attached to hydrogen. What is hydrogen? It neither shows plus I nor shows minus I. That means neither it donates sigma electron nor it withdraws sigma electron. That means this is a neutral species. That means it is a neutral species. That means it's a neutral species. What about this? CH2 positive is attached to this. This is alkyl group, and alkyl group shows plus I effect. What about this? It's also an alkyl group. Alkyl group shows plus I effect. What about this? As this chlorine is minus I, hence I can say this whole group shows minus I effect. So this is plus I, this is plus I, this is minus I, and because of this F, this is also minus I. Now, what is the formula over here? First of all, you have to write down plus I. Now, which one is plus I? Now tell me. This is plus I and this is plus I. But among these plus I, which type of plus I have to write down first? It's strong one, and after that weak one. Remember, if you are having alkyl groups show generally plus I. But if alkyl groups are such that one is having more branches, another is having lesser branch, the alkyl group with more branches is more powerful plus I group, is more powerful plus I group. If branches are same, then the alkyl group with more number of carbon atoms is more powerful plus I group. Now here it's having a branch, but this is without branch, so this is stronger plus I as compared to this. So I have to write down stronger first, so I will write down 3, after that 2. So first you have to write down plus I. After that I have to write down neutral. Now have a look. First plus I, then neutral. So neutral is this one, so it's first one. After that I have to write down minus I, but minus I weak first and after that strong. Now tell me, this is Cl minus I, this is F minus I. Whose power is more? F is stronger and as compared to Cl. So I have to write down weak one. Which one is weak? Weak is 4. After that I will write down 5. So this is the answer of this question, stability order. I hope this is clear till now. Let me know in the chat box, is this clear till now? Let me know in the chat box, is this clear till now? Quick. Let me know in the chat box, is this clear till now? Okay, for negatively charged species, you have to write down like this. That means it's directly proportional to minus I, or electron withdrawing group attached to it, or it is inversely proportional to plus I, or electron donating group. Or you can simply remember this formula: first minus I, then neutral species, then plus I. But for this one, you have to write down strong first, after that weak. Similarly here, first weak, then strong. You can write down this formula as well. Say for example, we are having a question like this: compare stability. Say for example, we are having CH3 having a negative charge. Number second, CH3, CH2 having a negative charge. After that, we are having CH3, CH2, CH2 having negative charge. And then we are having FCH2, CH2 having negative charge. And lastly, we are having Cl, CH2, CH2 having negative charge. Now have a look, have a look, have a look. This is neutral. Why neutral? Because this negative charge is attached to hydrogen, and hydrogen shows neither plus I nor minus I. But this negative charge is attached to plus I. This negative charge is attached to plus I. This negative charge is attached to minus I because of fluorine, and this is minus I because of chlorine. Now, what we have to write down first? What we have to write down first? Minus I. So, which one is minus I? 4 and 5 are minus I. But which minus I? Strong first, then weak. So, can I write 4 first and then 5? First 4, after that I will write down 5. Because first strong, then weak. After that, I have to write down neutral. Neutral is first. After that, I have to write down plus I, but weaker one, and then stronger. Now, once again, this is alkyl, this is alkyl. But both these alkyl does not have any branch. If alkyl groups does not have any branch, at that time, we will simply choose that alkyl group whose number of carbons are more. We will simply say that shows stronger plus I. So this shows stronger plus I because more number of carbons are here. This shows weaker plus I because lesser number of carbons are here. So which one I have to write down? I have to write down weaker one first. So weaker is 2. So I will write down 2 first. And after that, I will write down 3. Now, is this clear to everyone? Tell me quickly, write down in the chat box quickly. Is this clear to everyone? Is this clear to everyone? 4, 5, 1, 2, 3. Great, great. What's your name? Roshni. Great, great beta, great, great. Okay. What about others? What about others? Come on, quickly, write down, write down. What about others? Is this clear to everyone? Now, our next topic is acidic strength, but before doing acidic strength, we will have a break, and let me tell you, we will be back. So it's a break time, and break is till 1:45 p.m. So break is till 1:45 p.m. and I will be waiting exactly at 1:45 p.m. and I hope you all will be back at 1:45 p.m. Till then, take care. Goodbye.
Hello everyone, welcome back. Please let me know in the chat box if I am clear to everyone and if everyone is audible. If I am audible to everyone and if I am visible to everyone, please let me know in the chat box. Please let me know. Please let me know in the chat box if I am clear to everyone, if I am visible to everyone and audible to everyone. Let me know in the chat box, guys. Am I audible and visible? Am I audible and visible? Please let me know in the chat box if I am audible and visible to everyone. Okay. Okay. Now, here another thing is acidic strength. You know that if we are having any acid, a protonic acid, which upon treatment with water, it will always lose its proton and results in the formation of a conjugate base. So any acid, whenever loses its proton, it forms its conjugate base. And water will accept that electron and it will result in the formation of hydronium ion. Now, remember, strength of acid is directly proportional to tendency of an acid to lose H positive, that means to lose its proton. So if this is having tendency to lose proton, so it becomes a stronger acid. More it is having tendency to lose proton, more the tendency to lose proton, more will be the strength of the acid. But when it loses proton, it results in the formation of conjugate base. That means if conjugate base is more stable, then it will lose its proton more easily, more readily, so as to form a conjugate base. That means it is directly proportional to stability of its conjugate base. Which clearly means that first formula which you have to remember is strength of any acid is directly proportional to stability of its conjugate base. This is the first formula which you have to remember. Formula number next which you have to remember is that whenever we have to arrange different acids in their acidic strength order, first of all, we will write minus I, then neutral, then plus I. But if we are having more than one minus I groups, then you have to write down strong first and then weak. Similarly, you have to write weak plus I first and after that strong plus I. This is another formula. Another formula is that strength of acid is directly proportional to minus I group or electron withdrawing group. And another formula is strength of acid is directly proportional to plus I group or electron withdrawing group. What is meant by this formula? That means whenever an acid is attached to electron withdrawing group or minus I group or electron withdrawing groups make that acid more stronger acid. Similarly, if plus I group or donating group, not withdrawing, electron donating group is attached to an acid, it makes acid more, is inversely proportional. It makes acid weaker acid. So it is directly proportional to minus I and inversely proportional to plus I or electron donating group. So whenever electron donating group or plus I group is attached to an acid, it makes acid a weaker acid. Now, these are the four formulas. After that, you have to remember formula number 5, that is strength of acid is directly proportional to dissociation constant of acid. Okay, now sixth formula, this is already, you have learned this already in equilibrium. I hope you have done it. Now, after that, strength of acid is inversely proportional to pKa. This is another formula which you have to remember. After that, you have to remember that strength of acid is inversely proportional to dissociation constant of base. After that, you have to remember this another formula, that strength of acid is directly proportional to pKb. These are the, say Ka, Kb, pK, pKb, these are the terms which you have done in equilibrium. After that, you have to remember that strength of acid is directly proportional to concentration of H positive ion. More the concentration of H positive ion, more will be the strength of acid, which means formula number 10 will become like this. Strength of acid is inversely proportional to pH. After that, you have to remember this formula, that strength of acid is inversely proportional to molar concentration of OH minus ion. And lastly, you have to remember strength of acid is what we call directly proportional to pOH. Okay. These all terms are in equilibrium. What is pH? What is pOH? Everything is there in equilibrium. So there are a few formulas which you have to remember. So first of all, you have to remember these four, and then you have to remember these formulas. Say for example, let us understand these formulas. Let's understand these formulas. Suppose you are having a question like this. Say for example, you are having question like this. Just a moment, give me 1 second. Now, suppose you have to compare acidic strength. You have to compare acidic strength. And for example, that acid which is given over here is a carboxylic acid. Say it's like this, HCOOH. Number second, it is CH3COOH. Number third, it's like this, CH2CH2COOH. Number fourth acid is ClCH2COOH. And number 5 is FCH2COOH. Now, listen carefully. Please try to understand. Now, to this acid, to this COH, what is attached? Hydrogen is attached. But hydrogen neither shows plus I nor shows minus I. Neither it donates sigma electron nor it withdraws sigma electron. Hence, for us, it will be a neutral species. Now, what about CH3? What about this CH3? CH3 is a plus I group. What about this ethyl? Ethyl is also a plus I group. What about this Cl? Cl is minus I group. And what about this F? F is also minus I group. Now, listen carefully, and you have to remember this formula always. You have to always remember this formula. Whenever you want to write down the acidic strength order, first of all, you have to write down minus I, and that too strong. Now, have a look. We have to write down minus I, but minus I is this, minus I is this. But among these two, we have to write down the stronger one. F is stronger as compared to Cl as per minus I is concerned. So I will write down 5. After that, I will write down 4. After minus I have to write down N. That means I will write down first option. After that, I have to write down plus I. But plus I here is of methyl and plus I here is of ethyl. Methyl and ethyl are alkyl groups. Whenever alkyl groups are given, plus I order is directly proportional to branching. But if neither of the alkyl groups have branches or both the alkyl groups have same branches, at that time plus I is directly proportional to number of carbon atoms. So this is having stronger plus I and this is having weaker plus I. We have to write down weaker first and then stronger first. So I will write down 2 and after that I will write down 3. So this is the answer of this as per acids are concerned. So here our HA acid was RCOOH. So this is our acid, carboxylic acid, and when it's treated with water, what will happen? It will result in the formation of, it will lose H positive and result in the formation of RCOO negative on a conjugate base. plus hydronium ion. Now, this is our acid and this is conjugate base. So, either you have to answer the question with the help of conjugate base, or directly you can write down that formula minus I, then neutral, then plus I, but among minus I, stronger one, and among plus I, weaker first, and after that, stronger. Now, if this same question is asked like, but in a different manner, say for example, you have to write down the stability of their conjugate bases, order of stability of their conjugate bases. We know strength of acid is directly proportional to stability of conjugate base. So order will become once again 5, 4, 1, 2, 3. That means its conjugate base is more stable than the conjugate base of 4. If this is more stable, its conjugate base is more stable than the conjugate base of 1. Conjugate base of 1 is more stable than conjugate base of 2, which in turn is more stable than the conjugate base of 3. Similarly, if you are having question like this, what will be the Ka order? And we know strength of acid is directly proportional to Ka. First, we will write down the strength of acid order. After that, therefore, we will write down Ka is also 5, 4, 1, 2, 3. But if you were asked, write down pKa value, and we know strength of acid is inversely proportional to pKa. At that time, you have to reverse the order. I hope this is clear to everyone. This is carboxylic acid. Sometimes acid may be like this. Sometimes acid may be like this. Acid may be like alcohol. And whenever this is treated with water, what will happen? It will lose its H positive and it will result in the formation of RO minus. So here, this is the conjugate base. Alkoxide ion. This is carboxylate ion. So this is carboxylate ion, conjugate base of carboxylic acid. This is carboxylate, this is alkoxide ion, conjugate base of alcohol, and this will be the hydronium ion. But any acid, any protonic acid, whether it is alcohol, whether it is, carboxylic acid, or any other acid which can donate H positive like this, results in the formation of a conjugate base, and conjugate base of acid is having a negative charge. That means negatively charged species will be formed, and for that we know strength of acid is directly proportional to this, inversely proportional to this. So we directly use this formula, or we will use this formula. Now, next is basic strength of amines. Remember, this is solvent dependent. What does that mean? That means if we change solvent, basic character of amines will be changed. For example, number 1, we will see basic strength of amines but in non-aqueous media. In non-aqueous media or aprotic solvent. What is meant by aprotic solvent? That solvent which does not release, which does not donate H positive is known as aprotic solvent, or a gaseous phase. Gaseous phase means if solvent is absent. If solvent is absent, we can use this one. If solvent is given but that is non-aqueous or that is aprotic solvent, then we can use this. Remember here, basicity. Basicity means strength of base. Basicity is directly proportional to plus I or electron donating group attached to the base, and it is inversely proportional to minus I group or electron withdrawing group attached to the base. So directly related to plus I and inversely related to minus I. First formula is this, and another formula you have to write down is that you have to write down first plus I, then neutral, then minus I. But here you have to write down strong to weak, and here you have to write down weak to strong. Now what is meant by this? Let's understand this with the help of an example. Say for example, you are having an amine like this, RNH2. This is known as a primary amine. This is a primary amine. After that, I will write down this NHR. This is a secondary amine. You know, amine having NH functional group is secondary and NH2 is primary. After that, having N functional group is a tertiary one or 3-degree amine. So let's look towards these. These are the amines, primary amine, secondary amine and tertiary amine. We have to compare their basic order. Now the question is, what is meant by base as per organic chemistry is concerned? Let me write down that over here. Base according to organic chemistry is simply, remember forever, H positive acceptor. According to organic chemistry, either H positive acceptor or lone pair, electron pair donor. We will write down over here electron pair, not lone pair. We will write down over here electron pair donor. Any species which donates electron pair is a base, or which accepts H positive is a base, either H positive acceptor or electron pair donor. But in this medium, as there is no H positive present in a solvent, because solvent is a protic solvent which cannot donate H positive. So here we will look definition of base. We will look towards this electron pair donor, which means here nitrogen is having a lone pair of electron, nitrogen is having a lone pair of electron, nitrogen is having a lone pair of electron, which will donate lone pair of electron easily. Lone pair of electron will be donated by that nitrogen easily whose electron density is more. And which nitrogen is having more electron density? You can see this R shows plus I, it will donate electron towards nitrogen. This R shows plus I, it donates electron towards nitrogen. This shows plus R and donates electron, plus I and donates electron towards nitrogen. That means electron density of nitrogen has been increased due to 3 alkyl groups or due to 3 plus I groups. Here, electron density of nitrogen is increased due to 2 alkyl groups or due to 2 plus I groups. Here nitrogen electron density is increased due to only 1 plus I group. Now tell me, in case of primary amine, in case of secondary amine, and in case of tertiary amine, which nitrogen is electron rich? That's this one. So this can donate electron easily. That's why simply what you have to observe here, this nitrogen is attached to only 1 plus I. This is attached to 2 plus I. This is attached to 3 plus I. That means where is plus I more, which are attached to nitrogen here? So more stronger plus I. That means you have to write down that. After that weaker one. After that weaker one. So if I write down the basicity order among nitrogens in this medium, it will be simply, basicity order will be simply 3 degree, 2 degree and 1 degree amines. So remember, whenever question is like this, what will be the basicity order among amines? First of all, you have to check what is the solvent, in which medium this question is asked. If the question is asked, what is the basicity order among amines in non-aqueous medium or aprotic solvent or gaseous phase, you have to remember it's 3 degree, then 2 degree, then 1 degree. In nutshell, you have to write down this formula or this formula so that you can answer the question. As here, more plus I groups are there, so more stronger plus I are attached to nitrogen. Here, lesser, weaker as compared to this, as only 2 plus I groups are there. Here, only 1 plus I group is attached to nitrogen. So here only 1, here 2 plus I, here 3 plus I. You have to write down stronger plus I. That means this one, then this one, then this one, stronger to weak. You have to write down stronger towards weak. Next, if question is like this, please try to understand. You are having 1 degree amine, NH2, and after that CH3 is attached, and then CH3, CH2, NH2. This is also a 1 degree amine. And then this is like this, Cl, CH2, CH2, NH2. Once again a 1 degree amine. And then it's like this, F, CH2, CH2, NH2. We have to compare basic character or basicity order we have to compare basicity, but in non-aqueous medium, aprotic solvent or gaseous phase. At that time, you have to look towards this. The group attached to N is, I mean to say this amine is plus I group. Here, this group is also plus I. What about this Cl? This is minus I. What about this F? This is minus I. Now, have a look, have a look. We have to write down first plus I, then neutral, then minus I. But neutral is not present over here, so we will write plus I first. But which plus I will write first? Stronger one and then weaker one. Now, which among these two is a stronger? It's this one, so I will write down 2 after that 1. So first stronger plus I, then weaker plus I. After that, we have to write minus I. But among minus I, which minus I? A weaker one first and then stronger one. Now tell me, among F and Cl, which one is weaker? Cl is weaker, so I will write Cl first. That means option number 3 first, and after that, I will write down option number 4. So this will become simply the basicity order for this question. Now, is this clear to everyone? Please let me know in the chats quickly that is this clear to everyone or not. Is this clear to everyone? Let me know in the chats. Let me know in the chats. Is this clear? Is this clear? Guys, is this clear? 2, 1, 3, 4, 2, 1, 3, 4. Yes, it's clear. I hope it's clear. Okay. Now, after that, we will write if medium is changed in aqueous medium or protic solvent, what will happen to basic character? Now listen carefully, listen carefully. What will happen here? Now have a look. When we talk about aqueous medium or a protic solvent, what is meant by a protic solvent? Which can donate proton, and which solvents easily, which species can easily donate proton? When hydrogen is attached to electronegative elements like fluorine, chlorine, bromine, iodine, oxygen, nitrogen, carbon, sp, etc., so on and so forth. When these elements are attached to hydrogen, hydrogen is attached to these elements, hydrogen will be easily, say, donated as H positive, or these species can donate H positive easily at that time. Now, have a look. If I am having primary amine, RNH2, and let us suppose protic solvent is water, that means in medium water, what will happen? Now have a look. This lone pair will accept H positive. It will accept H positive from water and results in the formation of RNH3 with a positive charge. And this water, as it loses H positive, it will result in the formation of OH minus. Now tell me, as our solvent can donate proton, that means this lone pair can accept proton, and hence it becomes base as it accepts a proton. So this is a base. Whenever base accepts proton, the species which is formed is known as conjugate acid. Now after that, if I am having a secondary amine in water can also act as a base, and it can accept proton from water and results in the formation of RNH2R with a positive charge. So this is a conjugate acid of secondary amine. Similarly, if I am having tertiary amine, RNRR, if I am having tertiary amine, it can also act as a base by accepting proton from water, and it will result in the formation of a conjugate acid like this, RNRR, and this N will be having a positive charge. So this is the conjugate acid of tertiary amine. Now, tell me, before this medium, when medium was non-aqueous or aprotic or gaseous phase, there was no proton. Hence, amine remain as such. But in this medium, amines are converted into their conjugate acids. So remember, for this, say medium stability, or simply we can say basicity. Basicity of amines in this medium is directly proportional to stability of conjugate acid or stability of its conjugate acid. But this stability of conjugate acid depends upon two factors, plus I of R, that means plus I of alkyl group, or we can simply say extent of hydrogen bonding, extent of H bonding. Now have a look. Now if you have to find out which base is stronger base, you have to find out which conjugate acid is more stable conjugate acid. But stability of conjugate acid depends upon two factors. Now, so if I write like this, on the basis of factor number 1, please have a look. On the basis of plus I of R, on the basis of plus I of R, say for example this is factor number 1, we have to find out which conjugate acid is more stable. Once we know the stability order of conjugate acids, we can simply say which base is stronger base, because conjugate acid stability is directly proportional to basicity. This is conjugate acid of primary amine, this is conjugate acid of secondary amine, and this is conjugate acid of tertiary amine. Have a look, have a look. Now, tell me, this nitrogen is having positive charge, this is positive charge, this is positive charge. That means positive charge species are there. So, we know stability of positive charge is directly proportional to plus I groups. Positive charge stability is directly proportional to plus I groups, or we can simply say, more the plus I groups attached to positively charged species, that species becomes more stable. Now tell me, this R will donate electron and it will decrease its positive charge, but here positive charge is more decreased due to 2 plus I groups, and here positive charge will be most decreased due to plus I of what we call alkyl groups. So can I say here positive charge is less as compared to this, here positive charge is less as compared to this. So lesser the positive charge, more will be the stability. That's why we have written that stability of any positive charge is directly proportional to plus I. So more the plus I, more will be the stability of positive charge. More the plus I groups attached to, positive charge species, more will be the stability of that positive species, and lesser the plus I groups attached to positive charge, lesser will be the stability of that positive charge species. So can I say stability of conjugate acids will be simply, it's 3 degree conjugate acid of 3 degree amine, which is more stable than conjugate acid of 2 degree amine, in turn is more stable than conjugate acid of 1 degree amine. Therefore, can I say basicity order will be 3 degree amine greater than 2 degree amine greater than 1 degree amine. But this basicity order will be on the basis of, this order will be on the basis of plus I of R. I hope this is clear to everyone till now. Next factor is extent of hydrogen bonding, extent of H bonding. Now have a look. If I write conjugate acid of primary amine, first we have to compare the conjugate stability of this with conjugate acid of secondary amine. After that, we have to compare stability of conjugate acid of tertiary amine. Now, tell me, at this point of time, we have to see hydrogen bonding. Now, tell me, in case if solvent is water, this can form hydrogen bond with oxygen of water. This can form hydrogen bond with oxygen of water. this can form hydrogen bond with oxygen of water. Similarly, this can form hydrogen bond with oxygen of water, and this can form hydrogen bond with oxygen of water. Here, this can form hydrogen bond with oxygen of water. Here, hydrogen bond, only one hydrogen bond is formed. Here, 2 hydrogen bonds are formed. Here, 3 hydrogen bonds are formed. Now, tell me, which conjugate acid shows more hydrogen bonding? It's primary conjugate acid as compared to conjugate acid of secondary amine, as compared to conjugate acid of tertiary amine. So remember, what is hydrogen bonding actually? Hydrogen bonding is nothing but it is force of attraction between hydrogen and electronegative elements like fluorine, oxygen, and nitrogen. So it's electrostatic force of attraction. So can I say more hydrogen bonding means more electrostatic force of attraction? More electrostatic force of attraction means more stability. So can I say this is more stable than this, than this? So stability of conjugate acids on the basis of extent of hydrogen bonding, can I say it is conjugate acid of 1 degree amine, which is more stable, then it's conjugate acid of secondary amine, then it's conjugate acid of tertiary amine. Therefore, basicity order will be, I hope you are getting me. Now, basicity order will be 1 degree, 2 degree, and 3 degree. But this order is on the basis of extent of hydrogen bonding, and this order is based on what we call plus I of alkyl group. Now, if you look towards these orders, this is 3, 2, 1. But here, order is 1, 2, 3. So, where is the doubt? Where is the doubt? Doubt is between 3 and 1, because according to this order, 1 comes at first position, and according to this order, 3 degree comes at first position. That means there is no doubt between 2 degree, because 2 degree is here at second position, 2 degree here at second position. That means there is doubt between 1 degree and 3 degree. As there is no doubt between 2 degree amines, so we can simply say both the above factors, I mean say plus I of alkyl group and extent of hydrogen bonding, both the above factors favor 2 degree amines, favor 2 degree amines. Hence, 2 degree amines are considered strongest base among amines. Strongest base among amines. So remember, among 1 degree, 2 degree and 3 degree amines, if solvent is non-aqueous or aprotic or gaseous phase, at that time 3 degree amine is the strongest base. But if solvent is protic solvent or aqueous medium is there, then at that time secondary amine is the strongest base. Remember, if solvent is not given, one is if solvent is absent, then it is gaseous phase. But if solvent is not given, solvent is present, but it is not given. Say for example, you have to write down which one of the following is the strongest base. That's it. Question is like this: which one of the following is the strongest base? And options are 1 degree amine, 2 degree amine, and 3 degree amine. As solvent is not given, take water as solvent. And if water is solvent, that means solvent is protic, hence secondary amine is considered as the strongest base. Now, as we have doubt between 1 degree amine and 3 degree amine, we will once again compare stability of 1 degree amine conjugate acid or conjugate acid of 1 degree amine and conjugate acid of 3 degree amine. We will not now consider conjugate acid of secondary amine because there is no doubt in that. So doubt is between 1 degree and 3 degree. So we will once again compare stability of conjugate acid of 1 degree amine and stability of conjugate acid of 3 degree amine. Here we have two cases over here. We have two cases over here. Case number one. Case one is if R is small, if R is small, if alkyl group is small, and you know that is at that time alkyl group is CH3. Now, We have two factors, plus I and hydrogen bonding. As per plus I is concerned, among alkyl groups, plus I order, already I have written that 3 degree alkyl, after that 2 degree alkyl, after that it is ethyl, after that it is methyl. That means among alkyls, this methyl is having least, lowest, weakest plus I power. So its plus I can be neglected. So if R is small, then its plus I can be neglected. So you can neglect plus I because it is very low as compared to other alkyl groups. So plus I can be neglected. So if plus I is neglected, there will be only one factor, and that is hydrogen bonding. Hence, stability will be explained. Hence, stability of conjugate acid will be explained only by H bonding. Now tell me guys, here hydrogen bonding is more because here 3 hydrogen bonds will be formed, here hydrogen bonding is less. Now tell me stability order. What will be the stability order as per hydrogen bonding is concerned? So stability order of conjugate acids, but which conjugate acid? Only conjugate acid of 1 degree and 3 degree. Can I say it's 1 degree greater than 3 degree? So basicity order will be among these two. It's 1 degree amine, then 3 degree amine. But let me tell you, overall basicity order will be 2, because 2 degree was the strongest base. After that it's 1 degree, and after that it is 3 degree. In nutshell, if you have to write down the basicity order, if the value of R is CH3, it is 2 degree, 1 degree and 3 degree, because this order is explained only on the basis of hydrogen bonding. 1 is greater than 3. This order is based only on hydrogen bonding, as we have neglected plus I power, as that plus I power was very small. Now, case second is if R is large. Now tell me, large means alkyl have many values, but you have to remember only one. That means if that is CH2CH3, if that is ethyl. Now listen carefully. Now it's ethyl. That means it is larger than methyl. That means we can consider this as a bulky group. Now tell me, if we talk about plus I of ethyl is not the lowest among alkyl groups. Hence, we cannot neglect plus I. But what about hydrogen bonding? Listen, when water approaches towards hydrogen for hydrogen bonding, electron cloud of water will be repelled by the electron cloud of alkyl group, because now alkyl group is larger. If there is a repulsion to the electron cloud of water due to electron cloud of, alkyl group, can I say hydrogen bonding, extent of hydrogen bonding, it will be decreased. That means hydrogen bonding will not be efficient. Hence, we can, so at that time, if this is, R is large, then H bonding can be neglected. Now, why H bonding can be neglected over here? Because it's very poor, it's not that efficient hydrogen bonding, because whenever electron cloud of water, when water approaches towards hydrogen for hydrogen bonding, that means electron cloud of water will be repelled by electron cloud of alkyl group, because alkyl group is larger, more bulkier the alkyl group, more will be the repulsion. Hence, we can neglect H bonding. Hence, stability will be explained. Hence, stability of conjugate acid will be explained by plus I of R. Now have a look. Which is having more plus I? This one, so this is more stable as compared to this. So therefore, stability of conjugate acids. Stability of conjugate acid. That order will be simply 3 degree greater than 1 degree. and basicity order will be 3 degree amine greater than 1 degree amine. But overall basicity order will be, what will be that? That will be 2 degree, 3 degree and 1 degree. In nutshell, when R is ethyl, you have to remember that order will be 2, 3, 1. When R is methyl, order is 2, 1, 3. When R is ethyl, order is 2, 3, 1. Let me know in the chat box, is this clear till now? Is this clear till now? Why we neglect plus I over here and why we neglect hydrogen bonding there? I hope this is clear to all. And if plus I is neglected here, stability depends only on hydrogen bonding here. And if hydrogen bonding is neglected there, and their stability at that time will be decided by plus I of alkyl group only. Is this clear to everyone? Please let me know in the chat box. Because this is very, very, very important chapter. And your basics should be very strong. Your concepts should be very strong. For that, you have to tell me honestly, is this clear to you or not? Is this clear? Okay, this is clear. This is clear to everyone. Okay, thank you. Now, there are a few questions. Let's practice them. First of all, these are the positive charged species. These are the positive charged species. You have to write down their stability. For that positive charged species, I have already written that you have to first of all write plus I, then you have to write neutral, then you have to write minus I. Now, if plus I is more than, say 1, then you have to write first strong, then weak. Here you have to write weak first, and after that you have to write down strong. Now, have a look. This positively charged species is attached to fluorine. So this is minus I group. This is also chlorine, minus I, bromine, minus I, and iodine, minus I. That means all groups are minus I groups. First of all, you have to write down the distance because you use DNP rule first. Distance, number and power. So you can have a look and you will see that these fluorine, chlorine, bromine, iodine are at the same distance with respect to the carbocation. That means distance is same. After that, number. Number is also same. After that, it is power. So power of fluorine is more than chlorine. Chlorine's power is more than bromine. Bromine's power is more than iodine. But these are minus I groups. There is no plus I. There is no neutral. These are all minus I. But in case of minus I, we have to write weak minus I first. After that, strong. So what will be the answer? Answer will be 4, 3, 2, 1. I hope this is crystal clear to everyone. And I want all of you to practice these questions and so that you can, be very strong in these concepts, because your concepts should be very, very strong. Now, what about this? This carbocation is attached to alkyl group. Alkyl group shows plus I. This is also alkyl and a branched alkyl. It also shows plus I. This is also alkyl. Only difference is hydrogen has been replaced by deuterium isotope. That means this is also a plus I group. Here also a plus I group. But this is without branch. These are branched. And remember, more the branches in alkyl group, more will be the plus I power. That means these three are stronger plus I groups as compared to this. This is weaker. So all are plus I groups. So we have to write down first plus I, but stronger one. That means either 2, 3 or 4 be the stronger, not 1, because this is not having any branch. But this is H, this is T, this is T. This is H, this is D, and this is T. We know tritium or tritium is having more plus I power than deuterium, and deuterium is having more plus I power than hydrogen. So stronger plus I is in 4, after that it is 3, after that it is 2, after that it is 1. So this will be the answer of this question. And these two will be a home assignment for you or home task for you. I hope you can easily answer these questions as well. Now, other questions here are negatively charged species. And for negatively charged species, we have to write down first minus I, then neutral, and then plus I. For minus I, we have to write strong first, after that weak, and here weak first, and after that strong. Now have a look. Here it's minus I group. This is also, fluorine is also minus I group. Here fluorine is minus I, and here it is alkyl group, which means it's plus I. But here fluorine, and here fluorine are at different distances. You have to write down DNP rule first. Now let me tell you, distance wise, which one is closer? This. More closer is a group, more stronger it will show inductive effect, because inductive effect decreases as distance increases. So here distance is less, so this is stronger minus I. Then this is weaker, this is weakest minus I. We have to write down strongest minus I. Strongest minus I is 1. After that it is 2. After that it is 3. After minus I we have to write down N, but there is no neutral species attached to negatively charged species. After that plus I. So plus I is only 1, so we can write down 1, 2, 3, 4. Okay. Now here negative charge is attached to hydrogen, and hydrogen are neutral species. Negative charge is attached to plus I group. Negative charge is attached to two plus I groups. That means stronger plus I, because inductive effect is additive effect. So here stronger inductive effect. Here as plus I groups are more, hence inductive effect will be stronger. So we have to write down first minus I, but there is no minus I. After that neutral. Neutral is first one. After that plus I, but weaker one. This is strongest. This is stronger. This is weaker. So that means I will write down 2, then 3, then 4. So this is the answer of this question. And similarly, these questions you will answer at home. You will practice them, because these are the easy questions. Now, another is compare acidic strength. You have to compare acidic strength, and for acidic strength, you know, you have to write down minus I first, then neutral, then plus I. For minus I, you have to write down strong first and then weak. Here, weak first and then strong. Now, this HCOH, this is neutral, and this COH is attached to CH3, that means plus I. Here, this is minus I. Here, this is minus I. Now, you have to write down minus I first, but fluorine and chlorine, which one is stronger? Because you have to write down first stronger, then weaker. So I will write fluorine, that means 4. After that, I will write down, sorry, this is 2, this is 3. This must be 3. This is 3, not 2. This is 3. Please write down this is 3. Okay, so 4, then 3, then 2. After that, it should be 2. No, minus I, stronger, weaker. After that, it should be neutral. Neutral means 1. And after that, plus I. Plus I is only 1, and that is 2. So this is the answer. I hope this question can be easily done, and you can easily can answer this question as well. You can easily answer this question as well. Now, question here is, which among these hydrocarbons is acidic? So for that purpose, you have to form its conjugate base. Remove H positive here. Remove H positive here. Both the electrons will be attracted by carbon. Similarly, remove hydrogen here. So its conjugate base will be like this. Here, conjugate base will be like this. Now, this conjugate base is having sp hybridized carbon. This conjugate base is having sp2 hybridized carbon, and this is having sp3 hybridized carbon. So sp is having more s character. More s character, more electronegative, and more electronegative having negative charge is more stable. So this is more stable conjugate base than this. Hence this acid is stronger acid than this. So answer will become, for this question, answer will be simply 1 greater than 2 greater than 3. So this question is based on the stability of conjugate base, and this was on the basis of this. So we know strength of, another formula is strength of acid is directly proportional to stability of its conjugate base. So on the basis of this formula, we have answered this question. Other questions you will try, and you will answer these questions easily. Next, arrange the following species in pK value, Ka value, OH. So whenever question is like this, first of all, you write down their acidic strength value. Do you know this is neutral? Do you know this is plus I, which is attached to acid? This is minus I, which is attached to acid. This is minus I, which is attached to acid. First of all, I will write down this 4. Stronger minus I. After that, weaker minus I. After that, neutral. And after that, plus I. So this is the order, but this order is strength of acid. This order is strength of acid order. Now, we know strength of acid is inversely proportional to pKa. So whatever is the order, reverse over here. This is directly proportional to Ka. So whatever is the order, that order will be followed over here. So anything which is directly related, write down same order, which is inversely related, you simply reverse the order. I hope you can easily answer these questions because already I have given their formulas. What is the relation with pKa? What is the relation with Ka? What is the relation with OH minus? What is the relation with Kb? What is the relation with pH? What is the relation with pOH? What is the relation with pKb? What is the relation with H positive? What is the relation of stability of conjugate base with acid? We already know that. So you can you can easily answer these questions as well. Now after that, compare basic strength. Now let's have a look. Basic strength, you have first of all you have to write down plus I, then you have to write down neutral for such types of questions, and after that you have to write down minus I. But here you have to write down strong to weak first. Here you have to write down weak to strong first. Now have a look. This is nitrogen attached to alkyl group, and alkyl group shows plus I. This is also alkyl, and alkyl group shows plus I. This is also alkyl, and alkyl group shows plus I. This is also alkyl, and alkyl group shows plus I. First of all, more branches in alkyl means more plus I. We have to write down stronger plus I. As branches are more over here, so I will write down 4 first. Both are having same number of branches. That means we have to check where this CH3 is attached. What is the distance? So this is closer, this is far away from NH2. Hence, this plus I will be stronger as compared to this. So I will write down 2, and after that I will write down 3. Finally, I will write down 1. So on the basis of DNP or branching and all that, you can answer this question as well. You can answer question number 2nd. You can answer question number 3rd. Okay, let me help in question number 2nd. Here it is minus I group. 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 All are present at equal distance with respect to nitrogen. Now, first of all, we have to write down plus I, but there is no plus I. After that, neutral. There is no neutral. After that, minus I. So we will write down minus I, but which one? Which is weaker? So which one is weaker? Fluorine, chlorine, nitro, iodine. Iodine is weaker. So we will write down iodine first. After that, it's chlorine which is weaker. After that, it's fluorine which is weaker. After that, stronger is, say 3rd. That's why I will write down that at the last. So weaker to stronger. So this will be the answer. First, it's 4, then it's 2, then it's 1, then it's 3. So this question, we will try this question. And I know that you can easily answer this question. Okay. After that, you can have a look. This nitrogen is attached to carbon. That means it can withdraw its electron towards itself. That means these two groups, these two sides becomes plus I groups attached to nitrogen. So there are 2 plus I groups. What about this? There are 3 plus I groups. And what about this? This is electron withdrawing group. So it will withdraw electron here as well as here. It will withdraw electron. But only 1 electron withdrawing group here. 2 electron withdrawing groups are present. So we have to write first plus I, and that too strong. This is plus I group attached to nitrogen, plus I groups attached to nitrogen, but here plus I is stronger. So I will write down 2. After that, which one is stronger base? 1. After that, neutral, but there is no neutral. These are minus I groups. This is minus I, this is minus I. But here minus I is stronger, this is weaker. We have to write down weaker minus I. That means I will write down 3. After that, I will write down 4. So this is the answer. I hope you can easily answer this question, and I hope this is clear to everyone till now. Now, our next question will be resonance, but before starting resonance, let me know in the chat box, is everything clear till now? Is inductive effect clear to everyone? Is inductive effect clear to everyone? Let me know in the chats. Is inductive effect clear to everyone? Is inductive effect clear to everyone? Let me know in the chats. Let me know in the chats. Is this clear to everyone? Okay. Come on. Let's focus on this. Our question is resonance. But before Going to the definition of resonance, what resonance actually is, let me tell you what is conjugation. Conjugation means presence of at least 3 orbitals. Presence of at least 3 orbitals, whether p or d, at 3 adjacent positions. Parallel with respect to parallel and within the same plane. Parallel and within the same plane with respect to each other. With respect to each other. What is meant by this? Let's understand this definition with the help of few examples. For example, example number 1. If you have a compound like this, CH2 double bond CH, single bond CH, double bond CH2. Can I write this in this manner? CH2, single bond CH, single bond CH, single bond CH2, and after that I will show over here p orbitals. P orbital of this carbon, p orbital of this carbon, they have overlap, sideways overlap, that's why there is a pi bond. Similarly, here it's p orbital and here it's a p orbital, and after sideways overlap they form this pi bond. So can I say this means this? Now have a look and tell me, is this carbon having p orbital and p orbital within the same plane and parallel? Yes, that's why they overlap with each other. Similarly, this carbon and this carbon is also having p orbitals parallel and within the same plane, that's why they overlap with respect to each other. If I number these orbitals 1, 2, 3, 4, can I say at all these 4 positions there are orbitals which are parallel and within the same plane with respect to each other. If we have only 3 orbitals, whether they are p orbitals or d orbitals, which are present at 3 adjacent positions, parallel and within the same plane, we say that species is having what we call conjugation, or conjugation is present in that species. But here are 4 orbitals which are present at 4 adjacent positions, that too parallel and with respect to within the same plane with respect to each other. Hence, can I say this molecule is having what we call conjugation, or conjugation is present in this molecule. Now listen carefully. Alternate positions of, let me tell you that conjugation is present in this molecule. If conjugation is present in this molecule, compounds where conjugation is present, those compounds are known as conjugated compounds. So this is a conjugated compound. Why this is a conjugated compound? Because conjugation is present in this. And alternate positions of conjugated compound where conjugation is present, these are known as conjugate positions. So these positions where I form a star or asterisk, so these positions are basically alternate positions of a conjugated compound where conjugation is present. Where conjugation is present means where at least 3 orbitals are present at 3 adjacent positions, and that too parallel and within the same plane with respect to each other. These positions are known as conjugate positions. So this is a conjugated compound where conjugation is present, and their alternate positions is known as conjugate positions. So this is having conjugation. Similarly, if I write example number next, if I write like this, CH2 double bond CH, single bond CH3, can I say it means it's like this: CH2 single bond CH, single bond CH3. Here it's p orbital, basically it's p orbital, they have overlap with each other, and as this carbon is sp3 hybridized, remember whenever carbon is sp3 hybridized, there is no pure p orbital. No pure p orbital is available at that time. If carbon is sp2 hybridized, remember one pure p orbital or one unhybridized p orbital is available. So one pure p orbital is available at that time. And if carbon is having sp hybridization, we have two pure p orbitals available at that time. You know this from chemical bonding, you know this. Now, tell me what will happen over here. So, can I say in this molecule only two orbitals are present at two adjacent positions, parallel and within the same plane. Hence, this is not having any conjugation. Hence, this is not a conjugated compound. But if I write like this, CH2 double bond C double bond CH2. Remember, it's like this, CH2 single bond C single bond CH2. Now, as pi bond is formed between these two, that means its orbital overlaps with this orbital, and only those orbitals overlap which are adjacent to each other, parallel and within the same plane. Now, this is having sp2 hybridization, so only one p orbital will be available for this, but this is having sp hybridization. This is sp2, this is sp2. If this is having sp hybridization, this is one p orbital, so there will be another p orbital perpendicular to this. That means here will be another p orbital like this. But one p orbital will overlap with this, that means this one. Another p orbital will overlap with p orbital of this, so as to form this pi bond. That means there will be another p orbital, because this is sp2, this is having one p orbital, and they must overlap like this. Now tell me, this structure and this structure, they are same. But can you see there are these two p orbitals adjacent and parallel and within the same plane. These two are parallel, adjacent and within the same plane. But there are not three p orbitals, there are not three orbitals which are present at three adjacent positions which are parallel and within the same plane with respect to each other. There are four orbitals, but these two are in one plane, these two are in one plane. At least there must be three orbitals which should be present at within the same plane and at three adjacent positions. Hence, this is not having any conjugation. What about this? What about this? If I write down this, if I write down like this, now have a look. Have a look. This is like CH2, single bond C, single bond C, single bond CH2. Now have a look. Its hybridization is sp2, its hybridization is sp, its hybridization is sp, its hybridization is sp2. What does that mean? That means it's having one p orbital, this is having two p orbitals, this is having two p orbitals, this is having two p orbital. It's one of the p orbital will overlap with this and another will overlap with this. It's one of the orbital will overlap with this p orbital and another will overlap with this p orbital. Have a look, have a look. That means its p orbital, it's having only one p orbital as hybridization is sp2, will overlap with one of the orbitals of this, with one of the p orbitals of this carbon. But this carbon must have another p orbital perpendicular. So that means this is another p orbital and that p orbital will overlap with this, as these are within the same plane and form another bond. So this forms one pi bond here, one pi bond here. This forms one pi bond here, one pi bond here. After that, this is sp orbital, and sp orbital have two p orbitals. One is this, another will be perpendicular to this, that means like this and like this. What will happen? Now this will overlap with this. Now look towards this question, to this example, and tell me, can I say this pink orbital, this pink orbital, this pink orbital and pink orbital, these are within the same plane and parallel with respect to each other, and that too, these are four and we need only three. So at least three orbitals should be parallel and within the same plane and three adjacent positions, then conjugation is present. So yes, we can say conjugation is present. But this conjugation where only pi bonds are present, this is known as pi-pi conjugation. So conjugation over here is present. Now, I will simply give you a trick. If you have a pi bond and after that pi bond, any atom or any group is attached. If we have a pi bond, after that any atom or any group is attached by means of a sigma bond, this atom, we simply call this atom as key atom. So any atom other than hydrogen which is attached to carbon-carbon double bond, if this key atom contains a lone pair of electron or a negative charge or an odd electron or vacant orbital or a pi bond, then conjugation is present. Conjugation is present. This is in general trick, but this trick cannot be applied over here. This trick cannot be applied over here because here it's carbon-carbon double bond and it's not attached to any other atom or any other group by means of single bond. So this is actual way of finding whether conjugation is present or not. But this is the trick, and this trick is applicable everywhere except when carbon-carbon double bond is not attached to any atom or any group by means of single bond. Then you cannot use this trick. At that time you have to check whether all the orbitals are present at 3 adjacent positions, and that too parallel and within the same plane with respect to each other or not. Now, for example, with respect to this, if I write down example like this, CH2, double bond CH, single bond CH3. Now, what you have to look in this example, first of all, you have to find out whether carbon-carbon double bond is there. Yes. Is any group attached to that carbon-carbon double bond by means of single bond? Yes, that means this trick is valid. Now, this carbon becomes our key atom, but this key atom neither has a lone pair, nor a negative charge, nor odd electron, nor vacant orbital, nor pi bond. Hence, this is not a conjugated compound because conjugation is absent in this compound. Similarly, if I write like this, CH2 double bond CH, single bond BH2. What is B? B means boron. Boron is key atom here. And remember, first of all, you have to see whether this trick is valid or not. Yes, carbon-carbon double bond is attached to a group by means of single bond. That means trick is valid. Now, this key atom boron forms 3 bonds, 2 with hydrogen, 1 with this carbon. That means it's having 6 electrons. And we know second period elements must have maximum of 8 electrons. That means it's only having 6 electrons. That means it can acquire more 2 electrons. That means its orbital should be vacant. So key atom is having vacant orbital. Now tell me, if key atom is having vacant orbital, that means conjugation is present. So we can simply say conjugation is present. And this compound in which conjugation is present is known as conjugated compound, and these positions, alternate positions of conjugated compound where conjugation is present, these are known as conjugate positions. I hope this is clear to everyone that what is conjugation and what is the trick for conjugation. Now, after that, we will have types of conjugation. We will have types of conjugation. We will have types of conjugation. Now, with respect to unsaturated system, conjugation is of 2 types. Number 1 is pi lone pair conjugation, and another one is pi. Conjugation is of 2 types. Number 1 is pi p conjugation, and another is pi pi conjugation. I will not write down pi sigma positive, pi sigma negative, because it's not necessary that pi should be attached to sigma bond. You have seen that in this example. There is no sigma. So pi pi conjugation is present. So I will not write down like pi sigma positive, pi sigma negative, pi sigma lone pair. We will write pi p and pi pi. In this pi p, first example, or means say of this type is further subdivided into pi lone pair conjugation. What is meant by pi lone pair conjugation? That means you have an unsaturated system, and after that you have attached any atom or any group to this unsaturated system by means of single bond, and that key atom must contain lone pair. Key atom must contain lone pair. So this is the example of this. So what is pi lone pair conjugation? It is simply that conjugation in which all the conjugate positions have pi bond and a lone pair. All the conjugate positions have pi bond and lone pair. This is known as pi lone pair conjugation. Number second type is pi odd electron conjugation. Pi odd electron conjugation. Here, this is the simple example of pi odd electron conjugation. Conjugate position must contain pi bond and an odd electron. After that, third is pi negative charge conjugation. Pi negative charge conjugation. It means there must be pi bond and negative charge which are in conjugation with respect to each other. After that, it's a fourth type is pi vacant orbital conjugation. Pi vacant orbital conjugation. For example, either pi should be attached to a positively charged species, but that positively charged species which is having vacant orbital, or neutral species which is having vacant orbital. In nutshell, conjugate position must have pi bond and a vacant orbital is known as pi vacant orbital conjugation. Now here, which orbital is involved? Basically it is p orbital which is involved with this pi. That's why this is pi p. Here p orbital, here p orbital of carbon, carbon p orbital, here what we call p orbital of boron. That's why pi p conjugation. Another conjugation is Another conjugation is pi-pi conjugation. Its simple example is CH2 double bond CH, single bond CH, double bond CH2. Or it can be CH2 double bond CH, single bond CH, double bond O. I mean to say, this unsaturated system, atom which is attached to this unsaturated system must contain a pi bond, whether that pi bond is polar or non-polar. Whether that is non-polar, that means between similar elements, or that is between different elements. So these are types of conjugations, and these compounds where conjugations are present are known as conjugated compounds, and their alternate position where conjugation is present are known as conjugate positions. Hope this is clear to everyone. Now, after that, you must remember, if any conjugate position, say for example, I'm talking about of this conjugate position, oxygen, because first of all, which one is the conjugate position? This and this. So if any conjugate position contains more than one lone pair, only one lone pair will take part. Why? Because one lone pair is present in p orbital, another is present in sp2 orbital. But p orbital, this p orbital and this p orbital, they are parallel, hence they are in conjugation. This is present in sp2 orbital, which is not within the same plane with respect to these p orbitals. That's why whenever any conjugate position contains more than one lone pair, only one lone pair will take part in conjugation. This is a very, very important point. Another, whenever you are having more than one pi bond, if you are having more than one pi bond at one conjugate position, only one pi bond will take part. Only one pi bond will take part in conjugation. Only one pi bond will take part. You have to remember this as well. Why? Because another pi bond will be formed by those orbitals which are not within the same plane with respect to these p orbitals. Now, after that, whenever any species forms like this, I will change the example. If any species like this, contains a pi bond as well as a lone pair. If any conjugate position, say for example this is a conjugate position, its conjugate position is this and this. So if any conjugate position contains one pi bond and a lone pair, at that time it's only pi bond which take part in conjugation. Only pi bond will take part. Similarly, if any conjugate position contains pi bond and a negative charge, only pi bond will take part. That means this lone pair or negative charge is not taking part in conjugation, which is present on a double bond. What does that mean? That means whenever you have double bonded atoms, say for example carbon with a positive charge, similarly double bonded carbon with a negative charge, for example, or a double bonded carbon, I will remove this hydrogen, double bonded carbon, and similarly double bonded carbon with odd electron. So whenever you have a carbon or any atom with double bond as well as a positive charge, double bond as well as negative charge, double bond as well as, what we call odd electron, at that time positive charge, negative charge or odd electron will not take part in conjugation. Because conjugation, only those orbitals will take part in conjugation which are parallel and within the same plane. These orbitals are not parallel because their p orbital has already formed what we call pi bonds. These are present in different orbitals which are present in different plane. So I hope this is clear to everyone. You have to remember these 3 points for resonance or conjugation. You have to remember these 3 points forever. I hope you can easily remember these 3 points. Okay. After that, we have a look and try to understand what resonance actually means. Now, you have studied molecular orbital theory in chemical bonding, where sir told you if bond order is 1 between 2 atoms, that means those 2 atoms form a single bond. Similarly, if bond order is 2 between 2 atoms, at that time those 2 atoms form a double bond. And if bond order between 2 atoms is 3, at that time those 2 atoms form a triple bond. Okay, bond order can never be 0 and bond order can never be fractional. Or we can say if bond order is 0 or bond order is fractional, this one, at that time it does not have any physical significance. It does not have any physical significance. This is what you have already done in chemical bonding during MOT, molecular orbital theory. Does not have any physical significance. Now have a look. If I talk about CO3 having 2 minus ion, say carbonate ion. If I tell you that this carbonate ion have many properties, but one of the properties is that it's all carbon-oxygen bonds are identical. It's all carbon-oxygen bonds are identical. Please try to understand. We're going to understand resonance. Now, it's all carbon-oxygen bonds are identical. Now, I will try to draw the structure of this. It will be like this. CO having negative charge, double bond, O having negative charge. This is one of the structure. Another C double bond O having negative charge, O having negative charge. Its another structure will be C O having negative charge, double bond O having negative charge. Double bond between these two, double bond between these two, and double bond between these two. So these are the 3 structures. Now have a look. Between these 2 atoms, which type of bond is this? This is single bond. Single bond means bond order is 1. So this is having a physical significance. Similarly, bond order 1, physical significance. Bond order 2, physical significance. That means these structures are having some physical significance. Those structures which have physical significance, we can draw such structures. So we can draw such structures easily. But when we see its property that all carbon-oxygen bonds are identical, here this is single bond, this is double bond, they are not identical. Similarly, double bond and single bond, they are not identical. Double bond and single bond, they are not identical. So can I say, we can draw its different structures, but none of them can explain its property. But the structure which can explain its property, please try to understand. If I write bond like this, partial double bond, partial double bond, partial double bond, minus 2 by 3, minus 2 by 3, minus 2 by 3. If I draw this structure, please try to understand. If I draw this structure, it is clear that this structure, this carbon-oxygen bond is similar to this carbon-oxygen bond. And this carbon-oxygen bond is similar to this carbon-oxygen bond. That means this structure basically explains its properties because all carbon-oxygen bonds are identical. That structure which explains its properties is known as true structure. So this is true structure. Or we can simply say this is the real structure. But now tell me, is this bond single bond or a double bond? Neither single bond nor double bond. That means neither one nor two bond order. That means its bond order is fractional. But any structure whose bond order is fractional has no physical significance. And that structure which has no physical significance, we cannot draw that structure. So can I say, this species, this polyatomic ion is that species whose true structure cannot be drawn, but structures which we can draw cannot explain its all the properties. Yes or no? Remember beta, the species whose real structure cannot be drawn, but the structures which we can draw cannot explain all the properties of it. Remember, such species exhibit what we call resonance. So which species exhibit resonance? First of all, that's very important. So whenever we cannot draw true structure of a molecule or a species, or we can draw structures but none of them can explain its all the properties, then we simply say such species exhibit resonance. So can I say CO3 2 minus ion exhibits resonance? Similarly, if I write benzene, whose formula is C6H6. And when we talk about benzene, it's having many properties, but one of the properties is that all carbon-carbon bonds in benzene, are identical. Now, if I try to draw the structure of benzene, I will draw like this. Now, is this structure having any physical significance? Answer is yes. Another structure for benzene will be like this. So, is this having any physical significance? Answer is yes. But this is having double bond, single bond, that means different bonds. Double bond is smaller, single bond is larger. That means they are not identical. This structure cannot explain the property. Similarly, this structure cannot explain the property. But if I draw structure like this, that this bond is partial bond, partial double 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 bond. This can explain the properties, but problem is that we cannot draw this structure. Why we cannot draw this structure? Because here bond order is fractional and it can even, violate different theories, because this carbon can form 1, 2, 3, 4 and hydrogen. This is pentavalent, but carbon can form only 4 bonds. Hence, this structure cannot be drawn. We cannot draw this structure as bond order is fractional, and bond order fractional means this structure has no physical significance. Hence, the structure which is real, which is true, which can explain all the properties of a species, we cannot draw that. But we can draw structures which cannot explain all the properties. At that time, we call such species exhibit resonance. So, which species exhibit resonance? Those species exhibit resonance for which we cannot draw the structure which can explain all the properties, or which cannot draw true structure, but which we can draw structures But those structures, none of them can explain all the properties of a species. At that time, we simply say such species exhibit resonance. Now tell me, is this clear? Which species exhibits resonance? Only those species exhibits resonance whose true structure cannot be drawn, but whose structures we draw, none of them can explain all the properties. I hope this is clear to everyone. Let me know in the chat box, is this clear, so that we can move forward. Please let me know in the chat box, is this clear to everyone or not? So you should write down these things, that only that structure. Please let me know in the chat box, is this clear? Only those species exhibits resonance whose true structure cannot be drawn. Why cannot be drawn? Because that structure has no physical significance. That structure has bond order in fractional. But the structure which we can draw cannot explain all the properties of it. Okay, Priyanka. Okay, yes, sir. Okay, nice. Yes, sir. So clear. This is clear. So after that, now what is resonance? Try to understand that. So first of all, you must know which species exhibits resonance. Now, you must know what actually resonance is. Now, have a look. If I draw a ring like this, remember, all these carbon atoms are present within the same plane, and let us say these all carbons are present on this plane of this panel or plane of this board. Now, have a look. Let us suppose this carbon is having p orbital perpendicular to the plane. What is perpendicular to this board? That means p orbital is like this. One lobe is above this board and another lobe is below this board, but we will write down like this. So this is above and below. Similarly, this is having p orbital like this. This is having p orbital like this. This is having p orbital like this. This is having p orbital like this, and this is having p orbital like this. So each carbon are within the same plane, but their p orbitals are like this, perpendicular to the plane. Perpendicular to carbons, p orbitals are perpendicular to the carbons, but p orbitals are parallel with respect to each other. P orbitals are parallel with respect to each other. Now, listen carefully, listen carefully. Similarly, if I write down another structure like this, and here p orbitals are once again perpendicular to the carbon or the plane, but with respect to each other, they are parallel. They are parallel. Now have a look. If this is carbon, I mean say orbital number 1, orbital number 2, orbital number 3, 4, 5, and 6. Similarly, 1, 2, 3, 4, 5, and 6. Do you know, whenever orbitals are present at adjacent positions, parallel with respect to each other and within the same plane, they will overlap, sideways overlap and form a pi bond. You know that. So, can I say this 1 can overlap with 2 and result in the formation of a pi bond? Similarly, 3 can overlap with 4 and result in the formation of a pi bond. 5 and 6 will overlap and result in the formation of a pi bond. Now tell me, what will be the proposed structure at that time? The proposed structure of this will be at that time. Here will be a double bond, here will be a double bond, and here will be a double bond, and numbering is like this. Double bond is present between 1 and 2, between 3 and 4, and between 5 and 6. Now tell me, this double bond means pi electrons. These pi electrons are only between 1 and 2. These are only of 1 and 2. These pi electrons are not of 3. 3 is having another pi electron. Yes or no? Yes or no? These are having pi electrons. These pi electrons are only of 1 and 2. Whenever electrons are of only or shared between two atoms only, those electrons are known as localized electrons, and the bonding is known as localized bonding. So this structure is having localized bonding. Localized bonding. What about this? What about this? Is this necessary that 1 can overlap with 2 only? No, another possibility is 1 can overlap with 6. So another possibility is like this. But if this is another possibility that 2 can overlap with 3 and 4 can overlap with 5. So this is one of the possible structures of benzene, and this is another possible structure of benzene. Now have a look. Here double bond is present between this, this and this. Now tell, is benzene conjugated compound? Yes. Why? Because p orbitals are present at least at 3 adjacent positions, and that too parallel and within the same plane. So benzene is a conjugated compound. So we are talking about conjugated compound. So conjugated compound can overlap, benzene can overlap in this manner or in this manner. That means this is one of the proposed structure of benzene, this is another proposed structure of benzene. In both these structures, bonding is localized. Bonding is localized. What's meant by localized? That means this bond is of 1 and 2 only. This is not of 3 and 4. This is only of 1 and 2. Similarly, this is of 3 and 4. This is of 5 and 6. That's it. Similarly, these pi electrons or pi bond is between 2 and 3. It's not between 1 and 2. It's only between 2 and 3. It's only between 4 and 5. It's only between 1 and 6. That means pi electrons or pi bond is shared between 2 atoms only, not more than 2 atoms. Hence, bonding is localized and pi electrons are localized pi electrons. I hope this is clear to everyone. Now, listen carefully. If I write down like this, and if I draw its p orbitals, p orbital was like this, like this, like this, like this, like this, and like this. And this was number 1, number 2, number 3, number 4, number 5, and number 6. Now tell me, if I collect information from this, can I say 1 overlaps with 2? This will say 1 will overlap with 2. This says no, 1 will overlap with 6. So, collecting both these informations, can I say 1 can overlap with 2 and 1 can overlap with what we call 6 as well. Similarly, 2 can overlap with 1, 2 can overlap with 3. Similarly, 3 can overlap with 2, 3 can overlap with 4 as well. 4 can overlap with 3, 4 can overlap with 5 as well. 5 can overlap with 4, 5 can overlap with 6 as well. So this is the complete information taken from both these structures. When we take information, when we collect information from both these structures, we can simply say that benzene may have a structure like this, that this is here a partial overlap between 1 and 2 as well as between 1 and 6. Similarly, between 2 and 1 as well as between 2 and 3 as well as between 3 and 4 as well as 4 and 5 as well as 5 and 6. So I mean to say this is basically the structure where bonding is delocalized. Where bonding is delocalized. What is meant by delocalized bonding? Please remember. Here bonding is delocalized means these pi electrons are not between 1 and 2 only. These pi electrons are shared between more than 2 atoms now. In this case, pi electrons were shared between only 2 atoms. Here pi electrons are shared between more than 2 atoms. That means bonding is delocalized here. So for conjugated system, remember forever, for conjugated compounds, we can simply say resonance is, for conjugated compounds, resonance is defined as delocalization of pi electrons. It's defined as delocalization of pi electrons, which means partial overlap of orbital takes place. Partial overlap of orbital. Partial overlap of orbitals take place in such a way that pi electron density is same throughout. So whenever we are having conjugated compounds, for conjugated compounds, remember forever, resonance is nothing but resonance is delocalization. Resonance is delocalization of pi electrons, and that delocalization means partial overlap of orbitals, but in such a way that pi electron density is same throughout. So if you look towards this structure, whatever pi electron density is between 1 and 2, that is exactly same as that of 2 and 3, exactly same as that of 3 and 4, exactly same as that of 4 and 5, exactly same as that of 5 and 6. So here partial overlap of orbital takes place in such a way so that pi electron density is same throughout. This is known as what we call resonance as per delocalized, as per these conjugated compounds are concerned. So can I say here resonance takes place, but here there is no resonance because bonding is localized. So those structures whose bonding is localized, they are known as delocalized structures and is always separated by means of what we call double-headed arrow. Bonding is localized, but structures are known as, these structures are known as delocalized or resonating or contributing or canonical structures. So structure whose bonding is localized, they are basically known as delocalized structures, resonating structures, contributing structures, or canonical structures. They are always separated by means of double-headed arrow. And remember, they are basically hypothetical structures. These structures are hypothetical structures. These are not actual structures. They are hypothetical structures. These are proposed structures. These are theoretical structures. These are hypothetical structures. Why? Bonding is localized, still they are known as delocalized, because bonding is localized, but both these contribute. Both these give us information about delocalization. As both gives us information about delocalization, that's why those structures are delocalized structures. So structures which gives us information about resonance are known as resonating structures, which give us information about delocalization are known as delocalized structures. And it's their contribution that we can draw this structure. We can say resonance is present in this structure. That means they are known as canonical or contributing structures. I hope this is clear to everyone. But when we talk about carbonyl compound, when we talk about aldehyde or a ketone, say for example, we will talk about aldehyde or a ketone. Remember, my dear students, as there are only p orbital and p orbital, only two p orbitals are there, so we can simply say conjugation is absent. Conjugation is absent. But resonance is present. So it's not necessary that resonance is present only in those structures where conjugation is present. So this is not having any conjugation, but still resonance is present. So what is actually resonance? But before that, have a look. Actually, this carbon is having electrophilic nature. This is having electrophilic nature. So one of the properties of carbonyl compounds is that carbonyl carbon is electrophilic in nature. But this structure cannot explain that. But this structure can easily explain that this is electrophilic in nature. Electrophilic in nature means electron-loving species. So this is electrophilic in nature. So if this structure explains this property, but this cannot explain that there is double bond character between carbon and oxygen, but that is, given by this structure. So it's one is that it's having electrophilic nature, and there is double bond character between carbon and oxygen. Now tell me, this explains this explains this, but both these cannot explain all the properties. Hence we can simply say that these are not the true structures. This is an example where resonance exists. So from this and this, we can simply draw a structure. Now, have a look. This is either double bond and sometimes it's single bond. That means it's a partial double bond. Similarly, this is sometimes neutral, sometimes positively charged. That means this is partial positive, sometimes negative, sometimes neutral. That means this is having partial negative charge. So this is the actual structures. This actual structure explains its electrophilic character as well as double bond character between carbon and oxygen. So any species whose true structure, which explains all the properties, cannot be drawn, but structures which we can draw cannot explain its all the properties, we simply say a resonance is present. So hence in this example, a resonance is present, but this is not a conjugated compound. So we cannot say here resonance is delocalization of electron, because here that definition is not correct. So overall, what is the definition of resonance then? So remember, resonance definition, which is applicable for all compounds. Resonance is actually a way of describing bonding. It's a way of describing bonding or properties. Of certain molecules or polyatomic ions. By several contributing structures. With the help of several, contributing structures, and that property is explained in resonance hybrid. What is meant by resonance hybrid? Resonance hybrid means true structure, actual structure, like this, whose bonding is delocalized and explains all the properties. This is known as resonance hybrid. This is known as true structure, and whose bonding is what we call localized, whose bonding is localized and cannot explain all the properties. This is known as hypothetical structure, delocalized structure, resonating structure, contributing structure, or canonical structure. Now, have a look. Can I say resonance is simply a way of describing bonding? Okay? And it can explain properties of a species in resonance hybrid, but with the help of these several contributing structures. Similarly, here we explain properties of benzene. That means property of benzene is explained in resonance hybrid, but with the help of what? With the help of contributing structures. So what is resonance? Resonance is nothing but resonance is actually a way of describing bonding, or it's a way of describing properties in resonance hybrid, but with the help of several contributing structures, or with the help of delocalized structures. I hope this is clear to everyone what actually resonance is. But we generally deal with what we call conjugated compounds. That's why many teachers say that resonance is delocalization of pi electrons. But as far this is concerned, non-conjugated compounds, if conjugated compound is present, resonance is delocalization, no doubt about that. But what about this? This is not delocalization of pi electron. Hence, overall, this is applicable to every compound or every molecule, whether that is conjugated or non-conjugated. I hope this is clear to everyone what resonance actually means. Now, next question is conditions for resonance. Conditions for resonance. Point number 1. All resonating structures must have same energy or nearly same energy. All resonating structures must have same energy or nearly same energy. What's meant by that? Let's try to understand this with the help of example. If you are having CH2 double bond CH, single bond CH2 with a positive charge, and I will draw its resonating structure like this, CH2 single bond CH double bond CH2 with a positive charge. You can see if this is compound 1, this is compound 2, both are similar with respect to each other. That means whatever stability will be of this, same stable will be this compound as well. Hence, can I say their energy or potential energy of 1 is equal to potential energy of 2. So, both these structures have same energy. So, either both the resonating structures or all the resonating structures must have same energy or nearly same energy. These are resonating structure because their energy is same. This is one of the examples. Number second, if I write like this, CH2 double bond CH, single bond NH2. Now have a look, and I will draw its resonating structure like this, CH2 single bond CH double bond NH2 with a positive charge, and here with a negative charge. Now have a look. This is neutral. Neutral is more stable than charged ones, but here charge is present on a species, nitrogen and carbon, but those charged species are having complete octet. Remember, this is, if this is 1, this is 2. Remember here, 1 is more stable than 2, but stability difference is not that much. Hence, we can simply say potential energy of 1 is less than potential energy of 2, but it's not that much. Hence, we can simply say it's almost equal to potential energy of 2. So, when can we say that potential energies are almost same? If both are exactly equal, or one is neutral, another is charged, but charged species have, say complete octet. At that time, we can simply say the potential energies are almost same. But if I draw a structure like this, CH3, C double bond O, and then CH2 with a positive charge, and I draw its structure like this, its resonating structure like this, CH3, single bond C double bond CH2. Have a look, have a look. And then it's having like this. One is neutral, one is charged, another is also charged. But here positive charge is present on less electronegative element. That means stable. Here positive charge is present on more electronegative element, and that too which is not having complete octet. That means this is unstable. So if this is 1, this is 2. This is unstable, this is highly stable or stable. So we can say potential energy of 1 is very, very, very less than potential energy of 2. So how to decide potential energies? Listen carefully. If both are having similar structures, if one is neutral, another is charged, but charge present on an element is having complete octet, at that time almost same energy. But if one is having positive charge and less electronegative element, another is having positive charge and more electronegative element, but that too with 6 electrons only in its outermost shell. That means its octet is not complete. At that time, this is highly unstable structure. So we can simply say this is potential energy of this is highly lesser, or potential energy of this is very, very high as compared to this. Hence, we simply say these two can never be resonating structures. Hence, they cannot be separated by means of what we call double-headed arrow. I hope this is clear to everyone that potential energies must be either same or nearly same, either same or nearly same. If there is very large difference between potential energies, they can never be resonating structures. This is point number 1. Point number 2 is all the resonating structures must have same position or arrangement of atoms. For example, if I take an example like this, if I write down CH3 in this manner and then C double bond O, then H, and separated them by means of a double-headed arrow, you have to tell me can we separate these two by means of double-headed arrow? Now have a look. This hydrogen which is present over here at carbon is now at oxygen. What has happened here? Position of hydrogen has been changed, but what is the rule? All resonating structure must have same position or arrangement of atoms. That means position of atom cannot be changed. If position of atom cannot be changed, these can never be what we call resonating structures. Now, tell me, can I say these are the resonating structures? CH2, double bond CH, single bond NH2. Can I say these two are resonating structures? If I write down CH2, single bond CH, double bond NH2 with a positive charge over here and a negative charge over here. Answer is yes, they are. Why? Because carbon, hydrogen, nitrogen, no atom has changed its position. Arrangement is same, position is same, hence they are resonating structures. Hence, they can be separated by means of double-headed arrow. So, whenever resonating structures are there, you have to consider whether their energy is same or nearly same or energy difference is large. After that, is any atom which is, changing its position, or the position of every atom is same, or the arrangement of every atom is same. At that time, you have to understand which will be resonating structure and which will not be the resonating structure. So, this is point number second. Point number third. All the resonating structures must have same number of paired and unpaired electrons. Must have same number of paired and unpaired electrons. However, they differ in the way of distribution of electrons. In the way of distribution of electrons. What is meant by that? Let's have an example so that we can understand this. If you are having a structure like this, and after that like this. So what was rule number one? Energy should be almost same or same. So their potential energy is almost same. So yeah, we can simply say potential energy of 1 is equal to potential energy of 2. What was next rule? Position of atom or arrangement of atom should not change. All the resonating structures must have same position. So their position is same. And what is rule third? They have same number of paired electrons. How many paired electrons are there? You can count. 1, 2, 3, bond is having pair, 4, 5, 6, 7, 8. So I can write down 8 pairs of electrons. Here, 1, 2, 3, 4, 5. Oh, just a moment. It's having like this. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So 8 pairs. Okay. What about this? 1 unpaired electron. 1 unpaired. So, can I say both are having same number of paired and unpaired electrons? Both are having same position of atoms. And both are having same energies. Hence, these are resonating structures of each other. But distribution of electron, look towards this oxygen. Here, we are having 3 lone pair of electrons, but here only 2. So, distribution of electron has they differ in distribution of electrons, in the way of their distribution of electrons. Hence, these are resonating structures. Now, point number 4. Next point is, all the atoms which take part in resonance must be planar. or nearly planar. Why planar? Why nearly planar? Because what is resonance in general for conjugated compounds? It is delocalization. And what is delocalization? Partial overlap of orbitals. And overlap will take place only if orbitals are parallel and within the same plane with respect to each other, or nearly parallel. But once they are at 90 degree, that means once they are perpendicular to each other, they will never overlap. So they must be either parallel or nearly parallel with respect to each other. So let's understand this with the help of any example. Now have a look. If I write a structure like this, NH2, I will draw its resonating structure like this. This will overlap with this, and this overlap forms a negative charge over here. So this will be its structure. Now, if I write this one, now have a look. Hydrogens are replaced by methyl groups, that means bulky groups. This hydrogen is also replaced by methyl groups. These two positions are ortho positions, adjacent positions. Now, if resonance takes place, that means these two atoms, these two orbitals must overlap with respect to each other. After that, it will result in the formation of this one. After that, it will result in the formation of this one. Have a look. Now, the question is, these two groups, one, this one, and another this one. These two groups are bulky groups. And these bulky groups are present at adjacent positions. Hence, there will be a repulsion between electron clouds of these groups. And that repulsion is known as steric repulsion. Now listen carefully. First of all, these orbitals overlap because they were parallel with respect to each other. But once this group is repelled by this methyl group, this orbital changes its position because it goes to another plane. Now, this orbital is there, but this orbital, because of repulsion, goes here. Now tell me, this and this, they cannot overlap with respect to each other because they are not present within the same plane. So they can overlap within the same plane because there is no repulsion. They can overlap within the same plane. They can overlap. Why? Because they are present within the same plane. Similarly, they cannot overlap because they are not present within the same plane due to steric repulsion. Hence, we can simply say resonance is inhibited here because of steric repulsion, and that phenomenon is known as SIR. What is SIR? Steric inhibition of resonance. I mean, say this is inhibition of resonance, but due to steric repulsion, and steric repulsion takes place only if two adjacent positions, if two ortho positions, two adjacent positions have bulky groups. But here it's hydrogen, this is not bulky, NH2 is also not bulky, but here both the adjacent groups, both the groups are bulky which are present at adjacent positions. There might be steric repulsion, and this group goes in another plane and this carbon remains in another plane. Hence, these two atoms are not within the same plane. Hence, these are not resonating structures. They cannot overlap with respect to each other. This cannot be formed. Hence, these are not resonating structures. I hope this is clear to everyone. So, conclusion is, all those atoms which take part in resonance, they must overlap with respect to each other, and for that they must present within the same plane. But these two are not within the same plane. This is in one plane, this carbon is in different plane, and the reason is a repulsion between bulky groups, and due to that, as a repulsion between these groups converts this into another plane, and this carbon is in another plane. Hence, these two atoms are in different plane. There will be no overlapping, there will be no resonance. So steric repulsion inhibits resonance. This phenomenon is known as steric inhibition of resonance. Is this clear to everyone? Please let me know in the chats. Let me know in the chats. Let me know in the chats. Is this clear to everyone? Is this clear to everyone? What is meant by SIR? What is meant by SIR? What is meant by steric inhibition of resonance? And why these two atoms will not overlap? What happens here? And why these will overlap? These will overlap because there is no steric repulsion. These will not overlap because this is in another one plane. This is in another plane due to steric repulsion. And the property, that phenomenon is known as steric inhibition of resonance. Is this clear? 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 Let me know in the chats. Is this clear? We have to complete GOC. We have to complete GOC, and that too with, say, basics, and that too in detail, so that no question can bother you. Okay. Now, is this clear to everyone? Raj Kumar, it's clear, clear, clear. Okay. Okay. So can I move forward? Is this clear? Now, okay, all right. Now, after that, it's point number 5, condition number 5. All the atoms which take part in resonance, all the atoms which take part in resonance must have a maximum of 8 electrons if elements belong to second period. If elements belong to second period. Or maximum of 18 electrons if elements belong to third period. Because the elements used over here will be from second period mostly, but sometimes elements belong to third period. That's why I wrote only maximum of 8 electrons and maximum of 18 electrons. Now, have a look. If you are having a structure like this, CH2, double bond CH, single bond NH3 positive. Have a look. If I draw a structure like this, CH2, single bond CH, double bond NH3, what has happened to this? This nitrogen forms 5 bonds, 1, 2, and 3 with hydrogens. That means this is a pentavalent nitrogen. What is meant by pentavalent nitrogen? That means it's having 10 electrons. That means it is having 10 electrons. But do you know nitrogen is a second period element, and second period element can have maximum of 8 electrons because second period element is having outermost shell, that is second shell, and in that shell it's S subshell and P subshell. S subshell is having 1 orbital, P subshell is having 3 orbital. In total, there are 4 orbitals in valence shell of second period element, and an orbital can accommodate maximum of 2 electrons. So maximum electrons must be 8, but here it is 10, which is not possible. So this is not possible. If this is not possible, we cannot form this. If we cannot form this, that means these two are not the resonating structures of each other. So whenever elements which take part in resonance belong to second period, they can have maximum of 8 electrons. They can have 7, they can have 6, they can have 5, but they cannot have more than 8 electrons. Okay, but if I write like this, CH2 double bond CH, single bond PH3 positive. Now this P belongs to third period. This P belongs to third period. That means here P is pentavalent, but this P is pentavalent and it contains 10 electrons, but it is possible. Why? Because it belongs to a third period. So this is a third period element. It can have a maximum of 18 electrons. So it can accommodate 10 electrons easily. So these two are resonating structures. But if I write CH2 double bond CH, single bond OH, and draw a resonating structure like this, what will happen? It will result in the formation of this. This oxygen, carbon and carbon, they belong to second period. It's having 8 electrons, 8 electrons, 8 electrons. That's possible. So maximum of 8 electrons is possible. But more than 8 electrons is not possible if elements belong to second period. More than 8 electrons is possible up to 18, maximum of 18 electron if elements belong to third period. I hope this is clear to everyone. Now, after this, we must know how to draw resonating structures. Say for example, if you are having A double bonded with B and then any atom is attached to this unsaturated system by means of single bond and there is a lone pair, that means if we are having pi lone pair conjugation, at that time you have to draw a resonating structure like this. So this is pi lone pair conjugation. You have to write down structure like this. Okay. Now this was neutral, this becomes positively charged. This was neutral, this becomes negatively charged. So this is first one. And hybrid will be like this: A, B, C, sometimes single bond, sometimes double bond. Similarly, sometimes single bond, sometimes double bond. So sometimes negative charge, sometimes neutral, sometimes negative charge. So this will be their hybrid. So this is pi lone pair. Another will be, say for example, pi negative charge. Say it's like this. Similarly, you have to draw structure in similar manner. Here it will be A, B, double bond C, but this was negative charge, now it will become neutral. And this is negative charge. Only difference, neutral becomes positive charge, negative charge becomes neutral, and its structure will be like this. So this is having partial negative charge and this is having partial negative charge. Number third is pi vacant orbital. If this is having vacant orbital, say for example, then this is the way of drawing a resonating structure. Single bond B, double bond C. So this was having vacant orbital. Now, if this vacant orbital contains any positive charge, then it becomes neutral. But if this vacant orbital was neutral, if this was neutral, at that time it becomes negatively charged. At that time it becomes negatively charged. Okay, so this becomes positive charge, this becomes positive charge, and hybrid will be like this. Hybrid will be like this. Partial positive and partial positive. Here it will be A, B, C, partial positive will be on A, and C will be having partial negative charge. This is pi vacant orbital, but vacant orbital is having present on, say this atom is having vacant orbital, but at the very same time that atom is having a positive charge. But if this atom is having vacant orbital but is neutral, at that time it's like this. Okay, after that it is pi lone pair, pi odd electron conjugation. At that time you have to show fish hook arrow, half-headed arrow, so that one electron from here, one electron from here will form a double bond. So it will result in the formation of this. So it is A, B and C. A, B forms a partial double bond because sometimes it's single bond, it's sometimes double bond. Similarly, sometimes single, sometimes double, so partial double bond. This A is neutral, sometimes odd electron, so it is partial odd electron. Similarly, C is having odd electron, C is having neutral, that means it's having partial odd electron. So these are basically pi p conjugations. What has happened here? Lone pair becomes bond pair, and bond pair becomes lone pair. Similarly, lone pair becomes bond pair becomes lone pair, bond pair becomes bond pair becomes bond pair. Among bond pair, one electron is moved towards this odd electron and forms a bond. So this is the way of drawing resonating structures for pi p conjugation. Now, what will happen if conjugation is pi pi? Say if conjugation is A double bond B, single bond B, double bond A, and a double bond is between similar elements. At that time, either you will show arrow from this side to this side or from this side to this side. Now, it's our choice. After that, it will become A, single bond B, double bond B, single bond A. This is having negative charge, this is having positive charge. Hybrid will become A, B, B, and A. So partial double bond, partial double bond, partial double bond. This is having partial positive charge and this is having partial negative charge. Now, if A double bonded B and then C double bonded D, and let us suppose C double bonded D is electron withdrawing as compared to A double bond B, then arrows towards electron withdrawing. If A and B is electron withdrawing, then from CD towards AB. So it will be like this. So it is A, single bond B, double bond C, single bond D. D is having negative charge, this is having positive charge. So simply it can be like this. We must try different resonating structures so that you can easily draw these structures. So this was how to draw resonating structures. Now, after that, we have a very important question, and that is stability of resonating structures. Stability of resonating structures. Now, listen carefully. First, you have to remember that resonating structure, which is neutral, in nutshell, neutral resonating structure is more stable than charged resonating structure, is more stable than charged resonating structure. For example, you have a structure like this, CH2 double bond CH, single bond NH2. Suppose this is structure number 1. This is structure number 2. According to this rule, which one is more stable? Now, let me know in the chat box which is more stable. What will be the order of stability here? What will be the stability order here? Quickly let me know in the chat box. Quickly let me know in the chat box. According to rule number 1, neutral resonating structure is more stable than the charged resonating structure. So here, two resonating structures are present. One is neutral, one is charged. Which one is more stable? Because rule number 1 is given. That means neutral resonating structure is more stable than charged resonating structure. Now tell me, which one is neutral? Which one is neutral and which one is charged? You have to see that and answer this question. Let me know in the chats quickly which one is more stable, or what will be the stability order. What will be the stability order? This is neutral. This is charged. So which one is more stable? This is neutral. This is charged. Which one is more stable? Let me know in the chat box. Let me know in the chat box what will be the answer. What will be the answer? Let me know in the chat box. Great. One greater than 2. Nice. Now have a look. As this is neutral, this is charged. Can I say one is more stable than 2? One is more stable than 2. Why? No, more charged species is more reactive. More reactive means less stable. So this is less stable and this is more stable. So this is point number 1. Point number 2, or rule number 2, is resonating structure with more covalent bonds. Resonating structure with more covalent bonds. You can write pi bonds. You can simply use resonating structure with more pi bonds instead of covalent bonds. So resonating structure with more pi bonds is more stable. Resonating structure with more number of pi bonds is more stable. Example. If I write example number 1, CH2 double bond CH, single bond CH, double bond CH2. This is having 1 pi bond, this is having 1 pi bond. In total, this structure is having 2 pi bonds. After that, if I write CH2, single bond CH, double bond CH, single bond CH2, negative charge and a positive charge. What will be the stability order? What will be the stability order? Which one is having more number of pi bonds? Answer is 1 greater than 2, as this is having more pi bonds as compared to this. But remember, if same question is given in your NEET examinations, you simply use rule number 1. If rule number 1 does not give you answer, then use rule number 2. Suppose if this is given in an examination, I will use rule number 1. This is neutral, this is charged. I will say this is more stable as compared to this. But at this time, we have to understand rule 2. That's why we will focus on rule 2 at this time. This structure is having 2 pi bonds. This structure is having only 1 pi bond. So more pi bonds means more covalent bonds, means more force of attraction. More force of attraction means more stability. So this is more stable as compared to this one. Point number 3. Resonating structure in which all the atoms have complete octet except hydrogen, is considered more stable. Is considered more stable. For example, we can understand this rule with the help of this example. If you are having CH3, single bond C, triple bond O with a positive charge, and another structure is like this, CH3, C, positive, double bond O. Now have a look. This carbon forms 4 bonds, which means its octet is complete. This carbon forms 4 bonds, that means it's complete octet. Oxygen forms 3 bonds, means 6 electrons, 7 and 8, that means its octet is complete. Its octet is complete, its octet is complete, but it's having only 6 electrons. That means all the atoms here are having complete octet, but here this is not having complete octet. That means this is the structure where all the atoms do not have complete octet. So the resonating structure where all the atoms have complete octet is more stable. So the stability order will be 1 greater than 2. So this will be the stability order. Is this clear? Okay, is this clear to everyone? I hope this is clear to everyone till now. Now, after that, condition number 4, or we can say rule number 4. If all the resonating structures have some charge, then resonating structure in which negative charge is present on more electronegative element and positive charge is present on less electronegative element is considered more stable. For example, if we have a structure like this, CH3, C, CH3, O having a negative charge and carbon having positive charge. Second, CH3C, CH3, carbon having negative charge and oxygen having a positive charge. Now have a look. If we use rule number 1, neutral resonating structure is more stable than charged, but this is charged, this is charged. No one is neutral. So we cannot use rule number 1. After that, we can use rule number 2. What was rule number 2? More chemical bonds or more pi bonds, but both are having same number of bonds. That means rule number 2 cannot answer the question. After that, use rule number 3. What was rule number 3? Rule number 3 was, if all the atoms have complete octet, but here carbon is not having complete octet, that means all the atoms are not having complete octet. Similarly, here oxygen is not having complete octet. So we cannot use rule number 3 as well. So rule number 4. Rule number 4 says, if resonating structures are charged resonating structures, then positive charge should be present on less electronegative element. Carbon is less electronegative as compared to oxygen because charges are present on carbon and oxygen. We know carbon and oxygen, they belong to same period, and electronegativity increases from carbon to oxygen. So carbon is less electronegative, so positive charge on carbon is more stable as compared to positive charge on oxygen. Similarly, negative charge on oxygen is more stable as compared to negative charge on carbon. So its stability order will be 1 greater than 2. Next point or next rule, say rule number 5, is if charge separation, we can write down like this, resonating structure in which charge separation means distance between the charges, in which charge separation means distance between the charges between unlike charges is less, is considered more stable, is considered more stable. For example, if I write an example like this, it's having a negative charge, this is having a positive charge. Similarly, and another structure is like this. This is having negative charge and then this is having a positive charge. Now, positive and negative, unlike charges are there. Here, positive and negative, they are separated by a larger distance and they are separated by lesser distance. Wherever charge separation between two unlike charges is less, that resonating structure is more stable. Hence, the answer will be 2 greater than 1. Now, next is resonating structure in which like charges are present on adjacent, like charges are present on adjacent atoms is considered least stable, considered as least stable. I hope this is clear. Say for example, if you are having positive and positive charge on adjacent position, negative and negative charge on adjacent position, negative and lone pair on adjacent position, lone pair and lone pair on adjacent position, at that time remember these types of species or resonating structures are highly unstable if like charges are present on adjacent positions. Now, we will practice a few questions related to stability. But before that, I hope everything is clear to you. Now have a look. Have a look. First of all, question number 1, compare stability. How to compare stability? Now, neutral resonating structure is more stable, but there is no neutral structure. That means rule number 1 cannot explain the answer. After that, use rule number 2. How many pi bonds are there? 1, 2. 2 pi bonds. Only 1 pi bond and 2 pi bonds. That means the structure having more pi bonds is more stable. That means structure with lesser pi bond is least stable. So 2 is the least stable. After that, 1 and 4 having equal pi bonds. That means rule number 2 cannot distinguish these two. Now use rule number 3. What was rule number 3? Octet. Here in compound number 1 is species number 1. Every atom has complete octet, and in a third every atom has complete octet. Then next rule. Nitrogen is having positive charge. Nitrogen is having positive charge. That means positive charge is present on similar element. So positive charge stability is exactly equal. But what about nitrogen having negative charge, carbon having negative charge? Among nitrogen and carbon, which one is more electronegative? It's nitrogen. So negative charge present on nitrogen is more stable as compared to negative charge present on carbon. So the answer is 1 greater than 3 greater than 2. So this is the answer. Now, I hope second question you can easily answer that. Then after that, you just try third as well. I will answer fourth question. First of all, rule number 1. According to rule number 1, first one is neutral, other two are what we call charged. So rule 1 says that first structure is the most stable structure. After that, according to rule 2, number of pi bonds are equal. Then after that, every atom must have complete octet. Both are having complete octet. That means rule 3 cannot distinguish. After that, rule 4. Rule 4 says the charge, oxygen having negative charge, oxygen having negative charge is exactly, say stable. But here oxygen having positive charge and here positive charge is present on nitrogen, and positive charge present on less electronegative is more stable. Hence we can simply say 3 is more stable than 2. 3 is more stable than 2. So this is the answer. So question number, this question and this question. You simply solve these questions. These are easy questions and I hope you can answer these questions easily. Someone is answering 1, 3, 2. Yes, good, great, great. Raj Kumar, Siva, Krishna, nice. Physics 351, great, 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 great. Yes, yes, 1, 3, 2 is the right answer for this. But you have to solve question number 2 and question number 3. Yes, 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 beta, yes, Roshni, exactly 1, 3, 2 is the right answer. You have to solve this question and this question. This will be an home assignment or homework for you. Now after that, another heading is stability of any species. How can we explain the stability of any species but due to resonance? Remember forever, stability of any species due to resonance is directly proportional to extent of resonance. Means more the resonance, more will be the stability of that species but due to resonance. Now the question is extent of resonance. Is directly proportional to linear conjugation. So that compound in which conjugation is linear is having more resonance, and that compound which is having more resonance is more stable according to resonance, and it is inversely proportional to cross conjugation. Now try to understand this with an example. Simple example. If I write like this and second one like this. Now here conjugation is linear, but here conjugation is, but it's in branch. This is in conjugation with this is in conjugation with this, but these are not continuous pi bond, this chain is continuous chain, but this is outside this continuous chain. That means these pi electrons are in conjugation with this, but there is a branched conjugation. This is linear conjugation. So now tell me, this conjugation is linear, this is cross conjugation. Whenever there is a branched conjugation, this is cross conjugation. Hence, can I say this is having more resonance as compared to this? So 2 is having more resonance as compared to 1, or 2 is more stable as compared to 1 as per resonance is concerned. So this is point number 1. This is point number 1. Point number 2 is extent of resonance is directly proportional to equivalent resonance. And it is inversely proportional to non-equivalent resonance. It's inversely proportional to non-equivalent resonance. What is meant by equivalent resonance and what is meant by non-equivalent resonance? Let's have some example. Say for example, example is like this. First compound is RCOO having negative charge, and another example is RCOOH. And we have to find out which one shows more resonance or which one is more stable because of resonance. But this is the resonating structure. First of all, draw all its resonating structures. Whenever question is like this, draw all resonating structures. So when you draw all the resonating structures, you can draw its hybrid. So its hybrid will be, this will be a partial double bond, this will be a partial double bond, and after that, this is having partial negative charge, this is having partial negative charge. Remember. Question given was, among these two, which one is stable? Yeah, among these two, which one is having more resonance? But remember, we know we can draw its resonating structure, draw a resonance hybrid first. Similarly, draw a resonance hybrid of this. Whenever you can draw a resonating structures, draw a resonance hybrid, and after that compare resonance hybrid stabilities basically. So this is its structure. So its hybrid will be like this. Now, this is double, sometimes single, that means this is partial double bond. Sometimes single bond, sometimes double bond, that means this is partial double bond. So this is a partial double bond. And this oxygen is sometimes neutral, sometimes positive charge. This oxygen is sometimes neutral, sometimes negative charge. Now have a look. Tell me, resonance occurs in this, but that information was given by these two structures. Similarly, resonance occurs in this, but that information was given by these two structures. Now tell me, can I say resonance whose information is given by those structures whose stability is equal? Remember, because this structure and this structure, both are resonating structures and both are equally stable. So whenever equal stable resonating structures give information about resonance, we call that resonance as equivalent resonance, because that resonance has given, that information about that resonance has been given by equal stable resonating structures. Whenever equally stable resonating structures contribute towards resonance, gives information towards resonance, we simply call that resonance as equivalent resonance. But here, this is neutral resonating structure, this is charged resonating structure. This is more stable, this is less stable. That means they are not equally stable. Whenever resonating structures are not equally stable, they will not contribute equally. They will not give information equally towards resonance, hybrid towards resonance. That structure which is more stable, remember, that structure which is more stable contribute more towards resonance hybrid or contributes more towards resonance. That means its contribution will be more, its will be less. That means this is non-equivalent resonance. What about this? Its contribution and its contribution both are equal. Why? Because both are equally stable. Hence, contribution will be equally stable towards resonance hybrid. Hence, in this case, resonance occurs and that resonance is equivalent resonance. But in this case, there is resonance and is non-equivalent resonance. Whenever resonance is equivalent, that resonance is more resonance, or that structure will be more stable than non-equivalent resonance. I hope this is clear to everyone. So that resonance whose information is given by equally stable resonating structures is known as equivalent resonance, and that resonance whose information is given by unequal stable resonating structures is known as non-equivalent resonance. And any structure where equivalent resonance occurs is more stable than any structure where non-equivalent resonance occurs. That is the reason this is more stable as compared to this according to resonance. That's why this carboxylic acid loses H positive and forms RCO minus. That's why carboxylic acid is an acid. So why carboxylic acid is an acid? Because it prefers to lose H positive so as to form more stable what we call RCO minus or conjugate base. Okay. I hope this is clear. Now, tell me, is both these points clear? Let me know in the chat box. Now, one is equivalent, non-equivalent resonance. Another is linear and cross conjugation. Linear conjugation means when your conjugation is basically in a straight line or linearly, continuously, but when conjugation is not continuously, it is branched, then it is known as non-linear conjugation. Then it's known as cross conjugation. And what is equivalent resonance? That resonance in which resonating structures are equally stable and gives information equally towards resonance. But if resonating structures are not equally stable, they will not give equal information towards resonance hybrid. That is known as non-equal. That is known as simply non-equivalent resonance. Which resonating structure will contribute more? Which will give information more? That resonating structure will contribute more towards resonance, more towards hybrid, which is more stable. So I hope this is clear to everyone. Now, so these were 2 points, and point number 3 is extent of resonance is inversely proportional to electronegativity of atom which shows resonance. For example, CH2 double bond CH single bond NH2. What is the difference between these two structures? Have a look. And only difference is here it's NH2, here it is OH2. That means here it's N which takes part in resonance, here it's O which takes part in resonance. Which is having less electronegativity? N and O. Do you know N and O? We know electronegativity increases. So which one is less electronegative? Nitrogen. So any atom which takes part in resonance is less electronegative. That shows more resonance. So one shows more resonance as compared to 2. So one shows more resonance as compared to 2. So here it is also 1 greater than 2, because in 1 there will be equivalent resonance and 2 non-equivalent resonance. Here 1 is less electronegative, hence shows more resonance. This is more electronegative, hence shows less resonance. Now, point number 4. Extent of resonance is directly proportional to number of conjugated positions. For example, let's have a simple example. And number second. Now, both are conjugated compounds, but it's p orbitals. That means conjugation is from this point to this point. Here it's p orbital, p orbital, p orbital, p orbital. But these two are not having any p orbital. So conjugation is from this to this. That means here conjugate position is from this to this, 1 and its alternate position. That means 2 conjugate positions. So conjugation is present from this to this. So conjugated part is having alternate positions. These two. So alternate position of conjugated part is known as conjugate position. Here conjugation is complete from this to this, and the alternate position of conjugated part are known as conjugate positions. Here conjugate positions are 3, here conjugate positions are 2. Hence a resonance will be more in 1 as compared to 2. So 1 greater than 2 will be the answer. I hope this is clear till now. After that, point number 5. Extent of resonance is directly proportional to strength of overlapping. Why strength of overlapping? Because resonance in general is overlapping. So now have a look. If you are having CH2 double bond CH single bond NH2 and another one will be CH2 double bond CH single bond PH2. Here when this overlap takes place, it will take place between nitrogen and carbon, and it is basically 2p orbital of nitrogen which overlaps with 2p orbital of carbon. That means identical orbitals will overlap. But here, when this overlap takes place between phosphorus and carbon, it is 3p overlap of phosphorus, 3p orbital overlap of phosphorus with 2p overlap of carbon. And we know in chemical bonding, we know this, that identical orbital overlap is stronger overlap. So this 2p overlap will be stronger as compared to 2p 3p overlap. So the answer is 1 is having more resonance as compared to 2, or 1 is having more stability as compared to 2 according to the resonance. According to the resonance. Great. Now, next point is point number 6. Extent of overlapping, extent of resonance is directly proportional to energy of delocalized electrons. Energy of delocalized electrons. For that, let me tell you, in resonance, delocalized electrons are pi electrons. But what are pi electrons? They are electrons which are part of either double bond or triple bond, or which are present in conjugated orbitals. Now listen carefully. If conjugated orbital contains lone pair, that's also a pi electron. If it contains a negative charge, that's also a pi electron. And energies of these relative energies, energy order of these delocalized pi electrons is, first of all, negative charge, then lone pair, then double bond, then triple bond. So it's not only that double bond and a triple bond are having pi electrons. No. If lone pair is present in conjugated orbital, this is also considered as pi electron. If negative charge is present in conjugated orbital, this is also considered as pi electron. Now, have a look. Example. If I write like this, R S double bond O having a negative charge, and then I will write like this, R S double bond O single bond O having a lone pair. Now have a look. Here it is lone pair which takes part in resonance. Here it's negative charge which take part in delocalization or resonance. Whose energy is more? So energy of delocalized electron. If energy of delocalized electron is more, extent of resonance is more. So I can simply say 1 greater than 2. So 1 is having more resonance as compared to 2, or 1 is more stable as compared to 2. I hope this is clear till now. Now after that, we are having another question, that is another concept is there, that's negative charge holding capacity. Now, in this, remember stability of negative charged species. Stability of negative charged species, you have to remember, is directly proportional to negative charge holding capacity. Directly proportional to negative charge holding capacity. That means any species which can hold negative charge accurately is more stable negative charge. That means any species which can hold negative charge on it is more stable negative charge. Now, whenever we know negative charge holding capacity, we simply know, if we know negative charge holding capacity, we simply know what we call negative charge stability. But remember, point number one, negative charge holding capacity. Negative charge holding capacity is directly proportional to electronegativity. This is the formula you have to remember. Negative charge holding capacity is directly proportional to electronegativity, but here when it is applicable, if elements belong to the same period. Elements belong to the same period. If elements belong to the same period. For example, let's have an example so that we can understand this. Number one, you are having CH3 having negative charge. You are having NH2 with a negative charge. You are having OH with a negative charge. And then you are having F with a negative charge. Now here negative charge is present on carbon, nitrogen, oxygen, fluorine. They belong to the same period, and we know in same period electronegativity increases on moving from left to right. So this is having more electronegativity. So any species which is having more electronegativity, if they belong to the same period, then its negative charge holding capacity will be more. So whose negative charge holding capacity will be more? It is 4, then 3, then 2, then 1. So 4 is having more negative charge holding capacity. If 4 is having more negative charge holding capacity, that means 4 is more stable among these. After that it is 3, after that it is 2, after that it is 1. I hope this is clear to everyone. So this is point number 1, or rule or formula number 1. Formula number 2 is negative charge holding capacity. Negative charge holding capacity is directly proportional to size. That's another formula, is that negative charge holding capacity is directly proportional to size. But remember, this formula is applicable if elements belong to the same group. If elements belong to the same group. For example, if we are having F having a negative charge, then Cl having a negative charge, then Br having a negative charge, then we are I having a negative charge. As we know, these F, Cl, Br, I, they belong to the same group. If they belong to the same group, we have to check their size. And we know on moving from down the group, size increases. So whose size is larger? It's I minus, it's 4. Hence, 4 is having more negative charge holding capacity than 3, then 2, then 1. So this is negative charge holding capacity order, and this will be the stability order as well. I hope this is clear to everyone. Now, after that, if I write like this, whose negative charge holding capacity? Compare, question is like this. Compare negative charge holding capacity. Compare negative charge holding capacity. Compare negative charge holding capacity. So, it's like this. Number 1, OH minus. Number 2, SH minus. Similarly, it's having SH minus and number second Cl minus. In first question, can I say O and S, they belong to same group, hence we have to check size, and size on moving down the group increases. So whose size is more? It's SH minus, so can I write it is 2 greater than 1. But in second case, it is sulfur and chlorine, they belong to same period, so we have to check electronegativity. Whose electronegativity is more? It's Cl minus. That means I will simply write 2 greater than 1. It's Cl minus, which is more stable or which is having more negative charge holding capacity. Now, this is for you. Negative charge holding capacity. Negative charge holding capacity of, remember, one oxygen is greater than 10 carbon, number one. Number second, negative charge holding capacity of one chlorine is greater than 2 oxygens is greater than 1 sulfur. Now, what's meant by this? That means if only one oxygen is having negative charge and in comparison to it 10 carbons are having negative charge, then this is more stable as compared to this. Similarly, if one chlorine is having negative charge, 2 oxygen is having negative charge and 1 sulfur is having negative charge, which one is more stable? It's having 1 chlorine. What does that mean? Now, listen carefully. If you are having OH having negative charge, number one. Number second, you are having, say for example, a structure like this. You must know that this carbon having negative charge will take part in resonance, then negative charge will be at this position ortho, and after that it will take part in delocalization, negative charge will be here, after that it will be here. That means 1, 2, 3, 4. That means here negative charge is present on 4 carbon atoms. But here negative charge is present on 1 oxygen atom. So trick is that negative charge present on 1 oxygen is greater than 10 carbons. So where negative charge holding capacity is more, it is 1 greater than 2. Similarly, if we are having like this, Cl minus, number second, RCOO negative, and number third, SH having a negative charge. Can you say here negative charge is present on 1 chlorine, here negative charge is present on 2 oxygens. Why? Because when it resonates, negative charge is present on this, in another structure negative charge will be present on this. That means in hybrid negative charge is present on both the oxygens. Here negative charge is present on 1 sulfur. What was the trick? What was the trick? What was the trick? Negative charge present on 1 chlorine is more than 2 oxygens is more than 1 sulfur. So it will be simply 1 greater than 2 greater than 3. Okay. Now if I write like this, Cl minus, and after that I write OH minus, and after that I write SH minus. This is on 1 chlorine, this is on 1 oxygen, this is on 1 sulfur. Remember, this is more stable because negative charge on 1 chlorine is more stable than 2 oxygens. That means here it's only 1 oxygen and 1 sulfur. That means it's 1, after that it is 3, after that it is 2. Sir, why not 1? 1 is clear. Why not 2 and after that 3? Because OH and SH minus, you have already shown that OH and SH minus, it is SH minus because of size. But. So S comes first, after that oxygen, but if oxygens are 2, S is only 1, then oxygen comes first as compared to this one. Now, with the help of this negative charge holding capacity. You can simply answer negative charge stability or negative charge holding capacity. You can answer the stability of negative charged species, or you can answer acidic character as well. Say for example, you are having a structure like this. You're having structure like this. Say for example, this hydrogen is 1, this hydrogen is 2, this hydrogen is 3, this hydrogen is 4. And you have to write down the acidic character. So what will we do? We will remove H. That means we will see negative charge. Negative charge will be present on 1 nitrogen. Here, when this H is removed, that means conjugate base, we will form conjugate base, negative charge will be present on 1 oxygen. If we remove this, negative charge will be present on this. After resonance, it will goes to this. That means negative charge will be present on 2 oxygens. What about this? Negative charge will be present on only 1 sulfur. Now tell me, negative charge on 1 sulfur is greater than 1 oxygen. 1 oxygen is greater than 1 nitrogen, because oxygen and nitrogen belong to the same period, and same period is, say that depends on electronegativity. More electronegative oxygen as compared to nitrogen, so negative charge is stable on this. So when elements belong to same period, oxygen and nitrogen, the element which is having more electronegative element is more stable. So its conjugate base will be more stable as compared to this. But as compared to sulfur and oxygen belong to the same group, and we have to see size in that. So sulfur is having more size as compared to this, but oxygens, 2 oxygen, trick is here, 2 oxygen and 1 sulfur, which whose electronegative charge holding capacity is more, it's oxygen. So what will be the answer? Answer will be simple. First of all, it will be hydrogen number 3, which is easily removed, because after removal its negative charge is more stable. After that it is 4, then it is 2, and lastly it is 1. That means if we know negative charge holding capacity, we can answer many acidic order questions. We can answer many questions in which we have to find out the acidic order as well. Now tell me, is this clear to everyone till now? Is this clear to everyone till now? Is this clear to everyone? Let me know in the chat box. Is this clear? Is this clear, everyone? Is this clear? 4, 3, 2, 1. 4, 3, 2, 1. 4, 3, 2, 1. No, it's 1 sulfur, it's 2 oxygen. 2 oxygens, negative charge holding capacity of 2 oxygens is more as compared to sulfur, and negative charge holding capacity of 1 sulfur is greater than negative charge holding capacity of 1 oxygen. Now, there are few, exceptions. Now have a look. We know if we compare acidic strength, say for example, if we compare acidic strength of water and alcohol, we first of all form conjugate base. That means its conjugate base is this and its conjugate base is this. Now remember, these are the conjugate bases, and stability of conjugate bases, negatively charged species, will be like this on the basis of inductive effect. Whenever negative charge is attached to plus I, that becomes less stable. So answer is OH minus is more stable than RO minus in general. Therefore, what will be the acidic order? Acidic order will be water is stronger acid than alcohol. Water is stronger acid than alcohol. But if we take an example of water and methanol, methanol is an example of alcohol where R is CH3. What should be the answer? Answer should be water greater than methanol. But here acidic character, here acidic order or acidic character is a reverse. That means it is methanol which is more acidic than water. But this order cannot be explained on the basis of conjugate base. But why is it so? This is basically its Ka value is greater than Ka value of water, and Ka values have been find out, that means Ka values are known to us with the help of experiments. So this is the experimental order. So combining these two, we have to remember forever and note at what is that? That is, like, according to conjugate base concept, water should be stronger acid than methanol. But in actual sense, experimentally it has been shown that methanol is stronger than water, and the reason is Ka. Ka value of methanol is greater than Ka value of water, and we know strength of acid is directly proportional to Ka. So therefore, we have to remember always that water is stronger acid than alcohol except methanol, which means methanol is stronger acid than water. So remember these two formulas forever. Okay, similarly, next, so this was the exception. So here you have to mark this one, otherwise you will do wrong answer. Now, another thing is that if you have water and acetaldehyde, according to negative charge holding capacity, its conjugate base is this, and this is the conjugate base of this. Now have a look. Negative charge is present on one oxygen, negative charge is present on carbon, but it can be present on oxygen as well. That means it's present on one oxygen plus one carbon. So stability order of conjugate bases, order of conjugate bases should be this CH2 minus CHO should be stronger, more stable base as compared to OH minus. But in actual sense, this is not true. In actual sense, what happens is that CH2 minus CHO is less stable than OH minus, indicating that if this is in actual sense, this is, but indicating that it simply indicates, what it indicates, that water is stronger acid than acetaldehyde. And the reason is once again Ka values. So this cannot explained by conjugate negative charge holding capacity or stability of the conjugate base. So these are two exceptions which you have to remember. One, water and acetaldehyde. Another is water and methanol. So water and methanol is stronger acid because of more Ka than water. Similarly, in case of water and acetaldehyde, water is stronger acid as compared to acetaldehyde because of more Ka value as compared to Ka value of acetaldehyde. Hope this is clear to everyone. Now, next topic is resonance effect, but before doing that, let's have a break of it's 4:50, 25 minutes. So break till 4:15. So let's meet at 4:15, but I want everyone among you to be present so that we can move forward in this topic. So thank you. Take care. We'll meet at 4:15. Thank you. Hello, hello, welcome back, welcome back. Please let me know if I'm audible and visible in the chat box. Please let me know. Please let me know, am I audible and visible to everyone? Am I audible and visible to everyone? Please let me know in the chat box quickly. Please let me know in the chat box quickly. Am I audible and visible to everyone? Let me know in the chat box. Am I audible and visible to everyone? Please let me know in the chat box so that we can continue. Okay, yes, sir. Now, our question is resonance effect. Now, what is resonance effect? Before doing that, if I write down CH2 double bond CH, single bond NH2, can I say this NH2, what will this do according to resonance? This is our conjugated system. As this NH2 will donate electron towards this conjugated system. When this donates electron towards conjugated system, it increases electron density of this conjugated system. Similarly, if a conjugated system is like this and we have NO2 group attached to this conjugated system, what will NO2 do? It will simply withdraw. It will simply withdraw electrons away from conjugated system. So this group withdraws electron away from conjugated system and this group donates electron towards conjugated system. So can I say that electron donating capability or electron withdrawing capability of any substituent, electron donating capability or electron withdrawing capability of any substituent because of resonance is known as resonance effect. So what is resonance effect? It is simply electron donating or electron withdrawing capability of any substituent because of resonance. So here you must know that resonance is a mechanism. Resonance is a mechanism by which resonance effect operates. So, whenever any atom or any group withdraws electron or it donates electron, any substituent which can donate electron or withdraw electron because of resonance, at that time we call that effect as resonance effect, and resonance effect is operating only if resonance is present. That means if resonance is not present, there will be no resonance effect. I hope this is clear that what actually resonance effect means. Now, this resonance effect is of two types. Number one is electron donating resonance effect. That means it is plus R effect. First is plus R effect. What is meant by plus R effect? Have a look. It is that resonance effect due to which any atom or any group donates pi electrons towards conjugated system. and increases electron density of conjugated system. And if benzene is our conjugated system, then such groups increase electron density mainly at ortho and para positions. Now, let's try to understand what we have written over here. Now, this is a conjugated system, and if I attach a group which donates electron towards this conjugated system, then such group increases electron density of conjugated system. That's why these groups are known as what we call plus R groups. So what is plus R effect? It's that resonance effect due to which any atom or any group donates electron towards conjugated system and increases electron density of this conjugated system. But if our conjugated system is benzene, then what will happen? Now have a look. Such groups donate electron density towards conjugated system and increases electron density at this point. So I mean to say electron density will be increased at this position. So what is this position? What is this position with respect to this to which NH2 group is attached? This is adjacent position, that means ortho position. After that, when further resonance takes place, its electron density will be increased at which position? Have a look. Its electron density will be increased at this position. This is para. After that, once again, it will increase at what we call ortho position. In nutshell, now it can form another resonating structure like this. So if we look towards the hybrid of this, the hybrid will be like this. Hybrid will be like this. Hybrid will be like this. Here will be a partial double bond, 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 partial double bond. And after that, here will be a partial double bond. This nitrogen is sometimes neutral, sometimes positive. That means partial positive charge. And this is having partial negative charge, partial negative charge, partial negative charge. Have a look towards this hybrid. What has happened to this ring? This ring becomes negatively charged. It looks like to be neutral first. Now it becomes negative charge. That means gain of electron has been taken place. So its electron density is increased, but it has been increased with respect to this. It has been increased at ortho position and para position. Meta position remains unchanged. The electron density of meta position remains unchanged, which means resonance has no effect on meta position. So what is plus R effect? Any atom or any group when donates electron towards conjugated system and increases its electron density. If conjugated system is what we call benzene, it increases electron density at ortho and para position. Such groups are known as plus R groups, and such effect is known as plus R effect. I hope this is clear to everyone. Is this clear to everyone? Please let me know in the chat box. Is this clear till now? Is this clear till now? Is this clear till now? Let me know in the chat. Let me know in the chats. Yes, 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 yes. Let me know in the chats. Is this clear to everyone? So that we can move forward. Okay. Now, after that, you must know that plus R groups increase electron density at ortho and para positions. Hence, such groups are ortho para directing with respect to electrophile. With respect to electrophile. What is meant by that? We know electrophiles are electron-loving species. Say, for example, when we react this aniline with electrophile, electrophile wants to go to that position where electron density is more. Now, because of this NH2, electron density is more at ortho and para position. So, can I say this group gives a direction to electrophile that go to ortho and para position, as I have already increased electron density at ortho and para position. Hence, such groups, such NH2 or such plus R groups are ortho para directing with respect to electrophile. One more point is that plus R groups are activating groups. Basically, it activates the ring. They are activating groups. They are activating groups. Activates ring for electrophilic substitution or for electrophiles. So, plus R groups are activating groups except halogens. What does that mean? That means halogens are ortho-para directing, but deactivating group. Why is it so? Have a look. Now, if benzene ring is attached to halogen or halogen is attached to benzene ring, now because of lone pair of electron, it increases electron density first at ortho, after that at para, then at ortho. That means this is ortho-para directing. But this is ortho-para directing due to resonance. But do you know, in case of halogens, minus I, that means inductive effect is powerful than plus R, that means resonance. If inductive effect is powerful, that means it overall decreases electron density because it withdraws sigma electrons away from this benzene ring. So it increases electron density at ortho and para position due to resonance, but it decreases electron density by withdrawing sigma electrons due to inductive effect. So in nutshell, it decreases electron density of the ring in overall. That's why this is activated. This deactivates what we call halogens, deactivates the benzene ring. That's why halogens are deactivating. But due to resonance, they increase electron density at ortho and para. So electrophile will go to ortho and para position. Hence, they are ortho-para directing. So remember, plus R groups are always ortho-para directing and activating except halogens. That means halogens are ortho-para directing, but they are not activating, they are deactivating because their inductive effect is stronger than resonance. Their electron withdrawing inductive effect is stronger than electron donating resonance. I hope this is clear to everyone. Now, after that, you have to remember plus R series. For that, I have written mnemonics for that. That means that this will be a trick for you. So first of all, it's CH2 minus. For CH2 minus, you write, remember, crazy. Then NH minus, that means negative. Then O minus, that means outlaw. That means crazy, negative, outlaw, naughty nuns. Crazy, negative, outlaw, naughty nuns never obey old orange nurses offering offering fresh, clean brown ice. So you can remember, say these groups with the help of this mnemonics. But remember, first of all, we write down here anions which are present on key atom. Key atom is that atom which is attached to, conjugated system. So here it's a conjugated system to which this carbon is attached. So carbon becomes key atom. Whenever key atom is having negative charge, its plus R will be stronger than any neutral species. So first of all, anions, then neutral species. But among neutral, if elements belong to same period, then lesser electronegative, then more electronegative. But if elements belong to the same group, then smaller size, then larger size. I hope this is clear to everyone, and I hope this will help you in remembering this series. After that, electron withdrawing resonance effect. That means minus R effect. Now have a look. If we are having a conjugated system like this, and we are having N double bond O, and this is a coordinate bond, what will happen? This O is more electronegative than nitrogen, so it withdraws electrons away from nitrogen. Nitrogen becomes deficient, so it withdraws electrons from here. So can I say this nitro group withdraws electrons away from, pi electrons away from what we call conjugated system. Similarly, if our conjugated system, remember, if our conjugated system is benzene ring, then what will happen here? Have a look. It withdraws electrons away from benzene ring and it simply decreases electron density at ortho position. Have a look. It simply decreases electron density at ortho position. After that, electron density is decreases at para position also. Now when we draw another resonating structure, it will be like this. So you will see that electron density has been affected at either ortho or para. That means ortho and para positions become electron deficient because of electron withdrawing group. Finally, it will form like this, double, 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 single, and this is N, this is double bond O, it's like this. So have a look. If you look towards the hybrid, it's like this. So it will be a partial double bond, 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 partial double bond. So it's having partial negative charge. This is having partial positive charge, partial positive charge, partial positive charge. Now have a look. What will happen to the ring? It's forming positive charge. That means electron deficient. But at which position? At ortho, because with respect to this, these two are ortho positions and this is para. At ortho and para position because of NO2. So such groups which withdraws electrons, let me write down. So minus R effect is that resonance effect, due to which any atom or any group withdraws pi electrons away from conjugated system, and decreases electron density of conjugated system. Due to resonance. Have a look. So if any group withdraws pi electrons away from conjugated system and decreases electron density of this conjugated system because of resonance, then such groups possess plus, so what we call minus R effect. Yeah, such groups possess minus R effect, and the phenomenon is known as minus R. Now, have a look. If our conjugated system, if our conjugated system is benzene, then such groups decrease electron density at ortho and para positions due to resonance. Now tell me, if electron density is decreased, now tell me, if electron density is decreased due to this minus R group at ortho and para position, that means ortho and para becomes deficient, by default meta becomes rich. So where electrophile goes, it will go to meta position. So can I say such groups are, can I say such groups, I mean say minus R groups, such groups are meta directing with respect to electrophile, meta directing with respect to electrophiles. I hope this is clear. So minus R groups are simply meta directing due to electrophiles. That means they decrease electron density at ortho and para position. And remember, such groups are deactivating groups. Such groups are deactivating groups. Ortho para directing groups are activating groups except halogens, but these are all minus R groups are deactivating groups. I hope this is clear. Now, these are few groups which show minus R effect. That means this is minus R series. To remember this minus R series, I have written over a trick or a mnemonics like this. Pro nitro scholars can always keep all eggs away and conclude. I mean to say, first of all, it's PR3 positive, starts with P, hence pro. Nitro starts with N, hence nitro. This is sulfonic acid, starts with S, hence scholars. CN starts with C, hence can. This is CHO, but it's known as aldehyde, that's why always. This is known as ketone, that's why keep, starting with K. This is, I mean say, anhydride. Anhydride starts with A, hence all. This is ester. Ester starts with E, hence X. This is carboxylic acid, I mean say acid, hence A, starts with A. This is amide, starts with A, hence and. This is carboxylate ion, as it starts with C, hence this is conclude. So this is the way, with the help of these mnemonics, you can remember all these, I mean say, minus R groups. Now after that, remember, whenever you are having a conjugated system, say for example like this, and to this conjugated system there is an atom or a group. So this will be known as our key atom. If key atom, remember, if key atom contains either lone pair of electron or a negative charge or a non-polar pi bond, that means key atom forms a pi bond with similar element, and in addition to that shows resonance. Key atom is having lone pair and shows resonance, or it's having negative charge and shows resonance, or forms a multiple bond, double bond or a triple bond with similar element and shows resonance, then such groups possess what we call plus R effect. Such groups possess plus R effect. Similarly, this is point number one. Similarly, this is a trick for you, trick to remember. This is trick to remember which group shows plus R and which group shows minus R. Now, if you are having a conjugated system, whether it's carbon-carbon double bond or a benzene ring, to that key atom, an atom other than hydrogen is attached, And if this key atom is having vacant orbital, or it forms a polar pi bond, and it forms a pi bond, but that pi bond is formed with its more electronegative element. That means it forms a polar pi bond, and in addition to that shows resonance. So whenever key atom is having vacant orbital and shows resonance, or whenever key atom is having polar pi bond and shows resonance, at that time we simply say such groups possess -R effect. Now, if this is clear to you, let me have few questions over here. Let us practice over there which one is +R and which one is -R. Now have a look. Now this bond is attached to conjugated system. That means this becomes our key atom. Key atom is having lone pair and shows resonance. Hence, this is +R group. Similarly, this is +R group. Similarly, this is +R group because it's having lone pair and shows resonance. This is having negative charge and shows resonance, so +R. This key atom is having lone pair and shows resonance, hence +R. Similarly, negative charge is present on key atom and shows resonance, therefore +R. Now, carbon having positive charge, that means this is having vacant orbital. Whenever key atom is having vacant orbital and shows resonance, it's -R. Or sometimes we write +R and or we write +M. We write +M instead of +R in a plus mesomeric effect, or -M instead of -R. So +R, +M, one and the same for your class, and -R, -M is same for your class. Similarly, this is also having vacant orbital, therefore it shows -R. This is having a negative charge, therefore it shows what we call +R. Here it shows +R because of lone pair. It shows -R because of polar pi bond, because pi bond is present between two dissimilar elements, because this is the key atom and this key atom forms a pi bond with more electronegative element. The more electronegative element will withdraw electron towards itself. This becomes deficient and it will withdraw electron from what we call conjugated system. Hence, this is -R. This is also a -R group. This is also a -R group because key atom forms a polar pi bond. This phosphorus belongs to third period element. Third period element. It belongs to a third period element. Hence, it's having vacant d orbital. It's not having vacant p orbital, but it's having vacant d orbital. In nutshell, vacant orbital is there. Hence, it shows -R. It shows -R because of polar pi bond. 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 But look towards this. This is a second period element. And second period element can have maximum of 8 electrons. That means it already forms 3 sigma bonds with 3 hydrogen, and this is the fourth bond. It already is having 8 electrons. If it withdraw electrons, say for example this is the conjugated system. If it withdraws electron from conjugated system, listen carefully. If it withdraws electron from conjugated system, nitrogen becomes pentavalent. Nitrogen contains 10 electrons at that time, which is not possible. Hence, this neither shows -R nor shows what we call +R. It neither shows -R nor shows +R. Similarly, this neither shows -R nor shows +R. Why? Because for -R or +R, there must be resonance, but this cannot take part in resonance because this is already sp3 hybrid orbital. This is also sp3 hybrid orbital. Whenever hybridization is sp3, there is no p orbital. If there is no p orbital, there will be no overlap. If there is no overlap, there will be no resonance. If there is no resonance, there can never be -R or +R. I hope this is clear to everyone. Next topic is applications of resonance. First application is stability of carbocation. Second application is stability of carbonyl carbon radical. Number third is stability of carbanion. That means anion, negative charge present on carbon. And all these applications, all these, say stability of carbocation, stability of carbon radical, stability of carbon, anion or carbanion is directly proportional to extent of resonance. It is directly proportional to extent of resonance. For example, let me take few examples so that we can understand this. For example, we are having this one. This is known as phenyl methyl carbocation. And another one is like this. This is known as biphenyl methyl carbocation. Another one is like this. This is known as triphenyl methyl carbocation. Its shape is propeller shape. The fan of aeroplane, it's like of that shape. Or if you don't have, you don't never see, say if you don't have see that fan of aeroplane, exhaust fan. Let me tell you, exhaust fan. Their blades are somewhat like that. They are slightly tilted, so they can never repel each other. So they are having a propeller shape. Now, after that, have a look. These are the conjugate positions. These are the conjugate positions. How many conjugate positions are this? 4. What about this? Alternate positions. Alternate position with respect to this. Alternate position with respect to this. It's 1, 2, 3 in this ring. Similarly, it can show resonance with this ring as well. So more the number of conjugate positions, more will be the resonance or extent of resonance. More the extent of resonance, more will be the stability. So which one is more stable carbocation? Phenyl methyl carbocation, biphenyl methyl or triphenyl methyl carbocation. This can be written as this as well, this one. And this is basically this one. And this is this one. So what will be the stability order? Remember, stability order will be simply 3, 2 and 1. Why 3, then 2, then 1? Because 3 shows more resonance because of more number of conjugate positions. We know extent of resonance is directly proportional to what we call number of conjugate positions. This is 1. Example number 2. Example number 2 is like this. If I write phenyl methyl carbon free radical, then biphenyl methyl carbon free radical, then triphenyl methyl carbon radical. Once again, same reason over here. So conjugate positions 1, 2, 3, 4. Number of conjugate positions 1, 2, 3, 4, 5, 6, 7. Conjugate positions 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. More the number of conjugate positions, more will be extent of resonance. Therefore, stability order once again here will be 3, 2, 1. So more the resonance, more will be the stability according to the resonance. Another example is like this. Another example is like this. If you are having a carbanion, phenyl methyl carbanion, then biphenyl methyl carbanion, biphenyl methyl carbanion. Number third, triphenyl methyl carbanion. Once again, according to NEET, we will say answer will be like this. Have a look, have a look. So I think everything is clear till now. So according to NEET, stability order should be, it's 3, 2 and 1. This is for, say NEET. But listen carefully. If this 3 is most stable carbanion, if I write down a structure like this, remember forever, if I write down structure like this, triphenyl methane and biphenyl methane, and I will tell you which one is more acidic. Remember, strength of acid is directly proportional to stability of conjugate base, but conjugate base is this one which is more stable than this, hence it should be more stronger acid than this. But in actual sense, this is the acidic character order. This is the acidic character order in actual sense. This is the acidic order. What does that mean? If this is more stronger acid, that means it can donate H positive easily, or its conjugate base is more stable. So in actual sense, this is more stable than this. But for NEET, this is okay. You just remember 3, 2, 1. But I am giving you the actual idea. So this is more stable than this. Do you know the reason? Reason is simple. This is not propeller shape. There will be little bit repulsion between these bulky groups. So whenever a little bit repulsion is there, that means the groups which were present within the same plane, they will be slightly in different plane, hence resonance will slightly decrease as compared to this. So here resonance will be lesser, here resonance will be more. So this is more stable than this in actual sense. But according to NEET, you just remember 3, 2 and 1. After that, another application is application number 4. Application number 4. That is acidic, or simply we can write relative acidic characters. Relative acidic characters of sulfonic acid, let me write down like this. Relative acidic character of number 1 sulfonic acid, number 2 carboxylic acid, and number 3 phenol. Have a look. We know among these 3, stronger acid will be that whose conjugate base will be more stable. So let me form conjugate base of this. So conjugate base of this is like this. We will lose H positive, we will remove H positive and form a conjugate base. So its conjugate base will be like this. Its conjugate base will be like this. But when I draw all the resonating structures, I will form resonating structures like this. This will be its another resonating structure. And then another resonating structure will be like this. So this will be the resonance hybrid RSO, O, and then partial double bond, partial double bond, partial double bond. This is having what we call slight negative charge, slight negative charge, slight negative charge. So in this case, there will be a resonance. Similarly, if I write down its resonating structure and a resonance hybrid, so its resonance hybrid will be like this. Have a look. Slight negative, slight negative. And for this, its resonating structures will be like this. Now, negative charge, double bond, then negative charge will be at para position. then negative charge will be at ortho. So it's double bond, negative charge, double bond, then negative charge will be on oxygen. Have a look, have a look, have a look. So that means its hybrid will be like this. So it will be over here, partial double bond, partial double bond. This is sometimes negative charge, sometimes neutral, negative charge, and negative charge. Now have a look. We will compare these hybrids. Now this hybrid is formed with the help of these structures. That means these all structures give information to form this, which means when we compare these resonating structures, all these resonating structures are equally stable. When resonating structures are equally stable, their contribution towards resonance hybrid will be equal, and resonance is known as what we call equivalent resonance. Similarly, these two resonating structures are equally stable, hence both will contribute equally, which means this hybrid is formed with the help of equal contribution of these resonating structures. Hence, once again, resonance is equivalent resonance. But this resonating structure is more stable as compared to this. What does that mean? That clearly indicates there are not equal resonating structures, equally stable resonating structures. That means this will contribute in one way, this will contribute in another way. That means they cannot contribute equally. Hence, this resonance is non-equivalent resonance. Do you know resonance, when it is equivalent, means more, and when it is non-equivalent, means less? So can I say these two are more stable as compared to this? Now the question is, these two are more stable as compared to this, but here conjugate positions are more. Conjugate positions are 1, 2, 3. Conjugate positions are only 2. So can I say more the conjugate position, more the resonance? So this is most stable than this, than this. Can I say therefore acidic order? Therefore acidic order will be. Acidic order will be. Acidic order will be. Sulfonic acid will be stronger acid than carboxylic acid. In general, carboxylic acid is stronger acid than phenol. What is the reason? Why sulfonic acid is more stronger acid than carboxylic acid? Because conjugate base of carboxylic acid is more stable, that of sulfonic acid is more stable than conjugate base of carboxylic acid. Now what is the reason? Both are having equivalent resonance, but this is having more number of conjugate positions as compared to this. So more number of conjugate position, more resonance, more stability. But this is having more stability than this. Why? Because this is having equivalent resonance, this is having a non-equivalent resonance. So this is the answer, because this answer comes from the resonance hybrid. That means answer comes from resonance. That's why this becomes what we call another application of resonance. Now, after that, fifth application is basic character of amines. Basic character of amines. This is another application. Now have a look. Say for example, you are having a base like this. Then you are having base like this. And then you are having base like this. And you have to answer this question on the basis of resonance. And let us suppose you have to answer this in a protic solvent. What will happen? Now have a look. Can I say this electron density of nitrogen is used by resonance of this ring? This electron density will be used either towards this or towards this. That means electron density of this nitrogen is more used. What about this? Either towards this or towards this or towards this. Now tell me, among these three amines, which nitrogen is having electron density more available? Now listen carefully. As this uses electron density, but only on one side of the ring, this uses more because resonance is more. This uses most because resonance is most. That means electron density available here will be less, and electron density available here will be more. More the electron density, more more the availability of electron density, more easily it can donate its electron pair, and hence more basic will be the that amine. So basicity order here will be A greater than B greater than C, or in nutshell we can simply say basicity order for such amines or such bases in which base uses its electron density for resonance. Remember, whenever it uses more, so extent of resonance, remember, if it uses its electron density more in resonance, then its basicity will be less. So here extent of resonance is more extent of resonance, hence basicity will be less. Extent of resonance is less, hence basicity will be more. I hope this is clear to everyone till now. Now, after that, sixth example is bond length. Sixth example is bond length. Remember this one. Single bond is a larger bond than partial double bond, and partial double bond is larger than double bond. Double bond is larger than triple bond. Now, this partial double bond arises because of resonance. It's not, partial double bond cannot be because of inductive effect, it is because of resonance. Now, if it is because of resonance, it seems to be either single bond or double bond. Now, what is the difference between this single bond and this single bond? This is actual single bond. This is the single bond which seems to be single bond, but in actual sense it's a partial double bond. This is actual double bond, but this is the double bond which seems to be double bond, but in actual sense because of resonance it's a partial double bond. At that time, remember, bond length of such single bond which seems to be a single bond but in actual sense is a partial double bond because of resonance is inversely proportional to extent of resonance. And bond length of that double bond which is not actually the double bond, seems to be a double bond but in actually is a partial double bond, is directly proportional to extent of resonance. What is this? Let us understand with few examples. Let's understand these formulas with the help of few examples. Have a look. First of all, tell me what about this X? Is X a single bond or it seems to be a single bond? Now have a look. This is not single bond because when resonance takes place, it becomes double bond and this becomes single bond. So its resonating structure will be like this. Have a look, try to understand. So it will become like this. So X bond seems to be first, in this case single, now it seems to be a double bond. But when we draw hybrid of these, hybrid is like this, CH2, single bond CH, single bond NH2. But this CN bond is sometimes single bond, sometimes double bond, that means it's a partial double bond. Similarly, CC bond is sometimes double, sometimes single, that means it's a partial double bond. So this nitrogen is sometimes neutral, sometimes positive, this carbon is sometimes neutral, sometimes negative, hence partial negative charge. Now tell me, it seems to be single, but in actual sense it's a partial double bond. So this single bond is this one because it seems to be a single bond, but in actual sense it's a partial double bond because of resonance. Similarly, this double bond seems to be a double bond, but in actual sense it's a partial double bond. That means this double bond is actually this one, seems to be a double bond, but in actual sense it's a partial double bond. I hope you got what is this single bond and what is this double bond, and what is this single bond, what is this double bond. These are actual single and double bonds. Now, if I write a question like this, compare bond lengths. Compare bond lengths. Say, you have a question like this. CH3, CH2 and Cl. This bond is bond X. We have to find out bond length of X, Y and Z or Z. Now tell me guys, do you know this will take part in resonance? Whenever single bond takes part in resonance, it's not normal single bond. It seems to be a single bond, but it is actually a partial double bond. Similarly, here it takes part in resonance. So Z is not a single bond, it's a partial double bond. What about this? There will be no resonance at all. There will be no resonance at all. That means this is a normal single bond. What about this? Partial double bond. What about this? A partial double bond. Now tell me. We will write, first of all, we will write single bond and then partial double bond. So, whose bond length will be larger? So, bond length order will be simply bond length order will be simply X. Now, among Y and Z, both are partial double bond, but seems to be single bond. Partial double bond seems to be single bond. Now have a look. For that we have this formula. If you have partial double bond which seems like that of single bond, then bond length is inversely proportional to extent of resonance. Means where resonance is more, bond length will be less. Have a look. Can I say this is a conjugate position, this is conjugate position, this is conjugate position, this is conjugate position. 4 conjugate positions are here, and here we are having only 2 conjugate positions. So can I say resonance will be less, resonance will be more? Now have a look, sorry. If resonance is less, bond length will be more. Now tell me, among these two, resonance is less, bond length will be more. So can I say it is Y and after that it is Z. First of all, normal single bond, then partial double bonds. But among partial double bonds, both seems to be single bond. So write down that one in which resonance is less, after that in which resonance is more. I hope this is clear. Now, after that, next question. Next question is like this. If I write NH2, suppose this is bond X, then NH, suppose this is bond Y, and then bond Z. And then say for example bond M. Now tell me, what is this? As there is no resonance over here, this is normal single bond. There is no resonance over here because whenever pi bond and lone pair are there at same element, there will be no resonance. So this is a normal double bond. What about this? There will be resonance. That means this is partial double bond, but which seems to be like that of a single bond. Similarly, this is partial double bond, but it seems like that of a single bond because it's a partial double bond. Now tell me, first of all, we will write single bond, then partial double bond, and double bond will be at the end. So single bond is X. It's not 1. 1 is the molecule, but we have to write down the bond. So it is X greater than. And at the end, it will be Y. Now, in between, it will be Z and M. Now the question is, it seems to be single bond, but is a partial double bond? Then it's inversely proportional to, bond length is inversely proportional to resonance. Compound in which resonance is less, bond length will be more. So in this case, only 2 conjugate positions are there, so resonance is less. In this, we are having 3 conjugate positions, resonance is more. So lesser resonance means more bond length. Hence, we can simply say Z. After that, we can write down M and then what we call Y. Hope this is clear. Hope this is clear to everyone. Now, after that, let me show you another example. Let me show you another example. If you are having like this, CH2 double bond CH, number second, it is OCH3, single bond CH, double bond CH, single bond NO2. And then third is like this, CH2 double bond CH, single bond N, double bond O, single bond O. Now have a look. If this is X, this is Y, this is Z. Now can you say this is normal double bond? There will be no resonance, hence this is normal double bond. What about this? This is a partial double bond. Why partial double bond? Because you know there will be a resonance like this. There will be a resonance like this. So this is a partial double bond. Similarly, this is also a partial double bond. This is also a partial double bond. But my dear students, this partial double bond seems to be a double bond. It seems to be a normal double bond and it seems to be a normal double bond. Now tell me, partial double bond, among partial double bond and double bond, which one will be last? Double bond will be at last. So X will be at last. Now, among Y and Z, this is partial double bond, this is partial double bond, but it seems to be like that of a double bond. It seems to be like that of a double bond. In these two, we know more the resonance, more will be the bond length because it seems to be a double bond. So for that purpose, we must know conjugate positions. Now 1, this is 2, this is 3. Here conjugate position 1 and then it is 2. Only 2 conjugate positions are there. Here 3 conjugate positions are present. So in this case resonance is more. If resonance is more over here, this is Y. So Y will be having more bond length as compared to Z, and Z is having more bond length as compared to X. Now tell me, is this clear to everyone till now? Let me know in the chat box, is this clear to everyone till now? Let me know in the chat box, is this clear to everyone till now? Let me know in the chat box, is this clear to everyone till now? Come on, quickly. Come on. Come on, tell me. Is this clear to everyone? Y, Z, X. Great, great, great. Now, is this clear? Is this clear? Tell me, clear. Yes, sir. Okay. Now, after that, we are having aromaticity. It's already written over here, but the questions will not be asked from what are aromatic compounds, what are non-aromatic compounds. What you have to remember is the stability order. What you have to remember is their stability order. Remember, aromatic compounds are highly stable than non-aromatic compounds. Then non-aromatic compounds are highly stable than anti-aromatic compounds. So these are highly stable compounds, these are highly unstable compounds, and these are stable compounds. Remember this order. So with the help of this order, actually we make few, conditions for aromatic compounds, for non-aromatic compounds, and for anti-aromatic compounds. What are those conditions? Let me write down over here. For aromatic compounds, you have to remember these things. For aromatic compounds, you have to remember condition number 1 must be cyclic, number 2 must be planar, must be complete delocalization. Complete delocalization. But these three combine together and we can simply say our compound must be cyclic and must be having complete cyclization, complete cyclic conjugation or cyclic complete conjugation. I will write down like this: complete cyclic conjugation must be present. Similarly, for anti-aromatic compounds, there must be same condition. Number one, it must be cyclic, it must be planar, and number third, it must be complete. It must be having complete delocalization. Or instead of these three, we will see only this: complete cyclic conjugation. So, if our compound is having complete cyclic conjugation, it may be either aromatic or anti-aromatic. If complete cyclic conjugation is not present, then it's neither aromatic nor anti-aromatic. At that time, it is non-aromatic. Now, fourth condition is it must have 4n plus 2 pi electrons. And all these four conditions are known as Huckel's rule. So, in nutshell, compound must obey Huckel rule, then it's aromatic compound. So, if aromatic compound is that compound if it is having complete cyclic conjugation and must have 4n plus 2 pi electrons. Now, the question is, what is n? N starts here from 0 to infinity. So, if n is 0, at that time compound must have 2 pi electrons. After that, add 4 electrons. That means 2, after that it is 6, after that it is 10, after that it is 14, 18, 22, 26, so on and so forth. Now, here it must have 4n pi electrons, and here n starts from 1 to infinity. That means if compound is having 4 pi electrons, that means it obeys at that time 4n pi electron rule. Similarly, if it's having 8 pi electron, 12 pi electron, 16 pi electron, so on and so forth, 4, you have to add 4, then it obeys this rule, otherwise it obeys this rule. If electrons present are 3 pi electrons, that means it neither obeys this nor obeys this. That means it at that time neither is an aromatic compound nor is an anti-aromatic compound. At that time it is non-aromatic compound. Now, the question is, what are pi electrons? Remember, one lone pair of electron is considered 2 pi electrons. One lone pair is considered 2 pi electrons. I will write down over here. One lone pair is considered 2 pi electrons. One negative charge is also equivalent to 2 pi electrons. And one pi bond is also equivalent to 2 pi electrons. But if lone pair or negative charge or pi bond is present in a conjugated orbital. So let's use these in different examples and let us see which of the following is aromatic, which of the following is anti-aromatic, or which one is non-aromatic. Now listen carefully. All open structures are non-aromatic, because for anti-aromatic it should be cyclic, for aromatic it should be cyclic. So all open chain compounds are non-aromatic. Now have a look. Now this is carbon-carbon double bond. When carbon is having double bond, its hybridization is sp2. Remember, its hybridization is sp2. Its hybridization is sp3. What does that mean? That clearly indicates, have a look. This is having p orbital, this is having p orbital, but this is not having p orbital. What is conjugation? At least 3 adjacent positions must have 3 orbitals, parallel and with respect to each other. So can I say, In this ring, complete conjugation is absent. As complete conjugation is absent, this is non-aromatic species. Okay, what about this? This is sp2, that means p orbital is available. P orbital is available. This is also sp2 because this is having positive charge. That means p orbital is available. Can I say these three adjacent positions have three p orbitals parallel and within the same plane with respect to each other? That means conjugation is there, and that too within the complete ring. So this is complete cyclic conjugation. Now tell me, these two p orbitals overlap with respect to each other and forms a pi bond, and pi bond is having 2 electrons. That means here in these two orbitals 2 pi electrons are there, but here there will be no electron as it is empty. So can I say this is what we call complete cyclic conjugation is present? Have a look. Complete cyclic conjugation is present with 2 pi electrons. If you have complete cyclic conjugation and you have 2 pi electron, that means these 3 plus 4 and plus 2 pi, all the 4 conditions are fulfilled. Hence this is what we call aromatic compound with 2 pi electrons. I hope this is clear now. This is p orbital and p orbital. All are in conjugation. That means all these orbitals are conjugated orbitals. Now tell me, this conjugated orbital contains a negative charge, that means 2 pi electrons. These conjugated orbital contains a pi bond, means 2 pi electrons. That means complete cyclic conjugation is there, but it contains 4 pi electrons. Now have a look. Complete cyclic conjugation is there, but it's having 4 pi electron. That means it is anti-aromatic. So this compound is anti-aromatic. Now have a look. This is having p orbital, this is having p orbital, this is having p orbital. Complete cyclic conjugation is there. But how many pi electrons? One is of this pi bond is having 2 pi electron, and this is odd electron. 2 plus 1 is 3. That means complete cyclic conjugation is there, but it is having 3 pi electrons. Now if you are having complete cyclic conjugation and after that you are having 3 pi electron, that means this condition is not fulfilled, this condition is not fulfilled. That means all the 4 conditions are not fulfilled, hence this is not aromatic. All these 4 conditions are not fulfilled, hence this is not anti-aromatic, hence this is a non-aromatic species. Okay, now if structure is like this circle within the ring indicates complete cyclic conjugation. Now that means this structure already means that this is having complete cyclic conjugation. After that, this circle is within 3-membered ring. So as members of this ring are 3, so I will write 3. What is meant by positive charge? Positive charge means loss of electron. So I will minus 1, answer is 2. So this 2 gives me information about pi electrons. Now tell me, already this was complete cyclic conjugation with 2 pi electrons, hence this is aromatic with 2 pi electrons. Now here it is 3 plus 1. Why plus 1? Because negative charge means gain of electron. Answer is 4. So this compound is having 4 pi electrons. So complete cyclic conjugation with 4 pi electron. Answer is anti-aromatic. Okay. Now this is p orbital, and its p orbital is vacant because this is boron. So complete cyclic conjugation is there, but this is having vacant orbital. Here pi bond is there, so only 2 pi electrons. So this is aromatic with 2 pi electron. Whenever you have a structure like this, that double bond is within the ring. This is endocyclic double bond, and double bond outside the ring. This is exocyclic double bond. You simply move this pi electron towards more electronegative element and draw its resonating structure. Whenever you draw a resonating structure, look towards the ring only. When you look towards the ring only, this is the p orbital, this is p orbital, and this is p orbital. So complete cyclic conjugation is there, but this p orbital is empty. These p orbitals form pi bond, and that too is only 1 pi bond, means 2 pi electrons. Hence this is aromatic with 2 pi electrons. I hope you will simply try to solve these questions as well, and you will try to solve each and every one among them. But you have to consider only those pi electrons which are inside the ring, not outside the ring. Okay, so I hope you can simply tell me the answer up to these. After that, I will show these questions by myself, but as you all might be knowing that this is the month of Ramadan, and I have been fasting since whole day. So I want to take some food. For that, let me take once again a break, and we will meet at 7:30 sharp. So we will meet at 7:30 sharp, and after that I will explain these questions. So till then, take care. Thank you. Bye-bye. Welcome back, welcome back. Let me know if I'm audible and visible to everyone. Let me know in the chat box, please. If I'm audible and visible to everyone, let me know in the chat box. Let me know in the chat box. Quickly, quickly. Yeah. Am I audible and visible to everyone? Okay, now have a look. This is known as cyclooctatetraene, or we can simply write down as COT. COT always exists in the form of tub shape. It always exists in tub shape. So this is its structure, tub-shaped structure. And you know, if it's having a tub-shaped structure, that clearly indicates it is a non-planar species. And any species which is non-planar means that is non-aromatic. So COT is always non-aromatic because it does not exist like this. It exists in tub-shaped structure. Now, after that, this is known as 10-annuline. This is known as 10-annuline. What is meant by annuline? If you want, you can write down what is annuline. Annuline is completely conjugated monocyclic polyene containing even number of carbon atoms. Now, as this is a monocyclic structure, it contains 10 carbons and it's polyene, and that too conjugated polyene. So this is completely conjugated monocyclic polyene known as 10-annuline, this one. But remember, whenever you write down the number, so numbering is done in such a way that 1, 2, 3, 4 is this one. After that, this is 5, this is 6, this is 7, this is 8, and these are numbered at the end. So this is 9, this is having hydrogen, and this is 10, this is having hydrogen. Remember forever, hydrogen at 9 and hydrogen at 10, they are very close to each other. Hence, there will be hydrogen interactions or non-bonded hydrogen interactions, due to which there will be a repulsion, and due to that repulsion, carbon number 9 and carbon number 10 goes out of the plane. That means carbon number 9 is now not in plane with that of carbon 8 or carbon 1. Similarly, carbon 10 is not in plane with that of 5 or 4, which clearly indicates that there will be no conjugation now because carbon number 9 is in different plane, carbon 8 is in different plane, their orbitals are in different plane, they will not overlap now. Hence, because of this non-bonded hydrogen interactions taking place at carbon 9 and carbon 10, carbon number 9 and carbon number 10 becomes out of plane. So when they goes out of plane, their conjugation is not now completely cyclic conjugation. Hence, this 10-annuline becomes non-aromatic. So why this is non-aromatic? Because complete cyclic conjugation has been broken because of non-bonded hydrogen interactions taking place at carbon number 9 and carbon number 10. Now, after that, these structures, this structure, this structure, this structure, this structure, this structure, this, up to this, these are known as fused structures because between two rings, at least two carbons are common, two atoms are common between these two rings. I mean to say, whenever you are having fused rings, you have to see this long conjugated periphery. You have to consider long conjugated periphery. I mean to say, try to understand. Here it's p orbital, 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 and that too parallel and within the same plane. That means this is the longest path where conjugation is, considered. So this is longest conjugated path. This is longest conjugated periphery. Now, in this longest conjugated periphery, how many pi electrons are there? 2, 4, 6, 8, 10. That means complete cyclic conjugation is there, and that too with 10 pi electrons. Hence, this is aromatic with 10 pi electrons. Similarly, once again, longest conjugated periphery is this one. Longest conjugated periphery is this one. Have a look. This is longest conjugated periphery. In this 2, 4, 6, 8, 10, 12, 14. That means 1 complete cyclic conjugation, that too with 14 pi electrons. That means this is aromatic with 14 pi electrons. Now have a look towards this. This is having complete cyclic conjugation. That means longest conjugated periphery is this one. But how many electrons are there? 2, 4, 6 and 8. Or you can draw its resonating structure like this. You can write down like this. Now this is all clear. This is the longest conjugated path. How many pi electrons are there? This is 1 pi bond, means 2 pi electrons, 4, 6 and 8. So this is anti-aromatic because this is having complete cyclic conjugation but with 8 pi electrons. Hence, this is anti-aromatic. What about this? This is longest conjugated periphery. Longest conjugated periphery is this. How many pi electrons are there? 2, 4, 6, 8, 10. That means this is aromatic with 10 pi electrons. Have a look. This is longest conjugated periphery. This one, this one, this one, this one, this one, this one, and this one. Here 1 pi bond, 2 pi bond, 3 pi bond, 4 pi bond. That means 8 pi electrons and a lone pair. That means in total it's having 10 pi electrons. So this is aromatic with 10 pi electrons. This is known as azulene. One is 7-membered ring, another is 5-membered ring. Longest conjugated periphery is this one. And this is having 2, 4, 6, 8 and 10 pi electrons. That means once again it is aromatic with 10 pi electrons. Here, longest conjugated periphery. Here is no conjugation at all. So this is the longest conjugated periphery. This is the longest conjugated periphery. How many pi electrons are there? 6. So this is aromatic with 6 pi electrons. There is no conjugation, so you do not have to consider this. Now, what about this? This is known as pyrene. This is known as pyrene. Now have a look, have a look. This is pyrene. Now, this is longest conjugated periphery. This is longest conjugated periphery. This is longest conjugated periphery. You have to consider only longest conjugated periphery. These are 2 pi electrons, 2 pi electrons, 2 pi electrons, 2 pi electrons, 2 pi electrons. That means we have to see only peripheral pi bonds, not this one. This will not be considered. This pi bond is not considered. This is not considered because this is not within the longest conjugated periphery. So 2, 4, 6, 8, 10, 12, 14. So this is aromatic with 14 pi electrons. Now after that, these are isolated rings because one ring is joined with another ring by means of a single bond. For that, you simply remember this trick. If you are having one ring as aromatic, another as non-aromatic, overall molecule is aromatic. If one ring is aromatic, another is aromatic, overall molecule is aromatic. If one ring is aromatic, another is anti-aromatic, overall molecule is non-aromatic. Now, have a look. This ring is aromatic. This ring is non-aromatic. So, overall molecule is aromatic. This ring is aromatic. This ring is aromatic. Overall, this is aromatic in nature. Now, next, will be like this. This is known as ferrocene. This is a sandwich layer compound because between two cyclopentadienyl anion rings there is what we call iron. But these two rings are isolated. So this is aromatic ring, this is aromatic ring. Overall, this is aromatic in nature. Now have a look. If we talk about these rings are separated together by means of a double bond. These are joined by means of a double bond. Now, this double bond will be either shifted towards this direction or towards this direction. So, we will be having these two types of structures. Have a look. One is 3-membered ring, another 5-membered ring, double bond. Endocyclic double bonds are as such, but this exocyclic double bond, if I move pi electrons towards like this, this will become negative charge and this a positive charged species. So positive and negative, or it will be like this. It will be like this. Now have a look. This will be positive, this will be negative. But do you know this is having p orbital, p orbital, p orbital. So cyclic conjugation, complete cyclic conjugation is there with 2 pi electrons. So this is aromatic ring. What about this? 2 pi electrons, 2 pi electrons, 2 pi electrons and complete cyclic conjugation, that means 6 pi electrons. So this is aromatic. Aromatic, that means it becomes overall aromatic. What about this? This is having 2 pi electrons and 2 pi electrons, complete cyclic conjugation with 4 pi electron, that means this is anti-aromatic. And this is what we call this is also complete cyclic conjugation and 4 pi electron anti-aromatic, which means this is anti-aromatic. Now tell me, aromatic species are highly stable. They are highly stable. And anti-aromatic species are highly unstable. Now tell me, this will follow which path? This will follow this path, this will not follow this path. That means this generally exists in this form, hence this is aromatic in nature. Similarly, here, if I draw its structures will be like this. One structure will be a 7-membered ring. One structure will be a 7-membered ring joined to a 5-membered ring, in which this is having double bond, double bond, double bond, double bond, double bond, and this is having positive and this is having negative. Another will be a 7-membered ring. Another will be having a 7-membered ring joined to a 5-membered ring, but this will be having positive and this will be having negative. Now this ring is anti-aromatic, this is anti-aromatic, overall this is anti-aromatic, and this is aromatic, this is aromatic, overall this is aromatic. So this will follow this one. This will not exist in this form because this is highly unstable. So this won't to be aromatic, hence this is aromatic in nature. But if we talk about this, one is a 5-membered ring joined to a 5-membered ring. So double bond, similarly double bond, this will be having positive and this will be having negative. Please try to understand, For 5-membered ring with a positive charge, 5-membered ring with a negative charge. So this is anti-aromatic and this is what we call anti-aromatic and this is aromatic. Overall, this is anti-aromatic and this is aromatic. Overall, it becomes non-aromatic. This is aromatic and this is anti-aromatic. Overall, this becomes non-aromatic. So I mean to say this will exist either this or this, hence this is non-aromatic in nature. I hope this is clear to everyone. After that, we are having another term, and that is known as resonance energy. Remember, what is resonance energy? Resonance energy means it is the amount of energy decreased due to delocalization. Amount of energy decreased due to delocalization. I hope you know what delocalization is. Delocalization means partial overlap of orbitals. Because of that partial overlap of orbital, system needs energy. That means it uses its energy. Hence, system's energy will be decreased. So, it is the amount of energy decreased due to delocalization and is also known as delocalization energy. And is also known as delocalization energy or resonance stabilization energy. So resonance energy is also known as delocalization energy or resonance stabilization energy. Remember, this resonance energy can be calculated as energy of resonance hybrid minus energy of most stable resonating structure. But we know that this is the resonating structure. There will be no delocalization because bonding is localized. But this is resonance hybrid. This is the actual structure or the true structure where delocalization occurs. That clearly indicates its energy will be decreased as compared to this. So this will be having lesser energy as compared to this. If this is having lesser energy as compared to this, so can I say less minus more, value will be always negative. So resonance energy is always having negative value. But remember, negative value of resonance energy does not mean resonance energy is exothermic in nature, because it is not the amount of energy which has been lost. So this is not exothermic. It does not mean that it is exothermic, but it clearly indicates how much energetic most stable resonating structure is than resonance hybrid, or how much stable resonance hybrid is compared to most stable resonating structure. So that amount of energy which will be decreased due to delocalization, remember, is known as resonance energy or delocalization energy, or that energy is known as resonance stabilization energy. And it can be calculated with the help of this formula, that resonance energy of any species is equal to energy of resonance hybrid of that species minus energy of most canonical or most stable resonating structure of that. But remember, this value always comes out to be negative, but that does not mean that it is exothermic. That clearly indicates that how much energetic is this as compared to this, and we can simply say, or how much stable is this as compared to this, because this is less energetic means this is more stable than that. Now, remember forever, next point is like this. Resonance hybrid is always more stable than even most stable resonating structure due to delocalization. Now listen carefully. We know that delocalization takes place in resonance hybrid. It does not take place in what we call most stable resonating structure. Hence, resonance hybrid, delocalization takes place in resonance hybrid. So we can say that energy of resonance hybrid is decreased. If energy of resonance hybrid is decreased, it becomes less energetic as compared to this. When this becomes less energetic, that means it becomes more stable as compared to most stable resonating structure. Now, have a look. if we are having a graph like this, say for example, here we will say that this is energy is increasing like this, and I will simply use structure like this. Let us suppose this is resonance hybrid, and let us suppose this is most canonical resonating structure or most stable resonance hybrid. This is resonance hybrid and this is most stable resonating structure. You can see this is having less energy and this is having more energy. Why resonance hybrid is having less energy? It's having less energy due to delocalization, because due to delocalization there will be decrease in energy, hence this will be always less energetic as compared to most stable resonating structure. So here this difference is known as what we call resonance energy. Say for example, this is compound 1. So this is resonance energy of compound 1. Now, if I draw another graph like this, and for example, this is the resonance hybrid and this is the most stable canonical structure. Suppose this is the resonance hybrid and this is the most stable resonating structure. Let us suppose this is compound 2. Now tell me, this difference is known as resonance energy of 2. Tell me, can I say by both these graphs it's clear that resonance energy of 1 is greater than resonance energy of 2. Resonance energy of compound 1 is greater than resonance energy of 2. What does that mean? That means compound 1 will will decrease. That means in case of compound 1, there will be more decrease of energy due to delocalization as compared to this. If resonance energy of 1 is greater than resonance energy of 2, that clearly indicates that stability order will be like this. Stability order will be like this. Compound 1 will be more stable than compound 2. Why? Because we know that stability of any stability due to resonance sorry so due to resonance is directly proportional to resonance energy. Now listen carefully. Why? Because more the resonance energy, more will be the energy which has been decreased due to delocalization. If compound 1 is having more resonance energy, that means in compound 1 there will be more decrease in energy. That means compound 1 becomes less energetic, and any species which is less energetic is more stable. So remember, whenever resonance energy is more, that species is having less energy. If that species is having less energy, that species is becoming more stable. That's why stability due to resonance is directly proportional to resonance energy. So more the resonance energy, more will be the stability. More the resonance energy, less will be the energy, because energy has been decreased due to delocalization. I hope this is clear to everyone. Now, here are few questions based on resonating structures. Now, have a look. A, B, C, D. These are the resonating structures of formic acid. Do you know what is formic acid? Formic acid is HCOOH. Formic acid is HCOOH. So this is formic acid. So this A, B, C and D, these are the 4 resonating structures of formic acid. Now we have to say that what is B? What is this B? We have to choose among these. Now have a look. From this figure, it is clear that A is less energetic than B. B is less energetic than C. C is less energetic than B. That means A is more stable than B, than C, than D. Now have a look. So this is the energy. This is not resonance energy. This is energy. This is having least energy. Least energy means more stable. After that, B is more stable. After that, C is more stable. After that, D is more stable. That means which is B? B is among these which is having stability at position number 2nd. Now, these are resonating structures. Remember, Neutral resonating structure is more stable. That means resonating structure number 1 is more stable because this is neutral. After that, more number of pi bonds, that means 3. After that, we know these are having, all the atoms do not have complete octet, but positive charge is present on carbon, positive charge is present on oxygen. That means 4 is more stable as compared to 2. So this is the stability order among 1, 2, 3 and 4. Now listen, this is the stability order. So can I say 1 is the most stable? That means 1 will be least energetic. That means this is 1. This is 1. After that, can I say this is 3? Can I say this is 3? Can I say after that this should be 4? After that this should be 2. So our question is B means this one. B is 3. That means this is our correct option or correct answer. I hope this is clear to everyone. Now, here A and B are resonating structures of A and B. That means there are 2 resonating structures. So first of all, we should draw the resonating structures of each and here. Now, this is the resonating structure of this. Now have a look. This is the resonating structure. This is the resonating structure of first one. This is the resonating structure of second one. Now this is the resonating structure of second. This is the resonating structure of third. All these options are having 2 resonating structures like this. CH3, CO negative, double bond NH2 with a positive charge. But can I say this is neutral? This is charged. This is more stable. This is less stable. If this is more stable, this should become less energetic as compared to this. So both do not have same energy. So A and B are having same energy. So this is not the option. What about last one? This is more stable as compared to this. That means they do not have same energy. So A and B, these are not A and B. What about this one? This is neutral, this is charged. So these are having different energies. What about this? These are equally stable. That means they are having same energies. If they are having same energies, both are present at same energy level. So A and B are resonating structures of what? A and B are resonating structures of this CH3, COO negative. I hope this is clear to everyone. Now after that, after resonance energy, there are a few questions which are based on compare resonance energy. Let me tell you. Resonance energy means stability. And stability due to resonance means extent of resonance. Now have a look. Now here, conjugate positions are 1, 2 and 3. Here conjugate positions are 1, then it's 2, then 3, then 4. Here conjugate positions are 1, this is 2, this is 3, and this is 4. So more the number of conjugate positions, more will be the resonance. More the resonance, more will be the resonance energy. So this is having least resonance energy. After that, these two are having more resonance energy than this, but here it is pi bond, pi electrons which will take part in resonance. Here it's a lone pair of electron which will take part in resonance. Remember, energy of a delocalized electron is directly proportional to extent of resonance, or extent of resonance is directly proportional to energy of delocalized electrons. We know lone pair is having more energy as compared to pi bond, so this is having more resonance. So the answer is 3 greater than 2 greater than 1. So this is the answer of question number 1. After that, now this is oxygen, more electronegative. This is nitrogen, less electronegative. Remember, less electronegative, if takes part in resonance, its resonance is more. So 2 is having more resonance than 1. Hence 2 is having more resonance energy as compared to 1. Now this is anti-aromatic. This is non-aromatic. We know non-aromatic species are more stable than anti-aromatic species. That clearly indicates resonance energy of 2 will be more than resonance energy of 1, because more the stability, more will be the resonance energy. Now, this is aromatic and this is non-aromatic. Aromatic species are more stable than non-aromatic, so we can write 1 greater than 2, because more stability, more resonance energy. Now, have a look over here. Now, as you can see that conjugate positions are more in this, so it is 3, then 2, then 1. But if the question was like this, resonance energy per benzene ring. Say for example, question was like this, resonance energy per benzene ring. How many pi bonds? Please try to understand. How many pi bonds are there? How many pi electrons are there? 6. But this structure, this can be like this. Have a look. It can be like this as well. It can be like this as well. So these pi electrons, please try to understand, these pi electrons are basically of this ring as well as this ring. That means these 2 pi electrons are shared between 2 rings. Now, how many pi electrons are here? Please try to understand. Please try to understand. That means in total 10 pi electrons are between 2 rings. That means one ring is having 5 pi electron, another is having 5 pi electron. This will be having 6 pi electron. Here one ring is having 5 pi electrons. Now, total 2, 4, 6, 8, 10, 12, 14. 14 pi electrons are present in 3 rings. That means one ring will be having 14 divided by 3. That comes out to be 3 4s are 12. That means it is 4.6. Now tell me, this one ring is having 6 pi electrons. This one ring is having 5 pi electrons, and this one ring is having less than 5 pi electrons. So where pi electrons is more the pi electron, more will be the resonance. So resonance per benzene ring will be 1 greater than 2 greater than 3. So if the question is resonance per benzene ring, answer is 1, 2, 3. But if the question is not per benzene ring, overall resonance, then it is 3, 2, and 1. Now have a look. Here, conjugation is there between 2 atoms. Here, conjugation is between 3 atoms. This is having equivalent resonance. This is having equivalent resonance. But this is having non-equivalent resonance. So, equivalent resonance is more. But among these, equivalent resonance is present in this and this. But this is having more conjugate positions. So, first of all, it is 2, after 1, and then it is 3. Why 2 and 1? Are having more resonance energy? Because these are having equivalent resonance, that is having non-equivalent resonance. Now, have a look. These 2 are resonating structures. Whenever you have to find out the stability of resonating structures, here we can use a rule, and that is known as Fry's rule. It says, Fry's rule says, a resonating structure which contains more benzenoid rings resonating structure which contains more benzenoid rings is more stable. Now have a look. This is one ring and it contains what we call 2, 4, and 6 pi electron, and it's like that of benzene. But this ring, you are having, have a look, pi bond and pi bond. This is not like that of benzene. But what about this? What about this? Have a look. Double, single, double, single, double. That means this is exactly like that of benzene resonating structure. Similarly, this double bond can be counted over here as well as here. So because they are 2, 4, and 6, that means it's like double, single, double, single, double, single. So it's once again like that of benzene-like structure. So this is benzene-like ring, so benzenoid ring. This is benzene-like ring, benzenoid ring. That means there are 2 benzenoid rings, but here it's only 1 benzenoid ring. So structure in which more benzenoid rings are there is more stable. So the stability order is 2 greater than 1. Is this clear to everyone? Let me know in the chat box so that we can move forwards and take another question, that is hyperconjugation. But before that, we will before starting hyperconjugation, let me know in the chat that is everything clear till now. Come on, let me know. Is everything clear till now? Let me know in the chats. Let me know in the chats. Yes, sir. Thank you, thank you, thank you. So, hyperconjugation, it's also known as sigma delocalization or no bond resonance. or Baker-Nathan effect. Or this is also known as secondary resonance. Sometimes it's also known as extension of resonance. Sometimes it's known as extensive conjugation. Sometimes it's also known as sigma p overlap. Sometimes it's also known as sp3p overlap. Sometimes it's also known as sigma pi star overlap, antibonding pi orbital. Now, it's sometimes also known as reversed inductive effect. Now, first of all, question is, where can we say that compound shows hyperconjugation or hyperconjugation is present in a compound? For that, what are the conditions? Remember, conditions are like this. We must have sp hybridized carbon, or generally we are having sp2 hybridized carbon. We must have sp hybridized carbon, to which this can be of a triple bond, to which there must be alkyl group containing at least one hydrogen. An alkyl group containing one hydrogen is sp3 hybridized. So with respect to this carbon, this is adjacent, so we can simply say alpha carbon should be sp3, and to that there must be at least one hydrogen, or there may be carbon should be, say sp2. This sp2 carbon can be of either carbon-carbon double bond, it can be of what we call a phenyl ring or a benzene ring, it can be of carbocation, it can be of carbon free radical. So whenever this carbon, which is sp2, to that there must be one alkyl group, that means whose carbon is sp3 hybridized. So with respect to this carbon is alpha, and there must be one hydrogen. So whenever your compound is like this or this, you will simply say there exists a phenomenon, and that phenomenon is known as hyperconjugation. What hyperconjugation is? I have not explained what is hyperconjugation yet, but I have simply said that when is hyperconjugation present. Now, tell me, is hyperconjugation present or not? Have a look. If hyperconjugation is present, tell me yes or no. Is hyperconjugation present? Yes. Why? Because first of all, here is sp2 hybridized carbon. To that sp2 hybridized carbon, there is sp3 hybridized carbon. So we can call this carbon as alpha carbon. And this alpha carbon contains 3 alpha hydrogens. So this is having 3 alpha hydrogens. Any hydrogens present at alpha carbon are 3. So which carbon is alpha? Carbon should be sp3 and should be attached to either sp2 or sp hybridized carbon. So this is having 3 alpha hydrogens, which mean it shows hyperconjugation. For hyperconjugation, we need at least one hydrogen attached to sp3 hybridized carbon, and that too adjacent to either sp or adjacent to sp2 hybridized carbon. Now, second example is like this. Tell me how many alpha hydrogens are present in this. How many alpha hydrogens are present in this? Now, this is sp2. To this sp2, which is directly attached, this one, and this is sp3, that means this becomes alpha carbon. So there is no hydrogen attached to this alpha carbon. This is sp3, but this is not alpha. Alpha is adjacent to sp2 or adjacent to sp. So there is 0 alpha hydrogen. As there is no alpha hydrogen, there will be no hyperconjugation at all. Now, What about this? How many alpha hydrogens are there? How many alpha hydrogens are there? Now have a look. As carbon is carbon-free radical, that means it's sp2, and to this sp2, this carbon is sp3. As this carbon is sp3, hence this is our alpha carbon. This is having one hydrogen, so this is having one alpha hydrogen. So as one alpha hydrogen is present, so it will show a phenomenon known as hyperconjugation. What about this? What about this? This is our sp2 hybridized carbon. Ring carbon is sp2. Now to this sp2, this is sp3, and this becomes our alpha carbon. And this alpha carbon is having 3 hydrogens. So this is having 3 alpha hydrogens. So simply this shows hyperconjugation. What about this? What about this? My dear students, look towards the board. What about this? As this is sp2 hybridized carbon, to this becomes alpha because this is sp3 hybridized. Now, do you know this is neutral species, and neutral species forms 4 bonds, but visible are only 3. That means hidden bond is with hydrogen. That means this is having 1 alpha hydrogen, and that hydrogen is at here. Now, this is the hydrogen, so 1 alpha hydrogen is present, hence hyperconjugation is present. Now, what about this? What about this? How many alpha hydrogens are there? First of all, this is sp2 hybridized carbon. To this is alpha and this is alpha. Adjacent, because this is sp3, this is also sp3. So you have to find out adjacent sp3 hybridized carbon to what we call sp2. This is alpha. So here are 2 hydrogens, here is 1 hydrogen. In total, there are 3 alpha hydrogens. Hence, it can show what we call hyperconjugation. Now, tell me, how many alpha hydrogens are present in this? I will be waiting for this. I will be waiting for your answer for this, and let me know how many alpha hydrogens are present in this. Let me know in the chat box. How many alpha hydrogens are present in this? Let me know in the chat box. Come on, quickly. Let me know in the chat box quickly. How many alpha hydrogens are present? How many alpha hydrogens are present in this? Let me know in the chat box quickly. Come on. Let me know in the chat box quickly. How many alpha hydrogens are present in this? How many alpha hydrogens are present in this? Come on, come on, come on, come on. Yes, you can tell me the answer. You can simply write down how many alpha hydrogens are present in this. What are alpha hydrogens? Alpha hydrogens, come on. Alpha hydrogen means hydrogens present at alpha carbon. Okay. Now, have a look. Have a look, because that answer is not correct. Now, this is sp2 hybridized carbon. This is sp3, so this becomes alpha. This is sp3, so this becomes alpha. This is sp3, so this becomes alpha. How many hydrogens are there? 3. And here, 2. Here, 2. That means this is having 7 alpha hydrogens. As at least 1 alpha hydrogen, if at least 1 alpha hydrogen is present. Yes, exactly. There are 7 alpha hydrogens. At least, if at least 1 alpha hydrogen is present, hyperconjugation is present. So this is having 7 alpha hydrogens. Now, one more example. Tell me the answer. One more example. You have to write down the answer. How many alpha hydrogens are present in this? How many alpha hydrogens are present in this? How many alpha hydrogens are present in this? Tell me, how many alpha hydrogens are present in this structure? Come on, come on, come on, come on. Let me know in the chat box. Come on. How many alpha hydrogens are present in this structure? Come on. Let me know in the chats. Let me know in the chats quickly. How many? This structure. This structure. This structure. Okay. Now have a look. Yes, exactly. Right answer. Exactly right answer at the rate of Vishwas. Exactly. Serene. Exactly. Now have a look. This is sp2. This is sp3. sp3 attached to sp2 is alpha. sp3 attached to sp2 is alpha. This is having 2 hydrogen. This is having 2 hydrogen. In total, this is having 4 alpha hydrogen. Hence, hyperconjugation is present in this. So, what actually hyperconjugation is? Let me write down the definition of hyperconjugation as per NCERT textbook is concerned. That is, it is delocalization. Hyperconjugation is delocalization. This is definition of hyperconjugation. It is delocalization of sigma electrons of CH sigma bond of alkyl group attached to an unsaturated system or to an atom with unshared p orbital. Now have a look. So it is delocalization of sigma electron of CH sigma bond. Have a look. CH sigma bond of alkyl group. And this CH sigma bond of alkyl group should be attached to an unsaturated system. That means either triple bond or double bond or benzene ring, unsaturated system. Or this alkyl group, which is having at least one CH sigma bond, it should be attached to either carbocation or carbon free radical, because this is having unshared p orbital or this is having unshared p orbital. Now, I hope this is clear to everyone. Now, have a look. If we are having a carbon with a positive charge, we can simply say it is this orbital which overlaps with CH sigma bond. This is CH sigma bond, that means this is sigma orbital. This overlaps with this one. It simply overlaps like this. So it is sigma orbital of CH sigma bond of alkyl group which overlaps with empty p orbital or p orbital of sp2 hybridized carbon. So this is what we call hyperconjugation. Now, what is hyperconjugation? It is simply delocalization. Have a look. It is simply delocalization of sigma electrons. But sigma electrons should be of CH sigma bond. And this CH sigma bond should be of alkyl group. And this should be attached either to an atom with unshared p orbital, or this should be attached to an atom which is of unsaturated system. Now, what is meant by delocalization of sigma electron? Have a look. Delocalization of sigma electron means delocalization of sigma electrons mean partial overlap of p orbital of sp2 hybrid orbital or sometimes it may be sp hybrid orbital with sigma orbital of adjacent CH sigma bond of alkyl group in such a way so that sigma electron density remains constant. So which type of orbitals overlap during hyperconjugation? It is p orbital of either sp2 or sp hybridized carbon, which overlaps with sigma orbital of adjacent CH sigma bond, but that CH sigma bond should be of alkyl group in such a way that sigma electron density remains same. What is meant by that? Have a look. If you are having a structure like this, HCH, H, and then you are having CH2 positive. Now, this orbital, empty orbital, overlaps with this sigma orbital, and they will simply overlap and result in the formation of a bond. That means another structure will be like this. Another structure will be like this. Here will be a double bond, and there will be no bond over here, so this hydrogen will be without electron. But do you know this is sigma bond? Remember forever. This is sigma bond, and about the sigma bond, rotation is slightly free. That means the amount of energy what we need is already available in room temperature. That means if this is overlapping with this, when it rotates because of free rotation, this orbital can also overlap. This orbital can also overlap. If this is CH bond, this is CH bond. Now, have a look. Here we are having 3 CH bonds. If this will overlap, this can also overlap after that, but not at the same time. So another structure can be like this. If this overlaps, there will be no bond over here. Then here will be CHH double bond CH2. Another possibility will be like this. Another possibility will be like this. Another possibility will be if this bond overlaps. If this CH bond takes part in overlapping or delocalization, then another structure will be this. But none of them is the actual structure. None of them is the actual structure, but actual structure can be drawn with the help of all these structures. So with the help of all these structures, we can say this is sometimes single, sometimes there is no bond. So this is partial single bond. Similarly, this is partial single bond. Similarly, this is partial single bond. What about this? This is partial double bond. Now tell me. This carbon is sometimes positively charged, sometimes what we call neutral. That means this is partial positive. Similarly, this hydrogen is sometimes positive, sometimes neutral. This is partial positive charge. Similarly, this hydrogen is sometimes positive, sometimes neutral, means partial positive charge. Similarly, this hydrogen is sometimes positive, sometimes neutral, means partial positive charge. So this is actually what we call hyperconjugation. Now, what will happen due to hyperconjugation? This positive charge is now dispersed. This positive charge is now dispersed. Remember, more the dispersion of charge, whether it is positive, more the dispersion of negative charge, more the dispersion of positive charge, more the dispersion of electron deficient sites, more the dispersion of electron rich sites. Remember, more the dispersion, more will be the stability. So hyperconjugation basically increases stability. So what is hyperconjugation? Have a look. Overlap has been taken place in such a way so that electron density over here, here, and here, sigma electron density is uniform throughout here, here, and here. Sigma electron is uniform. So wherever CH orbital takes part in overlapping, everywhere, if this is the CH, this is CH, this is CH, if all these CH bonds take part in hybridization, their sigma electron density will be same. This is known as what we call hyperconjugation. And hyperconjugation increases the stability. These are known as hyperconjugative structures. None of them actually undergoes hyperconjugation, but with the help of these, we can draw a hyperconjugative structure or a true structure of hyperconjugation. Now, similarly, if you are having a structure like this, can I say this is sp2 hybridized carbon, it's p orbital, and sigma orbital of this adjacent CH sigma bond of alkyl group take part in overlapping. So here I will show half-headed arrow or fish hook arrow. So the bond formation will be like this. And it's having one electron because only one electron is moved towards this. Similarly, this bond can also overlap, so it will be like this. It can be also like this. or if this will take part in overlapping, then it will be like this. So with the help of all these structures, what will be the real structure? Real structure will be this. And this is the structure where basically hyperconjugation takes place. And this is having partial odd electron, partial odd electron, partial odd electron, partial odd electron. Have a look, have a look. So overlapping has been done in such a way, overlapping of this sigma orbital and this p orbital is done in such a way that every sigma bond is having same electron density throughout. I hope this is clear to everyone. Now, here one sigma orbital and another p orbital takes part in overlapping, sigma and p, sigma and p. So these two types are simply known as sigma p hyperconjugation, yeah, sigma p overlap, because it's sigma orbital taking overlapping with p orbital, sigma with p orbital. So this is sigma p overlap. So what is hyperconjugation? I hope this is clear to everyone. It's simply delocalization of sigma electron with, but sigma electron of what? Sigma electron of CH bond of alkyl group with unsaturated, with an atom of unsaturated system, that means double bond or a triple bond, or with an atom with unshared p orbital, that means either carbocation or carbon free radical. But what is this delocalization? This means this is overlapping between these two in such a way that sigma electron density remains constant, remains same throughout. Due to this delocalization or due to this overlapping, you can see there will be dispersion of charge or dispersion of electron deficient site, hence it increases the stability. Now, next is, if you are having structure like this, if you are having a structure like this, then it can overlap like this, then it will be pi electrons will move towards this. So our next structure will be HCH. Here it will be a double bond, then CH2 having a negative charge, and this will be having a positive charge. Now listen carefully, my dear students, listen carefully. After that, if this hydrogen takes part in overlapping, then it will be like this. Then it will be like this. And another possibility is that this hydrogen can also overlap. So it will be like this. What will be the hybrid of this? Hybrid will be partial sigma bond, partial sigma bond. After that, this is partial double bond. After that, this is partial double bond. So it will be like this. Now, have a look. This is partial sigma bond. This is partial double bond, because sometimes single, sometimes double, sometimes single. So partial double bond. This is having partial positive charge, partial positive charge, partial positive charge. And this is always neutral. This carbon is always neutral, and this carbon is having partial negative charge. Now, this type of hyperconjugation is simply known as sigma pi hyperconjugation. So can I say there are two types of hyperconjugation? So can I say types of hyperconjugation? If I write types of hyperconjugation, if I say what is hyperconjugation types, actually hyperconjugation is nothing but it is an extension to resonance. In case of resonance, there were two types. One was pi pi, here it is sigma pi. Instead of pi, it's sigma. Another was pi p, here instead of pi, it is sigma p. And in this sigma p, there are two, one is sigma vacant orbital, and another is sigma odd electron. Or instead of vacant orbital, you can write down positive charge, which I have already shown to you. Now have a look. Sigma positive or sigma vacant orbital, and this is sigma odd electron known as sigma p. That means sigma p is having two types. Another is sigma, and this is having a pi bond with this. That's why sigma pi hyperconjugation. So after that, remember this point. according to Muller and Mulliken, hyperconjugation is of two types, viz. Number one, sacrificial hyperconjugation. Sacrificial hyperconjugation. Remember, it is that hyperconjugation in which charge separation takes place. That means positive and negative charges will be separated. So charge separation takes place. For example, sigma pi hyperconjugation. Have a look. Have a look. Now, this is sigma pi hyperconjugation. You can see these are the positive charge, this is negative charge, so there is charge separation. Now, that hyperconjugation in which charge separation takes place in a hybrid, that is simply known as what we call sacrificial hyperconjugation. And why sacrificial hyperconjugation is the name of this compound? If you can count total number of sigma bonds, this is 1, 2, 3, 4, with hydrogen 1, 5, 6 sigma bond, then this is pi bond 7, 8, 9. That means total number of bonds, sigma plus pi, are 9 over here. But if you count this 1, 2, 3, 4, with hydrogen it's 1, 5, 6, 7 and 8. Here are 9, here are 8. That means during this conjugation, bonds have been sacrificed. That's why this is known as sacrificial hyperconjugation. Another type is isovalent hyperconjugation. Another type is isovalent hyperconjugation. Another type is isovalent hyperconjugation. It is simply that hyperconjugation. It is that hyperconjugation in which no charge separation takes place. In which no charge separation takes place. No charge separation takes place. For example, sigma p, I mean say sigma vacant orbital and sigma odd electron. Have a look. So these all positive charges are there. That means only one type of charge is present. So there is no another charge. So there will be no charge separation. Similarly, there is no charge separation. So sigma p is what we call example of isovalent hyperconjugation according to Muller and Mulliken. Now, why this is isovalent? Iso means same, valent means valency. You can count what we call bonds. 1, 2, 3, 4 and 2 bonds. 6 bonds are there. 1, 2, 3, 4, 5, 6 bonds are there. That means they are isovalent. Similarly, 1, 2, 3, 4 and then 2 bonds, 6 bonds, 1, 2, 3, 4, 5, 6. There is what we call valency remains same. That means they are isovalent in nature. So these are types of hyperconjugation. Now, after that, you must know this one. In case of aliphatic species, I mean say open chain structures, number of hyperconjugative structures, number of hyperconjugative structures which involve CH bonds is always equal to number of alpha hydrogens. Always equal to number of alpha hydrogens. Have a look. Have a look. Have a look, dear students. Have a look. Now, if I say how many hyperconjugated structures are possible for this? 1, 2, and 3. Why 3? Because this is having 3 alpha hydrogens. So this is having 3 alpha hydrogens. So 1, 2, and 3. In total will be number of alpha hydrogen plus 1. What is 1? 1 is this itself. Now, similarly, how many possible hyperconjugated structures are possible for this? That means 1, 2, and 3. That means equal to number of alpha hydrogens. Similarly, how many hyperconjugated structures are possible for this structure? 1, 2, and 3. That means equal to number of alpha hydrogens. I hope this is clear to all. I hope this is clear to all. Now, after that, you must remember this point. Now, have a look. If I write tertiary alkyl group, after that, I will write secondary alkyl group. After that, I will write primary alkyl group. And after that, I will write methyl group. What is their plus I order? If you remember, their plus I order was like this. Their plus I order was like this. If you remember, their plus I order was like this. Tertiary was having more plus I power than secondary. Secondary was having more plus I power than ethyl. Ethyl was having more plus I power than methyl. I hope this is clear to everyone. Now, if similar tertiary alkyl group is attached to, say for example, sp or sp2 hybridized carbon, or a carbocation, or a carbon free radical, say for example benzene, it's sp2 hybridized. Then similarly, this secondary alkyl group is attached to, say for example benzene ring, that means to an sp2 hybridized carbon. So for that, with respect to this sp2, this becomes alpha carbon. And similarly, if same this ethyl group is attached to benzene ring, so this becomes alpha. And if this methyl is attached to benzene ring, this becomes alpha. Now tell me, whenever these types of alkyl groups are attached to benzene ring, there occurs a phenomenon known as what we call hyperconjugation. And according to hyperconjugation, what will be the hyperconjugation order? What will be the H order? Or I can write down what will be the plus H order. Plus H means what will be their electron donating order because of hyperconjugation towards ring. This will donate electron towards ring, this will overlap, and this will increase electron density of the ring like this, like this. Now have a look. Have a look. Have a look. Now, this donates electron towards conjugated system, donates electrons and increases electron density. If our conjugated system is now benzene, what will happen to benzene? Benzene's electron density will be increased at ortho and para, but due to hyperconjugation. Because of 3 alpha hydrogens here, because of 2 alpha hydrogens, because of 1 alpha hydrogen, there is no alpha hydrogen. So, tell me, among tertiary alkyl, secondary alkyl, primary alkyl and methyl, which alkyl group donates electrons more because of hyperconjugation? It is this one, because of more alpha hydrogens than this, then this. Can I say that here this plus I order is now reversed because of hyperconjugation? That's why sometimes hyperconjugation is also known as reversed hyperconjugation. I hope this is clear to everyone. Okay. Okay, dear. Now, after that, it's application of hyperconjugation. It's application of hyperconjugation. Application number 1. Stability of carbocation. Number second, stability of carbon free radical. Number third, stability of alkene. Remember, it's directly proportional to extent of hyperconjugation. More the hyperconjugation, more will be the stability, because more the hyperconjugation, more will be the delocalization. More the delocalization, more energy will be decreased due to delocalization, and more energy will be decreased. That means system becomes less energetic, hence more stable. Now, have a look. These, can be understood with the help of few questions or examples. Now, compare the stability. Question is like this. Compare the stability. If I write question number 1 like this, CH3, CH3, CH3 with a positive charge. Number second is like CH3, CH3 and then H with a positive charge. Third is like CH3, HH with a positive charge, and fourth is HCHH with a positive charge. Now have a look. We know carbon having positive charge is sp2 hybridized, and to that this is sp3 hybridized carbon which is directly attached. So whenever sp3 hybridized carbon is directly attached to sp2, this becomes alpha, this is alpha, this is alpha. So at this alpha carbon there are 3 hydrogens, 3 hydrogens, 3 hydrogens. That means in total this structure is having 9 alpha hydrogens. To this carbocation, to this positively charged carbon which is sp2, which carbon is attached? This is not the carbon. This and this, these two carbons are attached, and these two are sp3 hybridized carbon, and both becomes alpha carbon. So this is having 3 hydrogens, this is having 3 hydrogens. In total, this is having 6 hydrogens. Are you getting me? Now, this is the carbon which is alpha because sp3 attached to sp2. So this is having 3 alpha hydrogens. There is no carbon attached to carbocation. That means there is no alpha carbon and there will be no alpha hydrogen. Now tell me, we have to find out the stability. Can I say that more the number of alpha hydrogens, more will be the hyperconjugation, and more the hyperconjugation, more will be the stability. So what will be the stability order? Therefore, stability order will be simply 1 greater than 2 greater than 3 greater than 4. I hope this is clear. Now, after that, if I write like this, CH3, 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 and this is a radical. Number second, CH3, CH3, here is a radical. Then CH3, CH2, this is the radical, and after that CH3. Now tell me the answer for this. Now have a look. This is sp2 hybridized carbon, and to this sp2 hybridized carbon, this carbon is sp3 and is directly attached to it. This carbon is sp3 and directly attached to sp2. Carbon sp3 attached to sp2 is alpha carbon. Similarly, this is alpha carbon, this is alpha carbon, this is alpha carbon, there is no alpha carbon. So here are 9 alpha hydrogens, here are 6 alpha hydrogens, here alpha hydrogens are 3, and there will be no alpha hydrogen. So what will be the stability order? Stability order will be 1, 2, 3, and 4. So simply this will be the stability order. Why? Because more the number of alpha hydrogens, more will be hyperconjugation and more will be the stability according to hyperconjugation. Now, next is, if we are having alkene like this, CH2 double bond CH2. Second alkene is like this, CH3 single bond CH double bond CH2. Third alkene is like CH3 CH double bond CH single bond CH3. Now have a look. Can I say simply that this is this is sp2 hybridized carbon, this is sp2, there is no sp3 hybridized carbon, so there is no alpha carbon. This is sp3 hybridized carbon attached to sp2, so this is alpha. This is sp3 attached directly to sp2, hence this is alpha. This is sp3 directly attached to sp2, hence this is alpha. So this is having 0 alpha hydrogen, this is having 3 alpha hydrogens, this is having 6 alpha hydrogens in total. So more the number of alpha hydrogens, more will be the stability. So the answer is 3, 2, and 1, because third option is having more alpha hydrogen, means more hyperconjugation. Now, fourth application is heat of hydrogenation. You have already studied this in physical chemistry. If not, let me tell you, heat of hydrogenation means amount of heat lost, amount of heat released, amount of heat evolved when 1 mole of hydrogen is added to an unsaturated species to form that into a saturated one. Say for example, you are having CH2 double bond CH2. Suppose you are having CH2 double bond CH2 and we want to convert this into CH3, single bond CH3. That means this unsaturated has been converted to saturated by addition of 1 mole of hydrogen, H here and H here. That means H2 means 1 mole of hydrogen has been added so as to convert 1 mole of alkene to 1 mole of alkane. At that time, some heat will be evolved and this heat is known as what we call heat of hydrogenation. Remember, for heat of hydrogenation, in organic chemistry, heat of hydrogenation is directly proportional to number of pi bonds. It is directly proportional to number of pi bonds. But if pi bonds are same, if pi bonds are same, then remember, heat of hydrogenation is inversely proportional to stability. More stable structures have lesser heat of hydrogenation and less stable structures have more heat of hydrogenation. Say for example, we are having a question, compare heat of hydrogenation. First structure is CH2 double bond CH2. Second structure is CH3 single bond CH double bond CH2. Third structure is CH3 single bond CH double bond CH single bond CH3. And fourth structure is, say for example, CH3 single bond C single bond CH3 double bond C single bond CH3 single bond CH3. Have a look. First of all, we will count alpha hydrogens. What is alpha? That carbon which is sp3 and is attached to sp2. So these are alpha carbons. So here 12 alpha hydrogens are present. Here 6 alpha hydrogens are present. Here 3 alpha hydrogens are present. Here 0 alpha hydrogens are present. We have to compare heat of hydrogenation for these compounds, for these species. As you can see, only 1 pi bond is present in this, and that. That means number of pi bonds are already equal in all these options. So heat of hydrogenation is inversely proportional to stability. So first of all, let me write down stability of alkenes, stability order of these alkenes. Stability order will be more alpha hydrogens, more stability. So 4, 3, 2, 1. But we know heat of hydrogenation is inversely proportional to stability. So we have to simply reverse this order. So our order becomes, for heat of hydrogenation, order becomes order of heat of hydrogenation, or heat of hydrogenation order becomes, for these, it becomes 1, 2, 3, and 4. So this is our answer. So this alkene is having highest heat of hydrogenation. after that it's having 2, after that 3, after that 4. I hope this is clear to everyone. Let me know in the chats, is this clear to everyone? Please let me know in the chats. Come on, quickly. Let me know in the chats quickly, is this clear to everyone? Let me know in the chats, is this clear to everyone? Is this clear to everyone? Yeah. Okay. Now, after that, application number 5. We are having 5th application, that is bond length. Once again, you must remember, in case of resonance, we have write down this bond length order, and in that we have write down that single bond is a larger bond as compared to partial double bond, as compared to double bond, and as compared to triple bond. This is bond length order. This is bond length order. Bond length order. But according to hyperconjugation, so this partial double bond can be due to hyperconjugation as well. This can be because of resonance, this can be because of hyperconjugation. Now, I will show you. Okay. Now have a look. Have a look. It's a partial double bond character. Now, so partial double bond character can be either because of resonance or because of hyperconjugation. Now, have a look. But if it is because of hyperconjugation, at that time it seems to be a single bond or it seems to be a double bond. When bond seems to be single bond but is actually partial double bond, at that time its bond length is inversely proportional to extent of hyperconjugation. Inversely proportional to extent of hyperconjugation. And here bond length is directly proportional to extent of hyperconjugation. Now, let me show you one example. Compare bond lengths. Compare bond lengths. For example, we have to compare bond lengths like this: CH3, CH double bond CH2. Number second option, CH3, CH2, CH double bond CH2. Third option, CH3, CH, CH3, then CH double bond CH2. Suppose we have to compare bond lengths of X, Y, and Z. Now, the question is, do you know here these are alpha hydrogens, alpha hydrogens, alpha hydrogens? When there are alpha hydrogens, that means there will be hyperconjugation and this bond becomes double and this becomes single. That means sometimes double, sometimes single. That means this is partial double bond. Similarly, this is having partial double bond character. Similarly, this is having partial double bond character. But these are the double bonds which seem to be double bond, but are actually partial double bond character because of hyperconjugation. That means among these X, Y, and Z, these are the partial double bond, but which seems to be double bond. That means we simply use this formula that bond length is directly proportional to extent of hyperconjugation. Means X, Y, among X, Y, and Z, that bond will be larger whose hyperconjugation is more. Now have a look. Here hyperconjugation is because of 3 alpha hydrogens. Here hyperconjugation is because of 2 alpha hydrogens. Here hyperconjugation is because of 1 alpha hydrogens. Can I say? In first case, hyperconjugation will be more as compared to second. In second case, hyperconjugation will be more as compared to third. So now tell me, where is hyperconjugation? More hyperconjugation is present in 1. So more the hyperconjugation, more will be the bond length. So the answer of this question will be simply X, Y, and Z. X, Y, and Z. I hope this is clear to everyone. Let me know in the chats. Is this clear to everyone? Let me know in the chats. Quick. Come on, come on, come on, come on. Let me know in the chats. Quick. Let me know in the chats. Is this clear to everyone? Is this clear to everyone? Come on. Is this clear to everyone? Yes, yes, yes. Okay, guys. Okay, guys. Now, come on. Another question is like this. Once again, you have to compare bond lengths, but the question is like, if you are having CH3, CH double bond CH2, similarly, second option is like CH3, CH2, CH double bond CH2. Third option is CH3, CH, CH3, single bond CH, double bond CH2. If you have to compare bond lengths of this X, this Y, and this Z. Now tell me, this is alpha hydrogen, alpha hydrogens, alpha hydrogen. That means there will be hyperconjugation. So this is not a normal single bond. It seems to be a single bond, but is a partial double bond. Similarly, this is a partial double bond, this is a partial double bond, but this is the partial double bond which seems to be single bond. That means we have to use this one. Structure in which there will be more resonance, there will be lesser bond length. Now tell me, this is having 3 alpha hydrogens. This is having 2 alpha hydrogens. This is having only 1 alpha hydrogen. So, can I say hyperconjugation will be more here, and hence this will be lesser. This bond length will be, say smaller. This will be the smaller bond as compared to this, as compared to this. So the answer here becomes Z, Y, and X. Why? Why this is the answer? Because this is the bond length order. Bond length order. Because we know more the hyperconjugation, lesser will be the bond. So this is bond length order. More the hyperconjugation, lesser will be the bond. Lesser the hyperconjugation, more will be the bond. Larger will be the bond. More the hyperconjugation, shorter will be the bond. And more the lesser will be the hyperconjugation, longer will be the bond. So this bond will be longer than this, than this. I hope this is clear to everyone. Next application is, sixth application of hyperconjugation is directive influence. Directive influence of alkyl groups. Directive influence of alkyl groups. Now have a look. If we are having a benzene ring to which alkyl group is attached which contains at least 1 alpha hydrogen. Listen carefully. Which type of alkyl group? If benzene is attached to that alkyl group, or that type of alkyl group is attached to benzene which contains at least 1 alpha hydrogen. So alkyl group must contain at least 1 alpha hydrogen. That means at that time it shows hyperconjugation. Whenever alkyl group shows hyperconjugation, what will it do? It will donate its electron towards ring and increases electron density of the ring at ortho and para positions. Have a look. And increases its electron density. Increases electron density of the ring at either ortho or para position. Now tell me, any alkyl group which contains at least 1 alpha hydrogen, when it shows hyperconjugation, because of hyperconjugation, it donates electron towards the benzene ring and increases electron density of the benzene ring at ortho and para position. At ortho and para position. So it will be like this. Now, give me a second. Okay. It is C it's H, it's double bond, it's having negative charge, okay, it will result in the formation of this. So tell me, look towards the board and tell me, can I say alkyl groups? But those alkyl groups which show hyperconjugation. Alkyl groups increase electron density of benzene ring at ortho and para positions. Hence R. So इस तरीके से, sorry, that's why as it increases electron density at ortho and para position, so can I say it increases electron density at ortho and para position means it gives direction to the electrophile, go to ortho and para position, as I have already increased electron density of ortho and para. So hence these alkyl groups are ortho para directing with respect to electrophiles due to hyperconjugation. So what is the directive influence of alkyl groups? Alkyl groups are ortho-para directing with respect to electrophile due to hyperconjugation, as these alkyl groups donates electron towards benzene ring and increases electron density at ortho and para position. Number second point, can I say like resonance, hyperconjugation has no effect. Hyperconjugation has no effect on meta position. It neither increases electron density of meta position nor decreases electron density of meta position like that of resonance. Now have a look. If I say how many resonating structures are possible for this, can I say because of this alpha hydrogen it's possible? 1, 2 and 3 are possible. 1, 2 and 3 are possible. Because of this hydrogen, similarly 3 are possible. Because of this hydrogen, 3 are possible. So can we form a formula that in case of benzene derivatives, number of hyperconjugative structures, which involve CH bonds is equal to 3 into number of alpha hydrogens. 3 into number of alpha hydrogens. So you can have a look over here. Here alpha hydrogens are 3. So for this structure we can form 3 into number of alpha hydrogen, that means 9 hyperconjugative structures. So this is 1, 2 and 3 with respect to this. Similarly with respect to this 1, 2 and 3, with respect to this 1, 2 and 3. In total number of alpha hydrogens plus 1 means this structure. Now, so this was all about hyperconjugation. Now there is another term known as reverse hyperconjugation. There is another term known as reverse hyperconjugation. There is another term known as reverse hyperconjugation. Now, what is meant by reverse hyperconjugation? It's also known as minus H. It's also known as minus H hyperconjugation. It's known as minus H effect. First of all, when it's possible, remember, if you are having carbon which is sp2, but this can be either carbon-carbon double bond or this is having this benzene ring. After that, to this carbon there must be one sp3 hybridized carbon to which one good leaving group. Remember, there should be at least one good leaving group, or what we call as well as an electron withdrawing group attached to it. Now, what is meant by good leaving group? Which can depart easily. That means after departure, that should be very much stable, or a weak conjugate basis of, say strong acids, and a weak conjugate base of strong acids are also good leaving groups. Say for example, simple example, if I write like this, CX3, this is halogen. We know when halogen leaves with electrons, say for example Cl, Br or I, so it's stable because negative charge is present on more electronegative element. Now, it becomes positively charged, it will withdraw electron from aromatic ring, so its structure will be like this. So it decreases electron density of the ring. It decreases electron density of the ring at ortho position and then at para position. Have a look. Then para position, and then once again ortho position. Now, if this is what we call hyperconjugation, have a look. If this is hyperconjugation, electrons were donated towards ring. Can I say this is the reverse to that of hyperconjugation? Can I say this is the reverse to that of hyperconjugation? Now electrons are taken away from the ring. As this is reverse to that of hyperconjugation, that's why reverse hyperconjugation. Can I say due to reverse hyperconjugation? Due to reverse hyperconjugation, due to reverse hyperconjugation, can I say due to reverse hyperconjugation, CH3 group decreases electron density at ortho and para position. Now, if electron density is decreased at ortho and para, which will become rich by default, it's meta, so electrophile will go to meta position. So, it decreases electron density at ortho and para position, and hence CH3 group is meta directing with respect to electrophile. Why this is meta directing? Because it decreases electron density at ortho and para. So meta becomes rich by default. So electron loving species goes to that place which is having more electron density, and that is meta. Hence this CH3 group becomes what we call meta directing. Once again, like resonance and hyperconjugation, like resonance and hyperconjugation, reverse hyperconjugation has no effect on meta position, because it decreases electron density at ortho and para, but it does not affect meta position at all. Now, this was all about reverse hyperconjugation. Now, after that, a question is Inductomeric effect. That means this is basically that our permanent effects have been completed. Now, this is a temporary effect, Inductomeric effect. So, what is Inductomeric effect? Have a look. If you are having CCl, H, say CH3Cl, we know sigma electrons will be displaced towards this, so there will be partial transfer of electron, so this will acquire partial negative charge, this will acquire partial positive charge. Now, if the same species is taken, in presence of an external reagent, if same species taken in presence of a reagent, now what will happen? It simply attacks this electron deficient site and it simply increases transfer of electron. Yes or no? Increases sigma transfer of electron. But what was that displacement of electron known as? Inductive effect. So can I say due to presence of this here, inductive effect is enhanced. So what is inductomeric effect? Remember, that effect which enhances or increases, inductive effect. And occurs in presence of external reagent or in presence of a reagent. In presence of a reagent is called inductomeric effect. Or we can simply say when complete transfer of sigma electron takes place, in presence of reagent, that effect is known as inductomeric effect. So basically here it results in the formation of this one. For example, and Cl minus will be liberated over here. So Cl minus will become a leaving group. So this is known as, this is complete transference of sigma electron. Here it was not complete transfer of sigma electron, but here sigma electron is completely transferred towards chlorine, but in presence of this reagent. This is the reagent. Actually it occurs, it actually what we call attacks its unoccupied molecular orbital, that's known as lowest unoccupied molecular orbital, and this is highest occupied molecular orbital. This is basically homo-LUMO interactions, but you don't need to go there homo-LUMO. You have to simply remember like this. So this is simple way to understand what is inductomeric effect. Now, inductomeric effect is simply complete transfer of electrons towards an atom in presence of attacking reagent. Okay. Now, after that, we have another effect known as electromeric effect. We have another effect known as electromeric effect. What is meant by electromeric effect? Have a look. If we are having an unsaturated species, say for example like this, unsaturated species like this, and if in presence of a reagent, if an unsaturated species is taken in presence of a reagent, what will happen? Now have a look. As we know, this reagent is positively charged when it approaches this pi bond electron density. So this pi electron density, it will attract pi electron density towards itself. So here complete transfer of pi electron takes place towards one of the atoms. So complete transfer of pi electron takes place towards one of the atoms. Have a look. Complete transfer of pi electron takes place towards one of the atoms linked together by means of multiple bond in presence of reagent. This is known as what we call electromeric effect. So what is electromeric effect? It's simply complete transfer of pi electrons towards one of the atoms, complete transfer of electron towards one of the atoms linked together by means of multiple bond. In presence of reagent. is called electromeric effect. So what is electromeric effect? It's complete transfer of pi electrons towards one of the atoms linked together by means of multiple bond in presence of reagent. This is known as simply electromeric effect. Now, what are the characteristics of electromeric effect? Now, characteristics. Have a look. So, as per characteristics are concerned, characteristic number one, it is a temporary effect. Point number two, it involves complete transfer of pi electrons. It involves complete transfer of pi electrons. Then, number third, displaced pi electrons during this effect leave their orbital. Next, it is the characteristic property of unsaturated compounds only. Because it does not take place in what we call saturated compounds, as it involves displacement of pi electrons. It is a reversible effect. Once reagent is removed, there will be no displacement. But in presence of reagent, there will be displacement of pi electrons. Next, due to this effect, polarization occurs. Due to this effect, polarization occurs. I hope this is clear to everyone till now. Now, after that, we must know types of electromeric effect. So, types. Have a look. Electromeric effect is of two types. It is of two types. Number one is plus E effect. And number second is minus E effect. Number second is minus E effect. Now, what is plus E? It is that electromeric effect. It is that electromeric effect in which pi electrons are transferred. Pi electrons are transferred towards an atom to which reagent gets finally attached. Reagent gets finally attached. For example, if you are having CH2, double bond CH2, and in presence of reagent, what will happen? When this H positive approaches pi electron density, it will result in the formation of this CH2 positive and CH3. What will happen? Have a look. Here pi electrons are transferred towards this carbon and reagent is also attached to this carbon. That means pi electrons are transferred towards an atom to which reagent gets finally attached. And remember, during this effect, cations are obtained. During this effect, cations are obtained. Now, here it is that effect, it is that electromeric effect in which pi electrons are transferred towards an atom other than the one to which reagent gets finally attached. For example, have a look. If we are having C double bond O and Cn minus is a reagent, now have a look. Cn minus is a reagent, it gets attached to C, but pi electrons are transferred to other atom. So this type of electromeric effect is known as minus E effect, and during this effect anions are obtained, and during this effect cations are obtained. So pi electrons are transferred to that atom to which reagent gets attached. Pi electrons are transferred towards an atom other than the one to which reagent gets finally attached. Now tell me, students, is this clear? Is this clear till now? Now, my dear students, is this clear till now? Let me know in the chats quickly, please. Let me know in the chats quickly. Is this clear till now? Let me know in the chats. Is this clear? Is this clear? Let me know quickly. Let me know quickly. Okay, this is clear to everyone. Now, after that, we must know direction. We must know directions. That in which direction we should, say transfer pi electrons and why. Condition number one, if multiple bond is present between, if multiple bond is present between two similar elements, if multiple bond is present between two similar elements to which similar groups are attached, then pi electrons are transferred in any direction. For example, have a look. Now, have a look. Here, pi electrons are present between carbon and carbon. That means between similar elements. And to this carbon, hydrogens are attached, and to this carbon, hydrogens are attached. That means pi electrons are between two similar elements, and to these elements, identical groups or identical atoms are attached. That means if multiple bond is present between two similar elements to which similar atoms or similar groups are attached, then pi electrons are transferred in any direction, either like this, so that it will result in the formation of this, or you can transfer pi electron in this direction. So whenever negative charge is here, so H positive goes there. So it will result in the formation of CH3, CH2 positive. Both are one and the same because this is ethyl carbocation, this is also ethyl carbocation. So pi electrons can be transferred in either direction, either towards right carbon or towards left carbon. Choice is yours. But this choice is only if multiple bond is between two similar elements to which similar atoms are attached. Now, then second point is, if multiple bond is present between similar elements to which to which different groups are attached, then direction of pi electrons will be decided by electronic displacement effects. For example, what is this? Have a look. Say you are having CH3, CH double bond CH2. Have a look. Pi electron is between carbon and carbon, between similar elements. But to this element, two hydrogens are attached. To this, one hydrogen and one CH3 group is attached. That means multiple bond is present between two similar elements, but groups attached to these elements are different. Here, there are two hydrogens here, one hydrogen and one CH3. That means they are different. So at that time, pi electrons will be transferred in a direction, and that direction will be decided by electronic displacement effects. Now, to this carbon, there are hydrogen. Hydrogen do not show inductive effect. Here, neither shows here what we call hyperconjugation, neither any resonance. But what about this CH3? This CH3 shows plus I as well as hyperconjugation, but hyperconjugation is powerful and the direction of hyperconjugation is towards this. So pi electrons will be transferred in the same direction decided by the electronic displacement effect of this group. Hence, pi electrons in general will be transferred towards this one and hydrogen will be attached to this. So this will form a carbocation more stable in this manner. We can simply transfer electron towards this, but that results in the formation of less stable carbocation. We are talking about majority cases. We are talking about most stable carbocation will be formed like this. Similarly, if we are having a structure like this, OMe, I mean say me means methyl, O methyl, then CH double bond CH, and then it is CH3. This shows hyperconjugation in this direction, and this shows plus R in this direction. That means these two groups show different directions. Now, as we know, hyperconjugation is weaker as compared to resonance, or resonance is stronger as compared to hyperconjugation. So we will transfer pi electron in the direction of a resonance because resonance is powerful effect. So it will be like this. So it will be like this. It will become CH3, then it will become MEO, that means methoxy group is there. After that it is CH, then it is single bond CH2, single bond CH3, and here will be a positive charge. And this positive charge will be stabilized due to back bonding. What is back bonding? When one orbital is completely filled and its adjacent is having an empty orbital. One is having empty orbital, its adjacent atom is having what we call orbital which is completely filled. At that time, overlapping takes place, and that overlapping is known as back bonding. Now, so pi electrons are transferred in a direction that will be decided by electronic displacement effects. I hope this is clear to everyone. After that, point number 3. If multiple bond if multiple bond is present between two dissimilar elements, if multiple bond is present between two dissimilar elements, then pi electrons will be transferred, pi electrons will be transferred towards more electronegative element, towards more electronegative element. For example is like this. If you are having C double bond O, so pi bond is between two dissimilar elements, then at that time pi electrons will be transferred towards more electronegative element, that means towards oxygen. So this will attack over here, so it will result in the formation of an anion. So this was all about hyperconjugation effect. Now we have another concept, but before that, do you want any break or shall I continue? Let me know in the chat box. Before having another concept, which is ortho effect, do you want a break or shall I continue? Let me know in the chats quickly. Let me know in the chats quickly. Do you want a break for your dinner? Do you want a break for your dinner? Completely tell me in the chats. Do you want break for your dinner? Break please, we haven't eaten yet. Okay. Now it's 9:30. Break will be till 10. You can have your dinner and we'll be back at 10 p.m. Take care, have dinner. Hello and welcome back. If I am audible and clearly visible to everyone, let me know in the chat box. Let me know in the chat box. Let me know in the chat box. Come on, let me know in the chat box. Am I audible and visible to everyone? Okay. Now, what is meant by ortho effect? Number one, first of all, we will see ortho effect in case of benzoic acid or its substituted benzoic acid. Now have a look. In case of benzoic acid, ortho effect says ortho substituted benzoic acid is more stronger acid than benzoic acid. So what is ortho effect as per benzoic acid is concerned? So that acidic order will be like this. Ortho effect says if any group is present at ortho position of benzoic acid, that means if any ortho substituted benzoic acid, whether that ortho substituent is electron donating or electron withdrawing, irrespective of electron donating or electron withdrawing nature, ortho substituted benzoic acids are stronger acids than benzoic acids. Remember, this is what we call ortho effect in case of benzoic acid. Why is it so? So we can simply say ortho effect due to SIR means ortho effect due to steric inhibition of resonance. Now try to understand. If I write benzoic acid like this, it's C double bond O single bond OH. Now if this acid loses a proton, it results in the formation of its conjugate base. Its conjugate base will be C double bond O and then O having negative charge. Similarly, if we are having benzoic acid, but now it's ortho substituted, that means I will simply write down G. G means any group which is other than hydrogen at ortho position. Let us suppose this group is a bulky group, then its conjugate base will be like this. Now have a look. As this conjugate base is negatively charged, this is negatively charged, and because of this benzene ring can simply increase electron density of this CO minus due to plus M effect. So can I say electron density of COO minus group increases due to plus R of benzene. In nutshell, if electron density increases, that clearly means that negative charge, magnitude of negative charge is increased, which means magnitude of negative charge of COO minus group is increased. Therefore, stability is decreased, because whenever magnitude of charge is increased, stability will decrease. But here, both the groups are bulky groups, so there will be steric repulsion. Due to this steric repulsion, this CO minus will be in another plane and this ring will be in another plane, so there will be no resonance. So SIR, there will be SIR, steric inhibition of resonance. So we will not take plus R of benzene. That means plus R of benzene is absent now. Now tell me, here ring shows plus R and increases electron density or increases the magnitude of negative charge, and hence destabilizes what we call this carboxylate ion or this conjugate base. But there is no plus R. That means negative charge present over here remains constant. So in these two cases, can I say here negative charge is more as compared to this? So this is less stable as compared to this. Can I say this is more stable? If this is more stable, its acid will be more stronger acid as compared to this. So this is because of what we call SIR. So because of SIR, ortho effect is operating. That means ortho substituted benzoic acid becomes more stronger acid than benzoic acid. So this is due to ortho, due to what we call SIR. Another is ortho effect due to hydrogen bonding. Another one is ortho effect. Ortho effect due to hydrogen bonding. But before that, we will form a formula over here. Now, as you know that SIR increases acidic strength, so we can write Ka. We can write Ka, that means acidic strength is directly proportional to SIR. So more the SIR, more will be the acidic strength. More SIR, more will be the acidic strength. Now have a look. Now ortho effect due to hydrogen bonding. Have a look. If you are having benzoic acid and another is ortho substituted benzoic acid, say for example OH. Now acid will lose H positive and results in the formation of its conjugate base like this, C double bond O, O negative. Here it will result in the formation of a conjugate base like this, C double bond O, O negative, but here it's OH. Between this H and O, there will be intramolecular hydrogen bonding or chelation. So this is intramolecular H bonding or chelation. So can I say this conjugate base is having intramolecular hydrogen bonding, means electrostatic force of attraction between H and O. Hence, this becomes more stable as compared to this. If this is more stable, can I say this acid is stronger acid as compared to benzoic acid? But can I say this becomes acidic? And Ka value of this has been increased, but due to H bonding, due to H bonding. So more the H bonding, more the hydrogen bonding, intramolecular hydrogen bonding, more will be the Ka of, say acid. That means more stronger will be the acid. So it is ortho effect due to H bonding, and this was ortho effect due to SIR. Say for example, we have a question like this: compare acidic strength. Suppose we are having question like this: compare acidic strength. First question is like, we are having COOH and here is CH3. Second is COOH, here is CH3, CH3, CH3. Now, this is bulky group. This is also bulky group, but this is more bulkier as compared to this. So here will be SIR. Due to SIR, its acidic character increases. But as this is more bulky group as compared to CH3, so here will be more steric repulsion, due to which SIR will increase. So therefore, we will say it is 2 is more stronger acid than 1. And what is the reason? Reason is because Ka is directly proportional to SIR. So we know that if group is more bulkier, SIR will be more, SIR will be more, acidic character will be more. Similarly, if I write like this is COOH, and here it is, say for example, Br, then COOH, say for example Cl, and then third one is COOH, and then it is I. So irrespective of electron donating or withdrawing group, as this is ortho-substituted benzoic acid, here this is Br, this is Cl, then this is I. They belong to same group. And we know on moving from top to bottom along a particular group, size increases. So chlorine is having smaller size, bromine is bulkier than chlorine, iodine is most bulkier. So most bulkier means more SIR. So can I say it will be 3, whose SIR will be more SIR, more acidic character. After that it will be 1, after that it will be 2. So more bulkier, more SIR. Similarly, if I write like this, COOH, this is CH3, so there will be SIR, and after that second one is like this, COOH, here it will be CH3, and here it will also CH3. Now here will be SIR on one side only, here it will be SIR on two sides. So more SIR is in case number 2 as compared to 1, therefore 2 is more acidic than 1 according to ortho effect due to SIR. After that, we can have another question. Say we can have this one. COOH, and number second COOH, OH and OH. Now listen carefully. Here was the formula, K is directly proportional to hydrogen bonding, but in conjugate base. But that hydrogen bonding should be present in conjugate base, not in the carboxylic acid or not in acid. That hydrogen bonding should be present in conjugate base. Similarly, this SIR should be in conjugate base. Now, we have to think about conjugate bases. Now, if this H has been replaced, is removed, that means CO minus conjugate base can attract, can show electrostatic force of attraction with this hydrogen as well as with this hydrogen. That means hydrogen bonding will be more as compared to this. So the answer will be 2 greater than 1. So hydrogen bonding in conjugate base is more in 2 as compared to hydrogen bonding in, say conjugate base of 1. So therefore, this will be the answer. But if you are having a question like this, COOH, this is CH3. And number second, you are having like this, COOH, but after that it's OH. That means here it is hydrogen, what we call it's ortho effect, but due to SIR, here it's ortho effect due to hydrogen bonding. Remember, answer is 2 greater than 1. What does that mean? That means ortho effect due to H bonding is preferred over ortho effect due to SIR. That means when we are having two acids, two ortho-substituted acids, in one case there is SIR, there is ortho effect due to SIR, and in another case there is ortho effect due to hydrogen bonding. Ortho effect due to hydrogen bonding increases acidic character more as compared to ortho effect due to SIR. Now, let's practice few more questions. like number 1 is like this. If you are having COOH and then we are having ortho substituent, we are having meta substituent, and we are having para substituent. As well as we are having benzoic acid. According to ortho effect, ortho substituted substituent is more stronger acid than benzoic acid, but you can simply remember that ortho substituted benzoic acid is stronger acid than benzoic acid, as well as more stronger acid than its isomers, whether it is meta isomer or para isomer. So we will write 1. First of all, we will write 1. Why 1? Due to ortho effect. Due to ortho effect. So this is the strongest acid among these. After that, remember this is halogen. Halogen shows -I and +R. But if halogen, say -I of halogen always. Take -I of halogen. So it shows -I, it shows -I. But in this case, there are no groups present at ortho, meta, ya para position. That means at ortho, meta or para, there are hydrogens only, and hydrogens are showing neither +I nor -I, neither +M ya +R nor -R. That's why we will write, normal or neutral. Now, as we are here, the question is compare acidic strength, and for acids, we have to write first of all -I. For acids, we have to write -I. So we will write that -I which is stronger. As meta position is closer to COH, that means distance is less, so it will be stronger. So I will write down 2. After that, I will write down 3. Then I will write down 4. So this will be the order of acidic strength. So this will be acidic strength order. This will be order of acidic strength. Order of acidic strength. First of all, write down that in which ortho effect occurs. After that, remember, after that, you must know these things. For acids, write -R first, then -H, then -I, then neutral, then +I, then +H, and then +R, and then +R. But these should be strong to weak, and these should be weak to strong. But as you know, here are no -R, -H, +I, +H, +R. These are only -I. So -I, we have to write down strong. Strong is whose distance is less, and weaker is whose distance is more. That's why answer is like this. Now, another question, acidic character, is like this. If you have to answer this question, this is COOH, and then here it's OH, then same OH is present at meta position. Same OH is present at meta position, and then it's present at para position. And finally, it's like this. Now, first of all, this will be number 1, because this will be the stronger acid, once again due to ortho effect. After that, it will show -I, because there will be no resonance operating from meta position. And here it will be 2 effects. One is +R, another is -I, but as distance is large, so you can simply write down the stronger one, that is +R. We can neglect -I. Here this is neutral. Now among -I, +R and neutral, first of all -I, then neutral, and then +R. That means first of all you have to write down -I, that means it is 2. After that it's neutral, that means 4. After that it's +R, which means it's 3. So this will be the answer of this question. I hope this is clear to everyone. After that, next question, let us suppose, is like this. It's COOH, then it's CH3, then it's COH, and CH3 is present at meta position, and COOH is present at para position. And you have COOH. Now, first of all, answer will be 1 because of ortho effect. Then this will show plus I, this will show plus H, and this is neutral. So, among plus I, plus H and neutral, have a look. Among plus I, plus H and neutral, first of all neutral, then plus I, then plus H. So, write neutral first. We will write neutral first. So, it's 4, then plus I, that means 2, then what we call plus H, that means 3. So, this will be the answer. But remember, whenever you are having benzoic acid in which ortho substituent is NH2, remember it forever. You have to simply, let's suppose this is there, you have to remember that here ortho effect is not applied. So, the example where ortho effect is not applied is the benzoic acid in which NH2 group is present at what we call ortho position. And why is it so? Have a look. According to ortho effect, this should lose H positive easily. That means this should be the strongest acid according to ortho effect. But as this nitrogen can act as a base, so it can accept this H positive towards itself, so it will result in the formation of a zwitter ion, that means a dipolar ion, and the rate of loss of hydrogen is decreased because this hydrogen will be lost if there will be no base, but due to base this hydrogen cannot be lost from this structure as it is only transferred from one place to another, and this is dipolar ion, negative charge and a positive charge, and this is a very stable because of, I mean to say, intramolecular hydrogen bonding or chelation. That means this can be formed easily. As this can be formed easily, that clearly indicates a rate of loss of H positive ion has been decreased. That means it is not the strongest acid as per ortho effect is concerned. Then what will we do? Have a look. We know that this shows minus I as well as plus R. But among these two, which one is stronger? Plus R is stronger. So I will write plus R. But as signs between these two effects is different, so one is minus, another is plus, that means opposite sign, I will write this is plus R, but this is weaker plus R. Because this negative part means withdrawing, plus means donating, as they oppose each other, so plus R effect becomes weak. What about this? It becomes minus I, this becomes plus R, and this is neutral. Now, first of all, we have to write minus I, so I will write down 2. After that, we have to write down neutral. That means I will write down 4. After that, plus R. But which plus R? Weaker one. You can have a look. Plus R. Write weak plus R first, and after that, strong plus R. That means I will write down this one. That means 1. And lastly, I will write down 3. So this is the acidic order or strength of acidic order. So this is the example. Note down. This is the example. You have to note down that this is the example. This is the example where ortho effect is failed. Where ortho effect is failed due to formation of this zwitter ion. I hope this is clear to everyone. Now after that, We have ortho effect in, ortho effect in case of aniline. Now, what is ortho effect in aniline? That aniline is stronger base than ortho substituted aniline. So this is the basic order. This is the basic order or basicity order. So whenever any aniline is there in which ortho substituent is present, that means ortho substituent aniline is there, whether that substituent which is present at ortho position of the aniline, whether that is electron donating or electron withdrawing, irrespective of that, you have to simply say that ortho substituted anilines are weaker bases as compared to aniline. Now, for example, you have aniline like this. For example, you have aniline like this. And in case of water, say for example, we are having a polar protic solvent, that means water, it will accept H positive and results in the formation of a conjugate acid, anilinium ion. Similarly, if I write ortho substituted aniline, it can form a conjugate acid like this. Now have a look. Water can come, negative part of water can come and will attract this positive part. That means here will be hydration. That means hydration or solvation, simply. Hydration or solvation means, what is meant by hydration or what's meant by solvation? That means water molecules or solvent molecules will surround due to force of attraction around this, and due to hydration or solvation, it becomes stable. But here, when water or say solvent molecules approach towards this positive part, this G bulky group, electron cloud or bulky group will repel water molecule or solvent molecule. This bulky group will repel water molecule or solvent molecule, due to which there will be lesser hydration or lesser solvation due to steric repulsion between electron cloud of bulky group and water molecule or electron cloud of water molecule or electron cloud of solvent molecule. Hence, this becomes less stable. Now tell me, if this is less stable, can I say this is weaker base? If this is more stable because of more hydration, so can I say this is stronger base? So aniline is stronger base as compared to ortho substituted aniline, and this effect is known as SIP, means steric inhibition of protonation. Here protonation rate will be more because this is more stable. As this is less stable, so protonation rate will be less. Addition of proton rate will be less because this is less stable, and this is known as steric inhibition of protonation. So can I say it's due to steric inhibition of protonation that, why steric inhibition of protonation? Because this steric repulsion, due to steric repulsion, there will be inhibition of proton. Why? Due to steric repulsion, this will become less stable. As this becomes less stable, so there will be inhibition of protonation. There will be lesser, addition of proton to this NH2 group. So this is, aniline is what we call more stronger base as compared to ortho substituted aniline, and the reason is SIP, steric inhibition of protonation. Now, say for example, if I say like this, compare basicity. Say for example, you have to compare basicity. Question is like this. Number one is NH2, aniline. Second one is ortho substituted aniline like this. Third one is meta substituted aniline like this. And fourth one is para substituted aniline like this. Remember how to solve this question. First of all, compare aniline with ortho. So can I say it is 1 greater than 2 and reason is ortho effect? Which one is more basic? 1 is more basic than 2 due to ortho effect. Now, compare aniline with meta. Meta is having minus I effect and this is aniline. There is no, this is neutral. And in case of bases, let me tell you, you have to write down first plus R, then plus H, then plus I, then neutral, then minus I, then minus H, and then minus R. Here strong to weak, and here weak to strong. Now have a look. In case of halogen, this is minus I, this is neutral. Which one should I write first? It's neutral. That means, can I say 1 greater than 2? Why 2 becomes weaker base? 1 greater than 3. Why 3 becomes weaker base? And the answer is minus I. After that, this 1, I have to compare this with 4. What is 4? 4 shows minus I effect because in case of halogens, resonance is weaker. So once again, 1 greater than 4. Once again, reason is minus I. So by combining all these factors, can I say 1 is stronger acid than 2, 3 and 4. Now, I have to compare 2, 3 and 4. Now, when I compare 2, 3 and 4, 2 shows minus I, 3 shows minus I, 4 shows minus I. All these are having minus I effect. But I have to write weaker minus I. More distance means weaker minus I. So here answer will be 4 will be first. Say stronger base, after that it will be 3, after that it will be 2 and therefore overall order will be 1, greater than 4, greater than 3, greater than 2. So you have to answer the question like this. Don't use ortho effect because then most of the questions becomes what we call exceptions. Now this is question number 1. Next question. Next question is like this. If you are having an aniline, after that you are having ortho substituted aniline, say for example OCH3, then you are having meta substituted aniline, for example NH2 and then OCH3. After that, you are having para substituted aniline, NH2 and then OCH3. Now, have a look. First of all, I will compare this with ortho. So I will say 1 greater than 2 and the reason is ortho effect. Now, I will compare this 1 with 3. 3 shows minus I and this shows N. So first of all, it's 1 greater than 3 because 3 shows minus I. After that, I will compare 1 with 4. Say aniline with para substituted aniline. This shows plus R effect. And we know plus R comes first, after that N. Have a look. It's plus R first and then N. So I will write plus R. That means I will write 4 greater than 1 and reason is plus R. So combining all these, can I say 1 is more stronger acid than 2 and 3, but 4 is stronger than 1. So 4 is stronger base than 1, but 1 is stronger base than 2 and 3. But I don't know among 2 and 3 which one is stronger base. So I will compare only 2 and 3. So 2 shows minus I effect as well as plus R effect. But among these stronger is plus R. But as we know, plus R effect is stronger effect. As we know, plus R is a stronger effect than I. That's why I write plus R. But signs are opposite. So this is weaker plus R. Now compare this plus R with this plus R. Have a look. We have to write
we have to write stronger one first and then weaker. So this is stronger and this is weaker. So among these, no, we have to compare, not this, we have to compare minus I and plus R. And we know plus R comes first, that means 2, after that 3. Therefore, overall basic order will be 4, 1, then 2, then 3. So, if you say that this is showing ortho effect, this will be the weaker base, it should come at the last, but it's not at the last, it comes before 3. So, another example will be like this. Another example will be like this, but just a moment. Okay. Now, another example will be like this. If you have to compare aniline like this with this one, ortho substituted aniline, meta substituted aniline, and para substituted aniline. First of all, compare ortho substituted aniline and aniline. At that time, aniline becomes more basic. So this is ortho effect, due to ortho effect. After that, compare aniline with this group. This is showing, let me tell you, it's minus I, but this is basically the basic position. This is also the basic position. This group is having more basic positions as compared to this. This is having only one basic position. So more the basic position. So I will write 3 greater than 1. Reason is because of more basic positions. So never use minus I over here, as both are identical and both are bases. After that, I will write this 4, because once again it's having 2 basic positions. So I will write 4 greater than 1, and reason is once again same, because of more basic positions. So by comparing these, I will say that 1 is stronger base than 2, but 3 and 4 are stronger bases than 1. 3 and 4 are stronger bases than 1. That means we have to compare 3 and 4. Now, listen carefully. Both are having similar number of basic positions. Now, I will write, this is minus I, this is plus R. I will write plus R first and then minus I. So, I will write 4 first and then 3. Therefore, overall basic order will be 4, 3, 1 and 2. So, this is the answer. I hope this is clear to everyone. Now, another question will be like this. If you are having aniline and then this aniline is having ortho substituent as OH, then ortho substituent is OH, after that meta substituent is OH, and then finally para substituent is OH. Remember, this is once again an example where ortho effect is failed, because due to ortho effect, this should become the weakest base. That means its conjugate acid means this one. Its conjugate acid should not be stable. But it is very stable because of intermolecular hydrogen bonding. That means ortho effect says its conjugate acid should not be stable, but in actual sense it's stable, hence ortho effect is failed. So how will we answer this question? This is neutral. This shows minus I effect as well as plus R effect, and both
Combining effect will be plus R but weaker one, as here signs are opposite. This is minus I and this is plus R. So first of all, we have to write plus R but stronger one. That means I will write 4, after that I will write 2, after that I will write 1, and then it is 3. So this is the answer of this question. I hope this is clear to everyone. And remember, this is an example where ortho effect is failed. Here, ortho effect is failed. Okay. So, my dear students, this is all for today, and thank you all for this wonderful patience. See you in the next session. Till then, take care, goodbye and good night.